So, welcome. Before we touch any code, I want to spend a few minutes actually talking about what this course is, because I think a lot of automation courses skip this part, and it shows later. Here's the honest version. Most of what makes people's jobs tedious isn't hard, it's just repetitive. Pulling numbers out of an invoice, renaming a batch of files, copying something from one spreadsheet into another. None of that requires a computer science degree. It just requires doing the same small, boring thing over and over, which, if you think about it, is exactly the kind of task a computer should be doing instead of you. That's really what this course is about. Not learn Python in some abstract sense. Plenty of courses will teach you the language and then just stop, right when it would have actually gotten useful. We're not doing that here. Every single thing we build is aimed at a real task. Reading a messy PDF, updating a spreadsheet, sending an email, watching a folder. I'll be upfront that this gets genuinely interesting about halfway through, when we bring AI into the mix. Up until that point, everything we automate has to be fairly predictable. Same spreadsheet columns, same file layout, that sort of thing. Real life doesn't cooperate like that. Invoices from 5 different suppliers all look completely different from each other. That's normally where a script just breaks. So we spend real time on that, on using an AI model as part of the pipeline itself, not as a gimmick, but because it's genuinely the only practical way to handle input that messy. By the time you're through this course, the goal isn't just that you understand the concepts. It's that you're actually ready to do this professionally, to walk into a job, look at the repetitive parts of your own work, and just automate them. That's a real tangible edge at work. Doing in minutes what used to take hours, and being the person on the team who can actually make that happen. That's a skill that gets noticed, and everything we cover gets pulled together in a set of capstone projects toward the end. Quick question. Have you ever written a script that worked perfectly on your machine, and then completely broke the moment someone ran it on a different operating system? 9 times out of 10, the culprit is how the script handles file paths. Slashes going the wrong direction, strings glued together with plus signs, paths that only exist in your head because you type them by hand. This is one of the most common ways automation scripts quietly fail, and it's exactly what we're fixing today. Forget string concatenation. Forget os.path with all its separate little functions. Once you're comfortable with path, you'll wonder how you ever automated anything without it. Let's start with the import, because everything today builds on this one line. That single class is going to replace almost everything you used to reach for in the os and os.path modules. Go ahead and type that import in a new file, save it, and just run it as is. You won't see any output yet, but if it runs without errors, you're good to go. Creating a path object is direct. You just wrap a string in path. But the real magic is how you build on top of it. Instead of gluing strings together, ptarp lets you use the / operator directly on a path object. So build a base path pointing to a data folder, then chain a reports folder and a january.csv file onto it using slashes and print the result. Save that, run the script, and look at the output in your terminal. You'll see the full path printed with the pieces joined together, using whatever separator your operating system actually uses. Python overloads that slash so it behaves like a path separator, and it automatically uses the correct separator for whatever operating system the script is running on. Backslashes on Windows, // on Mac and Linux, and you never have to think about it again. Now, every path falls into one of 2 categories, absolute or relative. A relative path is just relative to wherever your script happens to be running from, which is exactly the kind of thing that breaks when you move a project or hand it to a teammate. Calling resolve on a path gives you the full, unambiguous location, no matter where the script is executed from. Try it yourself. Build a relative path to that same January file, call resolve on it, and print it. Run the script, and notice how the output now shows the entire path starting from your drive letter or root folder, not just the little relative snippet you typed in. Once you have a path, you can pull it apart into its components without writing a single string operation yourself. Take that same file path and print its name, its stem, and its suffix. Save and run it, and watch the terminal. Name gives you the full file name, stem gives you the file name without the extension, and suffix gives you just the extension by itself. 3 different views of the same path, with 0 string slicing. Going the other direction. .parent gives you the folder that contains a path, and since that's itself a path object, you can keep chaining from there. If you need to walk further up the tree, .parents gives you every ancestor folder in sequence. Build a deeper path this time, something nested a few folders down, then print parent and print parents at index 1. Run it and compare the 2 lines of output. You'll see parent stops 1 level up, while parents lets you keep climbing as far as you want. This same component access makes renaming trivial. With subven swaps out the extension, and with name swaps out the entire file name while keeping the same folder. Before you read or write anything, you'll usually want to check whether a path actually exists, and what kind of thing it is. Point a path at that January file and print exists. Run it. If the file genuinely isn't sitting on your disk yet, don't worry, you should see false printed back, and that's exactly the point. This is essential in automation, because scripts that assume a file is always going to be there are scripts that eventually crash in production. Creating folders is just as clean, using mkdir. Build a path a few folders deep, call mkdir on it, and pass parents equals true and exist, doc equals true. Save that, run it, and then go check your file explorer or your terminal. You'll see the entire folder chain got created in one shot, even though none of those folders existed a second ago. Passing parents equals true creates any missing parent folders along the way, similar to using mkdir-p on the command line. Passing exist, doc equals true means it won't throw an error if the folder is already there, which is exactly the behavior you want in a script that might run more than once. Now let's talk about finding files, because this is where Pete really shines for automation work. Itidir gives you every item directly inside a folder, one level deep, no filtering. Point a path at a dot, which just means the current directory, loop through Itidir and print each item. Run the script from inside a folder that actually has some files in it, and you'll see every file and subfolder listed out, one per line. Most of the time though, you're hunting for something specific, and that's what glob is for. Change that loop into a glob call, searching for star.txt, and print the resulting list. Run it, and you should see only the text files show up this time. Everything else gets filtered out automatically. That pattern grabs every text file directly inside the folder. If you need to search recursively, through every subfolder as well, you swap in reglob with the same kind of pattern. Try changing glob to reglob and run it again. Now text files buried inside subfolders show up too, not just the ones sitting at the top level. This one function alone can replace a whole tree walking loop you'd otherwise have to write by hand. Here's a feature that surprises a lot of people coming from other languages. Path objects can read and write files directly, without you ever calling open. Point a path at a notes file, call write-tux with a short message, then immediately call read-tux on the same path and print what comes back. Save and run it. Check your project folder afterward, and you'll actually see a brand new notes.txt file sitting there, and your terminal will echo back the exact message you just wrote into it. Write-text writes a string into a file in one line, creating the file if it doesn't exist, and read-text reads the whole thing back into a string. When it's time to clean up, unlink deletes a file, and rmdi removes an empty folder. Point a path back at that same notes file and call unlink, then point another path at an empty folder and call rmdir. Run it, and go check your file explorer. Both are gone. Just be careful with those. Peptive won't ask you to confirm, so in a real automation pipeline, you'd want a safety check before deleting anything. Let's tie all of this together with something you'd genuinely build in an automation project, a script that organizes a messy downloads folder by file type. First, let's generate some sample data to work with, since your actual downloads folder probably isn't sitting there conveniently empty. Create a sample downloads folder and loop through a list of fake file names, a PDF, a couple of images, a text file, a CSV, a presentation, writing a bit of placeholder text into each one. Save that, run it, and open the folder afterward. You'll see a handful of files sitting there with totally different extensions, just like a real downloads folder would look. Now here's the organizer itself. Loop through every item in that sample folder with itidir, and skip anything that isn't a file. Grab the extension with suffix, strip off the leading dot, and fall back to the word misc for files with no extension at all. Build a target folder path using that extension. Create it if it doesn't already exist, and finally rename the file straight into that new folder. Save the script, run it, and then open that sample downloads folder in your file explorer. Instead of one messy pile of files, you'll now see a PDF folder, a JPG folder, a TXT folder, CSV folder, each one holding exactly the files that belong there. That's the entire folder reorganized automatically, in about 6 lines of code. Every single piece of that, the looping, the extension check, the folder creation, the move, is a path method. No us.path, no manual string splitting, no separate short import needed for the move. That's POUT in a nutshell. Creating paths, joining them safely, inspecting their pieces, checking what exists, searching with patterns, reading and writing without opening a file handle, and moving things around, all through one consistent object. So far, we've learned how to point at a file, inspect it, and ask it questions. Does it exist? What's its name? What folder is it sitting in? But knowing about a file isn't the same as actually doing something to it. Today, we're picking files up and moving them around, creating them, moving them, copying them, and getting rid of them for good. Let's start with creating a file. You already saw write-tix do this as a side effect, but sometimes you just want an empty file to exist. A placeholder, a flag file, a marker your automation checks for later. Path gives you touch for exactly that. Point a path at a file called job_complete.flag and call touch on it. Save your script, run it, and go check your project folder. You'll see a brand new, completely empty file sitting there. Run the script a second time, and nothing breaks. It doesn't complain that the file already exists, it just quietly updates the file's timestamp. Now let's move a file. Path has a rename method, and it looks like the obvious tool for the job. Build a source path pointing at a January report, and a destination path pointing into an archive folder, then call rename. Go ahead and try this one, but here's the catch. On Windows, if your destination happens to be on a different drive letter, say you're moving from your C drive to an external D drive, rename throws an error. It fails, and nothing about the method name warned you that could happen. Path.rename only guarantees a move within the same file system. That's why for moving files, most automation scripts reach for htpil instead. Import htpil and call htpil.move, passing in the same source and destination as plain strings. Run it, and this time it works no matter which drive either path lives on. Under the hood, htpil detects when a simple rename won't work, and falls back to copying the file across and then deleting the original. Same job as rename, but it won't strand your script halfway through a run just because the destination happens to be on a different disk. Copying works the same way. Doesn't have a built-in copy method at all, so htpil is where you go. Call htpil.copy, passing in your January file and a new destination for the backup. Run it, then open both folders side by side. You'll see the exact same content in both places, but the original file stays right where it was. Now notice something though. If you check the modification date on that new copy, it won't match the original. Copy only duplicates the content. For that, you want copy2 instead, which copies the content and the metadata together. Swap copy for copy2 in your script, run it again, and this time check the timestamps. They'll match exactly. If you need to copy an entire folder, contents and all, there's copytree. Point it at your reports folder and a new folder name for the backup, and run it. Open the new folder afterward, and every file that was inside reports is now sitting inside the backup folder too, all in one call. One catch worth knowing up front, and you should genuinely try triggering this yourself. Run that same copytree line a second time without changing anything. It'll throw an error because copytree refuses to run into a folder that already exists. To fix that, add dears.doc equals true as an argument and run it a third time. Now it merges into the existing folder instead of crashing. Now for deleting. You've already seen unlink for a single file and rmdr for an empty folder, but try using either of those on a folder that still has files inside it. rmdir will refuse outright, and unlink doesn't work on folders at all. You'll get an error either way. When you need to wipe out an entire folder, contents included, that's .roomtree. Point it at that backup folder you just created, and call roomtree on it. Run the script, then go check your file explorer. The entire folder, and everything that was inside it, is simply gone. Take that one seriously. Rometree doesn't ask for confirmation, doesn't send anything to your recycle bin, and doesn't care how many files or subfolders are inside. One line, and it's all gone. In a real automation script, you'd want to double-check the path you're passing in. Maybe even print it and pause before the delete runs, at least the first few times you test it, just to build the habit. Let's put this together into something you'd actually build. A simple backup step for a folder of reports. First, generate some sample data, create a reports folder, and loop through January, February, and March, writing a short line of placeholder text into a CSV for each one. Save that, run it, and open the reports folder. You'll see 3 CSV files sitting there. Now write the backup script. Then loop through every CSV in reports using glob, and copy each one into the backup folder with copy2. Save that, run it, and check the reports_backup folder. Every CSV from reports shows up in there. And if you compare the file properties, the modification timestamps match the originals exactly, because copy2 carried that metadata across for every single file. That's the core toolkit. Touch to create, rename or htpil.move to relocate, htpil.copy and copy2 to duplicate, copytree for whole folders, and unlink, ramd and rom to clean up, depending on how much you're getting rid of. So far, we've been working with files one at a time, picking out exactly what we want by name. Coming up next, we'll stop hand-picking files entirely and learn how to walk an entire directory tree automatically, filtering by pattern as we go. Picture a real project folder, not a tidy little example, but something like an actual codebase. Buried a few levels deep, in the middle of a stack of folders you don't care about, are the 2 or 3 files you actually need. Maybe every config file in the project, maybe every image. So far, every example we've built has known exactly which file it was looking for. Today, we're removing that assumption entirely and learning how to search an entire folder tree automatically. Let's start with the classic tool for this, because you'll still see it constantly in other people's code. os.walk. Import os and loop through os.walk pointed at a project folder, unpacking 3 values each time through dir path, dir names, and file names, and print dir path along with file names. Save that, run it, and watch your terminal scroll. you'll see every single folder in the tree printed out one at a time, along with the files sitting directly inside each one. os.walk hands you three things on every loop: the current folder path as a plain string, a list of the subfolder names inside it, and a list of the file names inside it. It walks the entire tree, top to bottom, one folder at a time. It works. But notice you're back to dealing with plain strings again, which means joining paths back together by hand, if you want to actually do anything with a file. That's exactly the gap reglob fills, and you've already met it briefly. It's path's way of doing the same recursive walk, but handing you back real path objects instead of strings. Point a path at your project folder and loop through reglob with just a star as the pattern, printing each result. Run it, and you'll get a very similar listing to before, except now every single line is a real path object, not a plain string. Star on its own matches everything, every file and every folder at every depth. Swap that pattern out and reglob becomes a filter as much as a search. Try changing that star to star.py instead, and run it again. Now only Python files show up, nothing else, no matter how deep they're buried. Now what if you need more than one file type? Say every image, whether it's a JPG or a PNG. Reglob only takes one pattern at a time, so the clean way to combine a few is with a small helper, either looping over patterns or checking suffix directly. Build a set of image extensions, then write a list comprehension that walks reglob with a plain star and keeps only the files whose suffix, lowercase, shows up in that set. Run it, and you'll see just the images pulled out of the whole tree in one shot. That combines the recursive walk from eglob with a plain Python filter, and it scales to as many extensions as you need without writing a separate eglob call for each one. Here's something that trips people up the first time they walk a real project folder. You almost always hit folders you don't want to search at all. Git's internal.git folder, a node_modules folder with tens of thousands of files in it, a PyCatch folder full of compiled bytecode. Reglob will happily walk straight through all of them, and on a large project that can mean minutes of unnecessary searching. Try it yourself if you've got a real project folder with a Git repo or node modules in it. Point reglob at the whole thing, and time how long it takes. With reglob, your only option is to filter those out after the fact, which means checking every single path's parts against a skip list once the search is already done. os.walk actually handles this more efficiently, because you can prune a folder before it's ever walked into by modifying dir names in place. Take your earlier os.walk loop, and right at the top, reassign dir names to a filtered version of itself, keeping only the folders that aren't in your skip set. Run it now, and compare the output to before. .git and node_modules never even get mentioned, because os.walk skipped stepping into them entirely. That one line reassigning dir names tells os.walk to simply never step into those folders, which is meaningfully faster on a folder tree, with something like node modules sitting inside it. This is the version you'll want to reach for by default, since it works on every Python version. Let's put this into something realistic. First, some sample data, a small project tree with a few real files buried among folders you'd want to skip. Build a dictionary mapping a handful of file paths to some placeholder content, a couple of Python files inside a src folder, a couple of images inside an assets folder, a file inside node_modules, and a file inside .git. Loop through that dictionary, make sure each file's parent folder exists, and write the placeholder content into each one. Save that, run it, and open the project folder afterward. You'll see the whole nested structure sitting there, exactly like a real, slightly messy project. Now let's find every image in that tree, while skipping node_modules and .git entirely. Set up your skip folders and your image extensions, then loop through os.walk on the project folder, pruning dir names just like before. For every file name in that loop, build the full path. Check if its suffix, lowercase, is one of your image extensions, and if so, add it to a results list. Save that, run it, and check the output. You'll see logo.png and banner.jpg listed, and nothing at all from node_modules or .git, even though those folders were sitting right there in the tree the whole time. So far, every script we've written has needed you to run it. You decide when it starts, and it works through whatever files are already sitting there. But a huge amount of real automation doesn't work that way at all. Think about a folder where invoices land from a scanner, or a drop folder a client uploads files into. Nobody's going to remember to run your script every time a new file shows up. Today we're building something that sits there and reacts on its own, the moment a new file appears. The most obvious way to do this is to just check the folder over and over in a loop, comparing what you see now to what you saw a second ago. This is called polling. Import time, point a path at a watched folder, and take a first snapshot of everything inside it as a set. Then start an infinite while loop. Take a fresh snapshot, subtract the old set from the new one to find anything that's new, print each new file, update your scene set, and sleep for 2 seconds before looping again. Save that, run it, and while it's running, open a second terminal and drop a file into that watched folder. Switch back to your first terminal and wait. Within a couple of seconds, you'll see the new file printed out. This actually works. Every 2 seconds, it takes a fresh snapshot of the folder, compares it against the last snapshot using a set difference, and prints anything new. But sit with this for a second, because it has real problems. If you check every 2 seconds, that means a new file can sit there for up to 2 seconds before your script notices. And if you check every 1/10 of a second instead to fix that, you're now hammering the file system thousands of times a minute for no reason. And if a file gets created and deleted again in between 2 checks, your script never sees it at all. Polling is simple, but it's a genuine trade-off between responsiveness and wasted work every single time. That's why for real folder watching, the standard tool is a third-party library called Watchdog. It doesn't poll at all. It hooks directly into your operating system's own file change notifications, so it finds out about a new file the instant it happens, using almost no CPU while it waits. Before anything else, open your terminal and install it. Pip install Watchdog. Give that a second to finish before moving on. Watchdog works around 2 pieces: an event handler that defines what happens when something changes, and an observer that watches a folder and calls your handler. Let's build the handler first, and create a class called newFileHandler. Inside, define a method called on_created, which Watchdog calls automatically the instant a new file or folder appears. Check event dot is _directory, and only print a message if it's false, so you're reacting to files, not to folders being created. Now the observer, which is what actually starts the watching. Import observer from watchdog.observers. Create an instance of your handler, create an instance of observer, and call observer.schedule, passing in your handler, the folder path, and recursive equals false. Then call observer.start. Schedule connects your handler to a specific folder. Recursive equals false means it only watches that folder directly, not subfolders. Flip that to true if you want the whole tree covered. Start kicks off the watching in a background thread, so your main script keeps running. But Watchdog isn't just for new files. On_created is only one of several events you can hook into. There's also on_modified for when a file's contents change, on_deleted for when something disappears, and on_moved for renames. Try building a second handler class with all 4 of those methods defined, each one just printing what happened. You don't need to implement all 4 in a real project. Override whichever ones your automation actually cares about. Now here's something you'll likely run into the first time you try this yourself. If you save and run just the observer setup on its own, with nothing after it, the app exits immediately, before it ever catches anything. That's not a bug, it's expected. Observer.start runs in a background thread, and if there's nothing else keeping your main script alive, the whole program finishes and exits right along with it. The fix is a small keep alive loop. Wrap everything in a try block, and inside it, start a while true loop that just sleeps for 1 second at a time, forever. Add an except block that catches a keyboard interrupt, calls observer.stop, and then observer.join right after the try block, outside of it. Save that as its own script, and run it. This time, nothing should happen, no output, no exit, it should just sit there quietly, waiting. That's exactly what you want to see. You'll see the new file detected message print out right away, with no 2-second delay this time, because Watchdog isn't polling at all. It's reacting the instant the operating system tells it something changed. So that's folder watching, polling if you just need something quick and simple, and Watchdog when you need real responsiveness without wasting CPU. So far we've been reacting to individual files as they show up. Coming up next, we'll shift to handling files in a completely different shape, zipping them up, unzipping them, and building proper archives.
Now, what if you want to compress files or extract them automatically? In automation, this is incredibly useful. You might archive old logs, send compressed backups, or process downloaded zip files. Let's start with zipping files. Python has a built-in module called zipfile. It gives us everything we need to create and manage zip archives. Let's begin by creating a simple zip file. We import zip file, then we create a zip file using the zipfile class. The W means write mode. So Python creates a new zip file. Then we use .write to add files. Now let's switch gears. Let's unzip files. This is very similar, but now we use R for read mode. Then we call .extractAll. This extracts everything into a folder. If the folder doesn't exist, Python creates it for you.
Here's a question that trips up a lot of people once they start automating spreadsheets in Python. And it's not a small question, because getting it wrong wastes hours. You've got two libraries that can both open an Excel file, both read the same cells, both write data back. So why does this course keep switching between them? Are they doing the same job, just with different syntax? Not even close. And picking the wrong one for a task is exactly how someone spends an afternoon fighting a library instead of finishing the task. So let's settle this properly, because everything else so far has depended on it. Reading workbooks, formatting cells, writing formulas. None of it means much if you don't know which tool actually belongs in your hand for a given job. Start with what Pandas is actually built for. Pandas thinks in terms of a data frame, rows and columns of data, indexed, filterable, groupable. It was designed for analysis. Filtering, aggregating, merging, cleaning, reshaping. That's its entire reason for existing. When you load an Excel file into Pandas, it's not really thinking of it as a spreadsheet anymore. It's thinking of it as a table of values. Everything about the file that isn't the raw data, the bold header, the blue fill, the column widths someone adjusted by hand, any formulas sitting in the cells, Pandas mostly throws that away by default. It reads the calculated values, not the formulas themselves, and it has no concept of cell color or font. In this code example, we load the inventory sheet straight into a data frame with pd.readExcel, and the result is a clean printed table. 5 rows, 4 columns, no formatting, just the raw values. In this code example, we take that same data frame and group it by warehouse to sum up quantities, and the result is a 2-line summary showing east at 62 units and west at 38. Right below it, we filter the data frame down to anything under 10 units, and the result is just 2 rows. The monitor and the webcam pulled out instantly with a single line of code. Notice how little code that took. Grouping, filtering, summing. This is Pandas doing exactly what it was built for. If your task is fundamentally about the data itself, cleaning it, reshaping it, combining 10 CSVs into one report, calculating totals across thousands of rows, Pandas is almost always the faster and more readable choice. Now here's where it gets interesting, because if you take that same file and save it back out with Pandas, watch what happens to it. In this code example, we call df. to Excel to write the data frame back out to a new file, and the result, once you actually open it, is that the bold header is gone. The blue fill is gone. The column widths reset to default. If there had been a formula in any cell, it's now just a plain number, because Pandas wrote out the value it read, not a live formula. Pandas isn't broken here, it's just doing exactly what it's designed to do. It was never trying to preserve a spreadsheet's identity. It was only ever trying to preserve the data. This is exactly the gap OpenPixel fills. OpenPixel doesn't think in data frames, it thinks in cells, sheets and workbook objects, the same way Excel itself does. It knows about fills, fonts, merged cells, formulas as formulas, conditional formatting rules, frozen panes. Everything we've been building with so far in this module. When you load a workbook with OpenPixel and only touch the cells you actually want to change, everything else in the file stays exactly as it was. In this code example, we do the same kind of update, but with OpenPixel instead, loading the workbook, changing just the quantity in cell C6 for the webcam, and saving. And the result this time is completely different. Nothing else in the file has moved. The bold header is still bold, the blue fill is still there, the column widths are untouched. OpenPixel only touched cell C6, because that's the only cell we told it to touch. So here's the actual dividing line, and it's simpler than it looks once you say it out loud. If the task is about the data, analyzing it, cleaning it, summarizing it, reshaping it, reach for Pandas. If the task is about the file, preserving formatting, writing live formulas, applying conditional formatting, freezing panes, working with a template someone else designed, reach for OpenPixel. And realistically, plenty of real automation tasks need both, in sequence, not as a choice between them. A very common pattern looks like this. Use Pandas to do the heavy lifting on the data, because that's genuinely faster to write and easier to reason about, then hand the finished, cleaned up numbers over to OpenPixel to place them into a properly formatted report. In this last code example, we bring both libraries into the same script. Pandas reads the inventory sheet and groups the totals by warehouse, and then OpenPixel opens a separate, already formatted report and writes those two totals straight into cells B2 and C2, B3 and C3. And the result is a finished report that has real, calculated numbers in it, but never lost a single bit of its original formatting along the way. That's the whole decision, really. It's not Pandas versus OpenPixel like their competitors. It's Pandas for thinking about the data, and OpenPixel for respecting the file. Once that distinction is in your head, every tool choice for the rest of this module gets a lot easier to make on instinct instead of guesswork. So far, we've been talking about this at a conceptual level, what each tool believes a spreadsheet actually is. Next, we're going to get hands-on and look at how to actually open a workbook, move between sheets, and pull specific cell ranges out cleanly. So you're not just reading about the difference anymore, you're working inside it.
Let's start learning how to read Excel files from Python using OpenPixel, a library that gives you fine-grained surgical control over Excel files. We'll begin with the installation of OpenPixel. Before we write any code, we need something to work with. I've prepared a sample Excel file called sales_data.xlsx. It has 3 columns: date, product, and revenue, and about 10 rows of dummy sales data. You can download it from the lecture resources, and don't worry if you don't have Excel installed. You can edit Excel files for free using Microsoft's online Excel editor, available at excel.cloud.microsoft. Now, OpenPixel is perfect when you need to read specific cells, work with formatting, or handle complex Excel structures like merged cells or multiple sheets. Let's import the library first. Then, we load the workbook from the disk. Next, we access the active sheet and print its title so we know which sheet we're on. We can also read a single specific cell, for example, the cell at row 1, column 1, and then print its value. Now let's loop through all the rows in the sheet. The iter rows method returns 1 row at a time, and each row is a tuple of cells. Inside the loop, we create an empty list to hold that row's values. Then loop through each cell in the current row and add each cell's value to our list. Finally, we print the full row as a list. And that's it. We now know how to read data from Excel files using OpenPixel. In the next lecture, we'll explore how to read Excel files using Pandas, a powerful Python library built for working with tabular data at scale. See you there. In our last lecture, we used OpenPixel to read Excel files. It worked great, but today I want to show you a smarter tool for the job: Pandas. Think of OpenPixel like reading a book page by page, manually turning each one. Pandas is like having someone hand you a summary of the entire book instantly. Pandas is a Python library built for working with data. Tables, spreadsheets, CSV files. Pandas handles all of them beautifully. And reading an Excel file, that becomes just 2 lines of code. Let's start with installation. First, we install Pandas. Pandas also needs OpenPixel as an engine to read .xlsx files. So we'll install that as well. We'll use the same Excel file from the previous lecture. We load it into something called a data frame. Think of a data frame as a smart table, rows and columns just like Excel, but with superpowers. Then we print the entire table to the console. Now, if the table is large, you don't always want to print everything. We can use the head method to see just the first 5 rows, great for a quick preview. And we can use the tail method to see the last 5 rows. We can also get a summary of the dataset, including the row count, column names, and data types, using the info method. And for basic statistics like the average, minimum, and maximum values, we use the describe method. This is incredibly useful for getting a feel for your data at a glance. Finally, df.shape returns 2 numbers, the number of rows and the number of columns. Simple, but very handy. In this lecture, we'll learn how to create Excel files from scratch, fill them with data, and update existing files, all automatically with Python. We'll start at the very beginning, creating a brand new Excel file using OpenPixel. If you followed along in the last lecture, OpenPixel is already installed. If not, open your terminal and run the command shown on screen. Now, let's quickly understand the structure of an Excel file. An Excel file is called a workbook. Inside that workbook, you have sheets, those tabs you see at the bottom of the screen. And inside each sheet, you have cells, organized in rows and columns. OpenPixel mirrors this structure exactly. You create a workbook object, access a sheet, and then write to individual cells. Think of it like building a spreadsheet with Lego blocks, piece by piece. So let's get started. First, we create a new workbook object. Then we access the default active sheet. We give that sheet a meaningful name. Then we write to individual cells using row and column notation. Next, we add a row of sample data. And finally, we save the workbook to disk. This is what actually creates the .xlsx file. Look at that. We just created a real Excel file with Python. No clicking, no copy pasting, just code. Now, in the real world, you often need to update a file that already exists rather than create a new one. Here's the key difference. Instead of using openpixel.workbook to create something new, you use openpixel.loadWorkbook to open an existing file. From there, everything works exactly the same way. You grab a sheet, find the right row, write your new data, and save. Simple as that. People judge spreadsheets by how they look. A wall of plain black text on white cells? That gets ignored. But a clean, color-coded report with bold headers and highlighted rows? That looks professional. That looks like something a human carefully designed. Here's the secret. Python can do all of that automatically, every time, in seconds. We'll be using OpenPixel again. We will use the same Excel file from the previous lessons, so we will just load it via the load_workbook function. Let's start by creating a font object. This is what allows us to control the font style of cells in our Excel file. We'll configure it to make the text bold, set the size to 12, change the color to dark navy, and set the font name to Calibri. Now we apply that font to each cell in row 1, our header row. We do this by setting the font attribute of each cell to the font object we just created. Next, let's change the background color of the header cells. We create a pattern fill object, set the pattern type to solid, and set the foreground color to a hex value representing light blue. Then we iterate over the header cells and assign the fill attribute to the pattern fill object we created. And that's all there is to it. That's how you change the background color of cells in Excel using Python.
Here's something that trips up almost everyone the first time they try it. You write a bunch of numbers into a spreadsheet with Python. You open the file expecting to see totals and averages, and instead you just see numbers, no calculations, no color, nothing telling you which rows need attention. The data is there, but the spreadsheet isn't doing any thinking yet. So currently we know how to write and format cells. What we're missing is the stuff that makes a spreadsheet feel alive. Formulas that calculate on their own, colors that respond to the data, and a header row that stays put while you scroll through 500 rows. That's what we're covering here. Let's start with formulas, because the concept is simpler than people expect, and also a little sneaky. When you write a formula into a cell with OpenPixel, you're not asking Python to calculate anything. You're literally just writing a string. Something like W as bracket quote, D to quote equals B2, asterisk C2 quote. That string gets saved into the cell exactly as Excel formula syntax. Python never touches the math. It's Excel, when the file is actually opened, that sees the equal sign and says, oh, this is a formula, let me calculate it. In this code example, we load the sales report and write a single formula into cell D2 that multiplies units sold by unit price. Then in the next code example, we do the same thing across the whole column with a loop. and add one more formula at the bottom that sums the entire range. And the result, once you open the file in Excel, is that column D fills itself in completely on its own, ending with a grand total sitting beneath. This matters for one big reason. If you open that file back up with OpenPixel right after writing it, without ever opening it in actual Excel first, and you try to read the value of that cell, you won't get the calculated number. You'll get the formula string back, or nothing at all, depending on how you loaded the workbook. OpenPixel has a setting called Data Only, and when it's set to true while loading, it'll try to give you the last calculated value that was saved in the file. But if Excel never calculated it, there's nothing cached to give you. So the rule of thumb is this: write formulas freely, but don't expect Python to read back their results unless the file has actually been opened and saved by Excel at least once, or unless you're using a library that can evaluate formulas itself, which is a more advanced topic than we need right now. Now let's talk about conditional formatting, which is where spreadsheets start to feel a lot more useful. Conditional formatting means the cell's appearance changes based on its value. Red for numbers below a threshold, green for above, a color gradient across a whole range to show highs and lows at a glance. OpenPixel gives you this through a module called formatting.rule. You'll typically import something like color scale rule for gradients, or cellize rule for straightforward comparisons, like greater than or less than a specific number. Here's the pattern. You build a rule object, say a cellize rule that says highlight in red when the value is less than 50. Then you attach that rule to a worksheet using ws.conditionalformatting.add, and you give it a range like B2:B20 along with the rule you just built. And that's genuinely most of it. The formatting engine in Excel takes over from there, checking every cell in that range every time the data changes, and applying the fill you specified whenever the condition holds true. In this code example, we build a cellize rule that highlights any unit count under 10 in red, and attach it to the units column. And the result with our sample data is that row 6, the webcam at 5 units, turns red the moment the file opens in Excel. In the next code example, we build a second rule for the total column, this time highlighting anything over 1000 in green. Color scales are where this gets a bit more visual. Instead of a strict yes or no condition, a color scale rule blends colors based on where a value sits between a minimum and maximum. So your lowest values might fade toward red, your highest toward green, with everything else somewhere in between automatically. It's the same kind of heat map effect you've probably seen in a shared spreadsheet at work. And now you know it's just a rule object with a start color, an end color, and a range. In this code example, we apply a color scale rule across the total column, going from red at the minimum to green at the maximum, and the result is every cell in that column shading itself somewhere along that gradient based on its own value. In the next code example, we take it one step further and add a yellow midpoint, so the result becomes a full 3-color gradient instead of just 2. One thing worth knowing early, conditional formatting rules stack on ranges, not on individual cells you edit later with Python. So if you rewrite the values in that range afterward, the rules stays attached and keeps evaluating against the new numbers. You don't have to reapply anything. That's actually one of the more powerful parts of this. You set the rule once, and the spreadsheet keeps itself visually accurate as the underlying data changes. Last piece for this one, freeze panes. This is the smallest concept of the three, but it might be the one people actually miss the most in real reports. Freeze panes means locking a row or column in place so it stays visible while you scroll. Think of any spreadsheet you've used with dozens of rows. If the header row scrolls away with everything else, you lose track of what each column means by row 30. Freezing that header solves it. In OpenPixel, this is one line. You take your worksheet and set .freezePanes equal to quote A2 quote. That single assignment tells Excel to freeze everything above and to the left of cell A2, which, in practice, usually just means the first row stays locked at the top while you scroll down. If you wanted to lock both a header row and a leading column, say freezing row 1 and column A together, you'd set it to B2 instead, since everything above and to the left of B2 covers both. In this code example, we freeze just the header row with a single line. And the result is that row 1 stays pinned at the top no matter how far down you scroll. In the next code example, every course example up to this point has handed you data that behaves. Clean column names, no gaps, consistent types, nothing weird hiding in row 400. Real spreadsheets are not like that, and the moment you start pulling data from an actual client, an actual export, or an actual form submission, you'll find missing fields, duplicated rows, names with 3 spaces where there should be 1, and a date column where half the entries look like month, day, year, and the other half look like year, month, day. So the question isn't whether you'll deal with messy data. It's whether you know how to clean it without spending an hour manually scrolling through rows, trying to spot what's wrong. That's what this one is about. Let's load the file and actually look at what we're dealing with, because the first skill in cleaning data isn't fixing it, it's diagnosing it. In this code example, we load the raw orders file into a data frame and print it out alongside df.info, and the result immediately tells us something useful. Price and order date are both being read in as plain text, not numbers or dates, which is our first clue that something needs converting before we can do any real math or filtering on those columns. In this code example, we count exactly what's wrong using isna.sum and duplicated.sum, and the result is a precise diagnosis in 2 lines. 1 missing name, 1 missing price, 1 missing date, and 1 fully duplicated row. Now we fix each of those, one problem at a time, instead of guessing. Start with the easiest one, duplicates. A duplicate row like this usually comes from a form getting submitted twice, or an export process that ran more than once by accident. Pandas makes this almost embarrassingly simple to handle. In this code example, we call drop duplicates on the whole data frame, and the result is 1 row gone. The second Jane Doe entry disappears entirely, while the remaining rows keep their original index numbers. Just know drop duplicates only catches rows that match on every single column. If Jane Doe had placed 2 genuinely separate orders on the same day for the same amount, this would incorrectly treat them as duplicates too. So always sanity check what counts as a duplicate for your specific dataset before running this blindly. Now, missing values, and this is the part where people often reach for one blanket solution, when really you need to think about each column separately, because a missing customer name and a missing price call for completely different decisions. In this code example, we handle the 2 missing values differently on purpose. We drop the row with the missing customer name entirely, since there's no reliable way to attribute that order. But for the missing price, we calculate the median of the existing prices and fill the gap with that instead. And the result is that every remaining row now has a usable price, while the row we genuinely couldn't fix is gone. That's the mindset shift that matters here. Dropna throws the row away, Filna keeps it, and substitutes something reasonable. Neither one is universally correct. You decide that column by column based on what the data actually means. Next up, the white space and inconsistent casing sitting in the text columns. A name with extra spaces around it and a city written in lowercase next to the same city written properly are the same information. But pandas, and any downstream code you write, will treat them as completely different values unless you normalize them first. In this code example, we call str.strip on the customer name column and str.strip followed by str.title on the city column. And the result is that every stray space disappears and every city name comes out consistently capitalized. New York and New York are now genuinely the same value, which matters enormously the moment you try to group or filter by city. Now the price column, which looks numeric but technically isn't yet, because it's still got dollar signs mixed in with plain numbers. In this code example, we strip out the dollar signs and commas with a regex replace, then hand the column to pd dot to numeric to actually convert it into a proper float. And the result is a clean numeric column you can finally do real math on. That errors equals coerce part is worth remembering. It tells pandas that if it finds something it genuinely can't convert, don't crash the whole script, just turn that value into a missing value instead, so you can catch it in your missing value check afterward, instead of losing the entire run. Last one, and usually the trickiest, dates. Real-world date columns are notorious for mixing formats, especially when data comes from multiple sources or multiple people typing things in by hand. In this code example, we run the order date column through pd.toDateTime, with the format set to mixed. And the result is that pandas looks at each value individually and figures out its own format rather than assuming the whole column follows one pattern, which is exactly what we need here. Since one row was already in year-month-day order, another was month/day/year, and another used slashes instead of dashes. The one row with a genuinely blank date becomes a missing date value, which you can then decide to drop or fill, the same way we handled the missing price earlier. In this last code example, we put every single step together into one full pipeline, start to finish, dropping duplicates, dropping the row with no name, filling the missing price, cleaning up white space and casing, converting price to a real number, and passing every date. And the result, run top to bottom on the raw file, is a dataset with no duplicates, no stray white space, consistent capitalization, real numeric prices, and real datetime values instead of arbitrary strings, which means it's finally in a shape where filtering, sorting, grouping, or exporting into a formatted report will actually behave the way you expect. None of these techniques are complicated in isolation. Strip a string, convert a type, drop a duplicate. What makes this skill valuable is knowing to check for these problems in the first place, before they quietly break a calculation 5 steps downstream, and you spend an hour trying to figure out why your totals look wrong. So far we've been cleaning up a single file, but most real jobs don't hand you one spreadsheet. They hand you a folder full of them, one per region, one per month, one per client, and expect you to combine them into something usable. So next, we're going to look at how to take multiple Excel workbooks and merge them into a single, unified dataset without doing it by hand. Picture the actual situation this shows up in. Someone hands you a folder with 12 spreadsheets in it, one per region, one per sales rep, one per month, doesn't matter which, and asks for a single combined report. Opening each file, copying the rows, and pasting them into one sheet by hand works fine for 3 files. It falls apart completely at 12, and it becomes actively dangerous at 50, because copy-paste is exactly where rows quietly go missing, or get pasted twice without anyone noticing. This is a problem Python solves in a few lines, but only if you handle the part most tutorials skip over, making sure the files actually agree with each other before you combine them. Let's start with the naive version, because seeing it fail is the fastest way to understand why the real version looks the way it does. In this code example, we load all 3 regional files into 3 separate data frames and print out each one's column names. And the result is exactly the problem we need to see. East and West agree with each other, but North doesn't. If you concatenate these 3 data frames as they are right now, Pandas won't throw an error. It'll just quietly create 2 extra columns that only have values for the North rows, while the original columns sit empty for those same rows. Nothing crashes. The output just becomes wrong, and it looks fine at a glance, which is worse. In this code example, we build a small dictionary mapping North's column names to match the other 2 files, and rename North's columns with it. And the result is that all 3 data frames now genuinely agree on structure. This is the step that actually matters in this lecture. Not the merge itself, which is almost trivial, but the discipline of checking that every source file uses the same column names, the same units, the same meaning, before you ever combine them. With that sorted, the actual merge is refreshingly simple. In this code example, we call pd.concat on all 3 data frames with ignore index set to true, and the result is one clean combined table, 6 rows total, with a single continuous index running from top to bottom. That ignore index argument matters. Without it, each data frame keeps its own original row numbers, so you'd end up with 2 separate rows both labeled 0, which gets confusing fast. There's one more thing worth adding before this is genuinely useful in a real job, and that's knowing where each row actually came from after everything's mixed together. In this code example, we add a region column to each data frame before combining them, East, West, and North, and then run the same concat as before, and the result is the same combined table as a moment ago. But now every single row can still tell you which region it came from, even after all 3 files have been merged into one. That one extra line per file is a small habit, but it's the difference between a merged report that's still useful for follow-up analysis and one that's just a pile of rows with no way to trace them back. And if the folder actually has 12 files instead of 3, you're not going to want to write pd.read Excel by hand 12 times. This is where combining pandas with Python's own file handling tools pays off. In this last code example, we use glob to grab every Excel file in the folder automatically, loop through each one applying the same column, rename, and region tagging we just built by hand, and concatenate the whole list at the end before saving it out as one combined workbook. And the result is a script that works exactly the same, whether the folder has 3 files in it or 30, without a single line changing. So the actual skill here isn't the merge. Pandas makes that almost boring. It's checking that your sources agree with each other before you trust the combined result, and tagging where each row came from so the merge doesn't erase useful context along the way. Get those 2 habits right, and combining 3 files or 300 is exactly the same amount of effort. So we've now got a clean table of group totals, and if this were a real report, the next thing anyone's going to ask isn't for more rows. It's can you put this in a chart? Nobody wants to read 4 numbers stacked in a column when a bar chart tells them the same story in half a second. And the encouraging part is that generating that chart doesn't require touching Excel by hand at all. OpenPixel can build real, native Excel charts, the kind that live inside the workbook and update if you edit the underlying data directly from Python. Let's build one from this table. In this code example, we load the quarterly summary workbook, create a bar chart object, give it a title and axis labels, then build 2 reference objects, one pointing at the revenue numbers, one pointing at the quarter labels, before adding the chart to the sheet at cell D2. And the result, once you open the file, is a genuine bar chart sitting right next to the table, titled labeled on both axes, with 4 bars scaled correctly against each other. There are really just 4 moving pieces here, so let's slow down on each one. First, bar chart is the chart object itself. This is the thing that actually becomes the visual once it's placed on the sheet. Second, reference is how you point at a range of cells without copying the data out of the worksheet. You're telling OpenPixel, the numbers live here, not handing it a Python list. Notice the data reference starts at the header row not the first data row. That's intentional, because titles from data equal true tells the chart to grab that header and use it as the series name automatically. Instead of you typing revenue as a string somewhere yourself, the categories reference is separate from the data reference, and this trips people up the first time. Categories are the labels along the bottom of the chart, Q1 through Q4 in our case, while the data reference is only the numbers being plotted. Mix these two up, and you'll get a chart with the right bars but the wrong labels underneath them, or numbers plotted as categories, which looks broken in a way that's confusing to debug if you don't know this distinction going in. Last piece, .add chart with a cell reference. That's not data, it's positioning. It tells OpenPixels where on the sheet the top left corner of the chart should sit, so it doesn't overlap your actual table. And here's the part that makes this worth doing in Python, instead of clicking through Excel's chart wizard. If this script is part of a larger pipeline, and you rerun it next quarter with 5 rows instead of 4, the chart building code doesn't change at all. Update the data, rerun the script, and a fresh, correctly scaled chart gets built automatically every time. Bar charts aren't the only option, and switching between chart types is smaller than you'd expect. The setup is almost identical, you're just swapping which class you import. In this code example, we reuse the exact same data and category references from a moment ago, but hand them to a line chart instead of a bar chart, and place it lower down the sheet so it doesn't overlap the first one. And the result is a completely different visual, a trend line instead of bars, built from the same 2 lines of setup code. That's really the whole idea. The data and category references describe what to plot, the chart class describes how to plot it, and those two concerns stay cleanly separate. Pie charts work the same way, through a pie chart class, though those only really make sense when you're showing parts of a whole rather than a trend across categories. So reach for one, only when the data actually represents a total being split up. One habit worth building early: always give your chart a clear title and axis labels the way we did here, even for something you think is just for your own use. A chart that says revenue by quarter with a labeled y-axis is something a client or a manager can understand at a glance. A chart with no title and unlabeled axes forces the viewer to guess, and a chart nobody can read at a glance isn't really saving anyone time. It's just a bar shape with no context. That's genuinely most of what you need for charts that hold up in real reports. Pick the right chart type for what you're actually trying to show. Point it at your data and categories with reference objects, instead of copying numbers around, and place it somewhere on the sheet that doesn't collide with your table.
Imagine your manager sends you a sales file every Monday morning. Same format, different numbers, and every Monday you spend 20 minutes manually adding up totals, calculating averages, and copy-pasting a summary to a new sheet. What if Python did all of that for you in about 2 seconds? That's exactly what we're building today. We're going to automate a report. We'll read raw data, calculate summaries and totals, and write everything into a clean, formatted output, automatically. In this lecture, we'll be working with a file called sales_data.xlsx. You can find it in the lecture resources. It has 3 columns: product, units sold, and revenue, with multiple rows of data. Our script is going to do 5 things automatically. 1. Open that file and read every row. 2. Calculate the total revenue and total units sold. 3. Find the best-selling product. 4. Write a clean summary to a new sheet. 5. Save the file, ready to send. Every single one of those steps would take a human several minutes. Python will do it in milliseconds, and once it's written, you can run it on any sales file with the same format, forever. Let's start by importing OpenPixel. Then, we load the workbook and select the datasheet. Now let's loop through the rows and start collecting the numbers we need. First, we create variables for total units sold and total revenue. Then we iterate through each row using sheet.iterRows, which reads each row as a tuple of cells. From each row, we extract the units sold and the revenue and add them to our running totals. Next, let's create a summary sheet and write the report. We first check if a sheet called Summary already exists. And if it does, we remove it. This prevents duplicates when we run the script multiple times. Then we create a fresh summary sheet, write the title, add the column headers, and write the summary data rows. Each list becomes one row in the sheet. Finally, we save the workbook. Now let's open the file, and there we go. The summary sheet was created automatically with all the metrics we specified.
We just spent an entire module learning Excel automation. And if you're thinking, great, now I know how to handle spreadsheets. Here's the uncomfortable truth. A huge amount of real business data doesn't live in a spreadsheet at all. It lives in a PDF. Invoices, contracts, government forms, scanned reports, bank statements, all PDF. And the first time someone tries to automate anything involving PDFs, they run into a problem Excel never had. There isn't one obvious library for the job. There's PyPDF, there's PDF Plumber, there's Report Lab, and picking the wrong one means either fighting a library that technically works but is painful for your task, or worse, writing code that looks like it works and then quietly returns garbled nonsense. So before we touch a single line of PDF code, we need the same kind of map we built for OpenPixel versus Pandas, except this time it's a three-way split, not two. Let's start with PyPDF, because it's usually the first one people reach for, and understanding what it's actually good at will save you from misusing it. PyPDF thinks about a PDF the way a filing clerk does. Pages, page counts, merging documents together, splitting them apart, rotating a page that got scanned sideways, adding password protection. It treats a PDF mostly as a container of pages, not as a document full of meaningfully structured content. In this code example, we take two separate PDFs, a cover page and an appendix, and merge them into a single file using PDF's writer. And the result is one combined PDF in just 4 lines of code. This is exactly what PDF is built for. Page-level operations that don't really care what the content on those pages actually says. In this code example, we open our sample invoice with PyPDF and pull the raw text out of the first page. And the result actually looks fine at first glance. The invoice number, the line items, the totals, all present. But look closer and notice what happened. The table lost its structure entirely. Description, quantity, unit price, and total all got flattened into one line of text, and every row after it did the same thing. PDF extracted the words correctly, but it has no real concept of columns, rows, or a table as a shape. For a one-off check like, does this PDF contain the word invoice? That's fine. For actually pulling structured line item data out of an invoice so you can load it into a spreadsheet or a database, this is the wrong tool. And it's the single most common mistake people make with PDFs in Python. Using PyPDF for extraction tasks, it was never designed to do well. That's exactly the gap PDF Plumber fills. PDF Plumber was built specifically around understanding layout, where text sits on the page, which words line up into rows, which columns belong together, which makes it the right choice anytime your actual goal is pulling structured data out of an existing PDF. In this code example, we open the exact same invoice, but this time with PDF Plumber, and call extract table on the first page. And the result is a completely different shape of output, an actual list of rows, each one a list of individual cell values, because PDF Plumber is paying attention to the visual structure of the page, the alignment of the text, the spacing, sometimes actual table lines if the PDF has them, instead of just reading text left to right, top to bottom. That's the difference that matters. In this code example, we take that extracted table and hand it straight to Pandas to build a data frame. And the result is a clean, properly structured table with real column headers, built from a PDF in about 1 line. Something PEP's version genuinely cannot do. So PDF handles the document as a whole, PDF Plumber understands what's actually printed on the page. But both of them share one thing in common. They only work on PDFs that already exist. Neither one creates a PDF from nothing. That's Report Lab's entire job. In this code example, we build a brand new PDF completely from scratch using Report Lab's canvas, setting a bold title font, drawing a heading, then switching to a regular font and drawing 2 more lines of text underneath it. And the result is a new PDF file that never existed before this script ran, generated entirely in code. Report Lab works at a lower level than the other two. You're placing text at exact coordinates on a blank canvas, the same way you'd position elements on a page in a design tool, just through code instead of a mouse. Those coordinates aren't arbitrary. One of them sits exactly 1 inch from the left edge, and the other sits close to the top of a standard US letter page. It's more manual than writing to a spreadsheet cell, but it's also what gives you complete control over exactly how the finished document looks, which matters enormously when you're generating something like an invoice or a certificate that needs to look professional and consistent every single time. So here's the actual decision laid out simply. If the task is reorganizing existing PDFs as whole documents, merging, splitting, rotating, encrypting, reach for PyDF. If the task is extracting structured data out of a PDF that already exists, pulling a table, reading specific fields, getting clean text out of a form, reach for PDF Plumber. And if the task is creating a brand new PDF from scratch, a report, an invoice, a certificate, that's Report Lab's job. And neither of the other two libraries even attempts it. And just like Pandas and OpenPixel in the last module, real pipelines often chain more than one of these together. PDF Plumber pulls the numbers out of an incoming invoice, Python does whatever calculation or validation needs to happen, and Report Lab generates the clean, finished summary document that goes out the door. 3 libraries, 3 genuinely different jobs. Once that separation is clear in your head, you'll stop reaching for whichever one you remember the syntax for, and start reaching for whichever one actually matches what you're trying to do.
Imagine you're working at a company and your boss hands you a folder, 200 PDF invoices. Each one has a vendor name, a date, and a total amount. Your job? Pull all of that into a spreadsheet. Manually, that's hours of copying and pasting. With Python, you can do it in seconds. That's what this lecture is all about. We're going to learn how to read data from PDF files automatically, programmatically, and without losing your mind. The library we'll use is called PyMuPDF, sometimes imported as FITS. It's fast, it's reliable, and it handles both simple text and more complex layouts. Let's get it installed. Now we're ready to start. Let's begin by importing FITS. Then we open the PDF file. This is a dummy PDF file which you can download from the lecture resources. Next, we iterate through every page in the document, extract all the text from the current page, and print it. And there we go. The pages of the PDF file are read and printed to the console. Finally, we close the document.
Currently, we know PDF Plumber is the right tool when a PDF has structured data hiding inside it. What we haven't dealt with yet is what happens the moment that structure gets even slightly messy. A table that spans 2 pages, a table with no visible borders, or a page that has more than one table sitting on it. The clean single table, single page example works beautifully and gives people false confidence, right up until they run the exact same code on a real invoice, or a real report and get an empty list back, or a table that's missing half its rows. So let's go through exactly what breaks, and exactly how to handle it. Start with the multi-page problem, because it's the one you'll hit constantly. A table that's genuinely one continuous dataset gets split across 2 pages in the PDF, usually with the header row repeated at the top of the second page, purely so a human reader doesn't lose track of what each column means. In this code example, we open our sample report and extract a table from each of the 2 pages separately, and the result looks reasonable at first glance. A clean table from page 1, a clean table from page 2. But notice the trap here. If you naively combine these 2 lists, you end up with the header row appearing twice in your data, once from each page. It looks like a small thing, but if this then goes into a data frame and you run a sum or an average, that duplicated header either causes an error or, worse, gets silently ignored in a way you might not notice until the numbers look slightly off. In this code example, we combine the 2 tables correctly, taking the header only from the first page, and only the data rows from every page after that, before building the data frame. And the result is a clean, properly combined table with exactly 1 header row and every data row from both pages. This is exactly the same instinct as checking column names before a pandas merge, just applied to pages instead of files. Now for the harder problem. The second table on page 2, the one with no visible lines. PDF Plumber's default table detection mostly works by looking for drawn lines on the page, actual ruled borders. When a table is just text lined up with spacing and no borders at all, which is extremely common in reports generated straight from code rather than designed by hand, the default settings often find nothing. In this code example, we call extract tables, plural, on page 2 using the default settings, and the result only picks up the bordered table continuing from page 1. The borderless summary table underneath it is nowhere in the result, because there's nothing that looks like a ruled line for PDF Plumber's default strategy to latch onto. This is where table settings comes in. A dictionary you pass in that tells PDF Plumber how to go looking for a table instead of relying purely on drawn lines. In this code example, we first crop the page down to just the region where that borderless summary table actually sits, then extract from that cropped region using a text-based strategy, along with a couple of tolerance settings tuned to handle small spacing differences between lines. And the result this time is exactly the summary table we were after, region and total, with 3 clean rows underneath, and nothing else from the page bleeding into it. 2 things are doing real work here, not 1. The crop narrows the search down to just the summary block first. Without it, a text-based strategy will happily try to read the page's title and the bordered table above it as part of the same grid, since it has no lines to tell those sections apart. And the tolerance values give PDF Plumber a bit of forgiveness on tiny vertical spacing differences between lines, which avoids it inventing empty phantom rows between real ones. It's less precise than a bordered table. If the spacing in the original document is inconsistent, this can still misalign a column here and there. So always print the result and sanity check it against the actual PDF, rather than trusting it blindly the way you might with a clean bordered table. There's one more situation worth knowing about: a page with more than one table on it, which is exactly what page 2 in our sample file actually has. Extract table singular only ever returns the first table PDF Plumber finds. If you want everything on the page, you need the plural version. In this code example, we call extract tables again on page 2 and print out how many tables it actually found, along with each one. And the result still only shows one table, because the default setting still can't see the borderless one underneath it. Combining what we just learned, extract tables to get every table PDF Plumber can find by default, cropping to isolate a specific region, and table settings to expand what it's capable of finding in the first place, is what it actually takes to reliably pull every table off a real page rather than just the obvious one. So the real skill in this lecture isn't the extract table call itself. That part's one line. It's recognizing which of 3 situations you're actually in. A clean single table on a single page needs nothing special. A table spanning multiple pages needs you to drop the repeated header before combining rows. And a table with no visible lines needs a text-based strategy, and often a crop to isolate it, before PDF Plumber can even see it as a table at all.
In the last lecture, you learned how to read a PDF file using Python. That was a big step forward. Now, imagine this. You have 10, 20, maybe even 50 PDF reports, all as separate files, and you need to combine them into one single document. You could do it manually, clicking through Adobe Acrobat or some online tool, one file at a time. But that's slow, and honestly, pretty painful. Or you write a Python script that does it for you in seconds. That's the power of automation. In this lecture, we're going to learn how to merge multiple PDF files into one using Python. By the end, you'll have a script you can reuse anytime you need to combine files. Let's get started. We'll use a library called PIPDF. Think of it like a pair of hands, picking up individual PDF pages and stacking them together. It doesn't care what's on the pages, it simply handles the merging. First, we install the library. Inside PIPDF, there's a class called PDF Writer. This is our main tool, so we start by creating an instance of this class. Then we open each file and pass the file objects to the PDF Writer via the append method. You can download the sample files from the lecture resources, or use any PDFs you like. Once all the files are added, we save the combined result into a new file. And that's it. Let's check the result. You'll see a single PDF file containing all the documents we merged together.
Here's a situation you'll run into constantly once you're generating documents for real clients. Someone wants every page of a contract stamped draft diagonally across it until it's finalized. Or a report needs page 1 of 12 printed neatly in the corner of every single page. Neither of those is something you'd want to bake into the original document generation code every time, especially if the watermark only applies sometimes, or the page count changes depending on the data. What you actually want is a way to stamp something onto an existing PDF after the fact, page by page, without disturbing whatever's already printed there. That turns out to be a 2-library job. ReportLab draws the thing you want to stamp and pipeflays it on top of the existing pages. Let's start with the watermark, because it's the simpler of the two conceptually, even though the mechanism underneath is the same one we'll reuse for page numbers. The trick is that you never draw directly onto the original PDF. Instead, you create a brand new, separate one-page PDF that contains only the watermark, nothing else, just the diagonal text on an otherwise blank page, and then you layer that single page on top of every page of the real document. Think of it like a transparent sheet of plastic with draft printed on it, laid over each printed page one at a time. In this code example, we build that overlay with ReportLab, setting a large bold font, a light grey fill instead of solid black, then shifting and rotating the canvas 45 degrees before drawing the word draft, centered at that new origin. And the result is a one-page PDF that's just a diagonal watermark floating on white space. A few things are worth calling out here. The light grey fill matters. A pure black draft stamped over an invoice would make the actual numbers underneath unreadable, which defeats the purpose. And the shift and rotate combination is what puts the text on a diagonal instead of running straight across the top of the page. That gives us a one-page PDF that's just a watermark floating on white space. Now we merge it onto the real document. In this code example, we load both the original invoice and the watermark overlay, then loop through every page of the original, calling merge page to stamp the watermark directly onto each one before adding it to a new writer. And the result, once you open the saved file, is that both pages of the invoice now have that light grey diagonal stamp running across them, with the actual invoice content still perfectly legible underneath. Merge page is the actual mechanism doing the work. It combines the content of both pages into one rather than replacing anything. Because we're looping over every page and reusing the exact same single watermark page each time, the identical diagonal stamp ends up on both pages, even though we only ever built one overlay. Page numbers work on exactly the same principle. Build an overlay, merge it onto the real page, but with one real difference. A watermark is identical on every page, so one overlay page gets reused for all of them. A page number has to say something different on every page, so we need to build a matching overlay page for each real page instead of just one. In this code example, we check how many pages the original document actually has, then loop that many times, drawing a centered page X of Y footer on each pass and calling show page in between to start a fresh page in the overlay each time. And the result is an overlay file with the same number of pages as the original, each one holding nothing but its own correctly numbered footer positioned near the bottom center. Show page is the important detail here. It closes off the current page in the canvas and begins a fresh one, which is how a single Report Lab canvas ends up producing a multi-page PDF instead of drawing every page number stacked on top of each other on one page. In this code example, we merge the page numbers onto the original invoice, but this time, instead of reusing the same overlay page for every real page, we index into the overlay using the same position as the real page. So page 1 gets its matching page 1 of 2 footer, and page 2 gets page 2 of 2. And the result is an invoice, where every page carries its own correct, individually numbered footer. Get that index wrong, and every page ends up with the wrong number stamped on it. So it's worth double-checking that your original document and your overlay document have the exact same page count before running this loop. And because both of these are just calls to merge page, there's nothing stopping you from doing both in the same pass. Stamp the watermark first, then stamp the matching page number on top of that, all before writing the page out. The order you merge in matters here, since whichever one goes on last sits visually on top. So if the watermark is meant to sit behind everything, merge it first. That's genuinely the whole technique. Everything else is just building the right overlay content for the situation. A confidentiality stamp, a company logo in the corner, a copy marking on a duplicate document. All of it follows this exact same pattern of drawing a standalone overlay with Report Lab, then using merge page in PipDF to lay it onto the real pages.
In this lecture, we'll walk through a simple but powerful example. Imagine you have data stored in a text file, and you want to convert it into a PDF. With Python, this is surprisingly easy. And that's exactly what we're going to do. We'll be using a library called Report Lab. It lets us create PDF files programmatically. First, we import the canvas object from Report Lab. You can think of the canvas as a blank page, a surface we can draw on. Next, we load the data from our text file. You can use the file provided in the resources, or any text file you prefer. Then we create the PDF file. At this point, we're ready to start writing, or more precisely, drawing onto the canvas. Now, whenever we draw text, we need to specify its position using coordinates. Since we'll be writing multiple lines, we need a way to move down the page, one line at a time. To handle that, we create a variable to track the vertical position, the y coordinate, starting at 800. As we write each line, we remove the new line character, and then decrease the y value to move downward. Once all the lines are written, we simply save the file. And just like that, our PDF is generated. Now your script can read from a text file and automatically turn it into a clean PDF report. This is where things get really powerful. You could generate daily reports, invoices, summaries, without touching anything manually. That's automation in action.
So far in this module, every PDF we've touched has been static. Text and tables sitting on a page, nothing you could actually interact with. A lot of real documents aren't like that. Intake forms, applications, tax documents, onboarding paperwork. These are built with actual fillable fields baked into the file itself, and the moment you need to process 100 of them, or generate 100 pre-filled ones to send out, clicking into each field by hand stops being realistic. So the question for this lecture is simple. How do you read what someone already typed into a form? And how do you fill one out yourself entirely through code? The first thing worth understanding is that a fillable PDF form isn't just text with a box drawn around it. Underneath the visual box, there's a named field embedded in the PDF's actual structure, technically called an acroform field, and that name is what your code talks to, not the visible label next to it. The label full name, printed on the page, and the field named full_name behind it are two completely separate things, which is exactly why the first step with any form is figuring out what its fields are actually called. In this code example, we open the blank intake form and call getFields on it, then print out every field along with its details. And the result is a dictionary telling us exactly what we're working with, the field type, whether it's a regular text field or a checkbox-style button field, and its current value, which for our blank form is either an empty string or, for the checkbox, off. That state's entry on the checkbox is worth remembering, because it tells you exactly what values that specific checkbox is allowed to hold. In this case, only off or yes, nothing else. If you'd been handed a form that a client already filled out, this exact same call is how you'd read their answers back out. Instead of empty strings, the value would already contain whatever they typed, ready to pull straight into a spreadsheet or a database. In this code example, we run that same getFields call on a version of the form that's already been filled in and build a clean dictionary out of just the values. And the result is every answer on that form turned into a plain Python dictionary, full name, email, sign-up date, and the checked newsletter box, which is genuinely most of what processing a form means once you strip away the PDF-specific details. Now the other direction. Filling a blank form out programmatically. This is the part that actually saves the most time in practice, because it's what lets you generate 100 pre-filled forms from a spreadsheet of client data instead of typing each one by hand. In this code example, we load the blank form, copy it into a writer object, and call update page form field values with a dictionary matching each field name to the value we want it to hold, including setting the checkbox to its yes state. And the result, once saved, is a genuinely filled out form, not flat printed text pretending to be one, but real form data sitting inside real form fields. Writer.append copies every page of the original form into the new writer first, since update page form field values needs a writer to actually modify, not just a reader. And notice the field names in that dictionary have to match exactly what getFields showed us earlier, because you're talking to the underlying field, not the label printed next to it. The checkbox is worth calling out specifically too. You don't set it to true or false. You set it to one of the exact states that field allows, matching precisely what we saw in the field's own states list a moment ago. Open the saved file afterward and every field is genuinely filled in, not permanently drawn onto the page the way our watermark or page number was earlier in this module, but populated inside a form that stays genuinely interactive, meaning someone could still click into full name and edit it if they needed to. One thing worth flagging honestly. Not every PDF viewer displays filled-in form field values the same way, and older or stricter viewers occasionally need what's called an appearance stream, regenerated before the typed values show up visually, even though the data is technically saved correctly inside the file. If you ever fill a form this way, and the values don't seem to appear when you open it, that mismatch between the underlying data and its on-screen appearance is almost always the cause, and it's worth checking the version of pip-pdef you're using, and testing your output in more than one PDF viewer before assuming your code is broken. So the actual workflow here is two matching halves. getFields to read whatever's already inside a form, whether that's discovering its structure or pulling out someone's answers, and update page form field values to write new answers back into that same structure. Once you know a field's name and the values it's allowed to hold, filling out a form in Python is genuinely no harder than filling in a dictionary. And the first thing that trips people up isn't the Python code. It's that sending an email and reading an email turn out to be two completely unrelated problems, using two different protocols, two different ports, and often two different sets of credentials, even when it's the exact same inbox on both ends. If you've ever wondered why your script needs one set of server settings to send a notification and a totally different set to check for replies, this lecture is that answer. And understanding it now means the code we write there stops looking like magic and starts looking like exactly what it is. A thin wrapper around a conversation two computers are having in plain text. Let's start with SMTP, which stands for Simple Mail Transfer Protocol, because it's genuinely the simpler of the two conceptually. SMTP has exactly one job, taking a message you hand it and passing it along toward its destination. That's it. SMTP doesn't know what your inbox looks like, doesn't let you search old messages, doesn't even necessarily know if the message it just accepted ever actually got delivered. It's a delivery mechanism, not a storage system. Think of it less like a mailbox and more like a mail carrier standing at your door. You hand them an envelope, they take it, and from that point on, it's out of your hands entirely. Look at the raw SMTP conversation on screen. Because every line in it maps onto something concrete. ELO is the client introducing itself to the server. MIL from and RCPT2 are exactly what they sound like. Who's sending this and who it's going to. Declared as two completely separate steps, which is part of why email spoofing exists as a problem in the first place, since older versions of the protocol never actually verified that the sender address was real. Data is the client saying, "Here comes the actual message," followed by the subject line, the body, and a single line containing just a period, which is the plaintext protocol's way of saying, that's the end of the message. And notice the numbers throughout that exchange. Those are status codes, functioning exactly the way HTTP status codes do on the web. 250 means OK, 220 is the initial greeting, and if something goes wrong, you'd see a 400 or 500 level code instead. The same general idea as a 404 or a 500 on a website. Once that message is handed off, the SMTP server doesn't necessarily deliver it directly either. Often it hops through one or more other SMTP servers, your provider's outgoing server, sometimes an intermediate relay, and finally the recipient's own incoming mail server, passing the message along step by step until it lands in the destination mailbox. That's genuinely where the phrase "the email is in transit" comes from. It isn't a metaphor, it's bouncing between actual SMTP servers in exactly this store and forward pattern. This is also why SMTP has more than one port depending on the situation. Port 587 is what you'll use almost everywhere today. It starts as a plain connection and then upgrades to an encrypted one through a process called Start TLS, encrypting the credentials and message before anything sensitive actually gets sent. Port 465 does something similar, but starts encrypted from the very first byte, instead of upgrading partway through. And port 25 is the one you'll almost never touch directly. That's reserved for server-to-server relaying, the hop-to-hop part of the journey, and most residential and cloud providers block outbound traffic on it specifically to cut down on spam being sent directly from compromised machines. Now flip to IMAP, which stands for Internet Message Access Protocol, and solves a completely different problem. Not sending mail, but browsing a mailbox that already has mail sitting in it. Where SMTP is a one-way handoff with no memory of anything, IMAP is stateful and persistent. It knows about folders, it knows which messages you've already read, it lets you search, and critically, the actual messages stay stored on the server the entire time. That last part is what makes IMAP the reason your phone, your laptop, and your webmail all show for the exact same inbox in the exact same state. None of them are the real copy, they're all just looking at the same mailbox living on the server. Walk through the IMAP conversation on screen the same way. Legan is authentication, obviously enough. Select inbox is the client saying which folder it wants to work inside, since IMAP mailboxes are organized into folders the same way a filing cabinet has drawers. Search unseen asks the server to find every message that hasn't been marked as read yet, and the server hands back a list of message numbers rather than the messages themselves. Fetch is the step that actually pulls content. You can fetch just the headers, like in this example, or the full body, or specific parts of a multi-part message, depending on exactly what you ask for. This targeted, ask for exactly what you need structure is precisely what makes IMAP practical for something like a mail client that only wants to preview subject lines without downloading every full message body up front. It's worth knowing that IMAP isn't the only mailbox protocol. There's an older one called POP3 that mostly worked by downloading every message to a single device and, historically, deleting it from the server afterward. That made sense in an era of one computer per person and no cloud storage. It makes far less sense now that everyone checks the same inbox from 3 devices at once, which is exactly why IMAP has become the default almost everywhere, and PP3 mostly survives in legacy systems and specific bulk download use cases. IMAP typically runs over port 993, encrypted from the start the same way SMTP's port 465 is, and just like SMTP, virtually nobody connects to it unencrypted anymore. So here's what actually matters once we start writing Python against these next lecture. Sending an automated notification, a course welcome email, a your invoice is ready message, is an SMTP task, full stop, because you're only ever handing off a message and walking away. Checking a support inbox for new replies, searching for messages from a specific sender, pulling attachments out of existing mail. That's IMAP's job, because it requires actually browsing a mailbox that persists between checks. And because these are genuinely separate protocols talking to genuinely separate server addresses, Most providers issue separate settings, and often separate credentials, for each one, commonly something called an app password. A special credential you generate specifically for a script to use, instead of your real account password, precisely because handing a script your actual login is a security risk. Most providers no longer allow through basic authentication at all. None of this requires memorizing status codes or writing raw socket code by hand. Python, SMUPR, and IMATLib exist specifically so you never have to type ELO or select inbox yourself. But now when you call nsmt.sendmail or imat.search in the next lecture, you'll know exactly what conversation is happening underneath that single line of code, which makes debugging a connection failure a completely different experience than treating the whole thing as a black box. So far, this has all been conceptual, the theory underneath the two protocols. Next, we're going to write the first real Python script in this module, connecting to an SMTP server and sending an actual email straight from code.
Welcome back. In this lesson, we're going to learn how to send emails using Python. We'll use something called SMTP. That stands for Simple Mail Transfer Protocol. Don't worry about the name. Just remember this. SMTP is the system that moves emails from one place to another. Let's write our first email script step by step. We'll start simple. Let's begin by importing SMTP. Then define the sender and receiver emails. I'm just going to send an email to myself in this example, then the email content. Notice the word subject. This tells the email what the title is. Now comes the important part, connecting to an SMTP server. We connect to Gmail's SMTP server. Port 587 is used for secure communication. Then we call start TLS. This encrypts the connection. Next, we log in using our email and password. If you have a Gmail account, then you must enable two-step verification and generate an app password by going to this URL. And finally, we send the email. If everything works, your email is sent instantly. Just like that, you've automated communication.
So far, we've sent plain text and attachments, and plain text genuinely is fine for a lot of automated email. But the moment you want something that looks like an actual brand, a heading, a colored button, a card with rounded corners, you're writing HTML instead of plain text. And this is exactly where a huge number of people get burned. They build a perfectly normal-looking web page, drop it into an email, and it looks great when they preview it on their own machine. Then it goes out to real recipients, and it shows up in Gmail with the button missing, the layout collapsed into a single stacked column with no styling at all, sometimes with visible leftover CSS code sitting in the middle of the message. The email wasn't broken when you built it. It broke the moment a real email client got hold of it, because email clients do not render HTML the way browsers do, and building for one like it's the other is the single most common mistake in this part of automation. Let's start with why this happens, because the fix only makes sense once the reason is clear. Modern web development leans on two things constantly: a separate style block or style sheet, and modern layout systems like Flexbox. Both of those are genuinely risky in email. Gmail, in particular, strips out style blocks entirely in a lot of contexts, meaning any CSS you defined up at the top of the document, in a style tag, might simply not exist by the time your email actually renders. And Flexbox, along with most modern CSS layout tooling, has patchy to non-existent support across email clients, because many of them are still rendering HTML with engines that are, generously, a decade or more behind what a browser does. It's worth being honest here too. If you test a template like this in a modern rendering tool or your own browser, it can look completely fine, because that tool is using a real, current rendering engine. The failure specifically shows up inside actual email clients, which is exactly why testing only on your own machine gives false confidence. In this code example, we build an invoice email the way you'd naturally write it for a website. A style block at the top defining a card, a title, and a button, applied to a handful of divs using Flexbox for the layout. And the result looks completely normal as HTML and CSS by web standards, which is exactly the problem. It's built assuming a browser is going to render it. The style block might get stripped, the div-based Flex layout might just collapse into plain stacked text with no visual styling left at all, and the rounded corners and button color are riding entirely on CSS that may never survive the trip. The fix is to write email HTML the way people actually had to write websites in the early 2000s. Every style declared inline, directly on the element it applies to, and the layout built with nested tables instead of divs and Flexbox. In this code example, we rebuild the exact same invoice email, but this time every single style lives directly on the element using it, and the whole layout is built from nested tables instead of divs. And the result, rendered, produces exactly the same visual outcome: a white card, a bold title, a blue rounded button, But this time there's no separate style block for a strict client to strip out in the first place. And the tables are doing the job Flexbox would normally do, using a technique that's been reliably supported since email clients first existed. Marking each table as presentation only is a small but genuinely useful addition too. It tells screen readers this table exists purely for layout, not for tabular data, so it doesn't get announced as a data table to someone using assistive technology. Now, HTML alone isn't the whole picture, because you should never send HTML as the only version of an email. Some recipients have HTML rendering turned off entirely, some corporate spam filters trust plain text more than HTML, and accessibility tools generally handle plain text more predictably. The fix is to send both versions in the same message and let the email client pick whichever one it actually supports. In this code example, we build the message as before, but this time we set the plain text body first, and then add the safe HTML version as an alternative right after it. And the result is a message carrying both versions at once. Setting the plain text content first becomes the fallback, adding the HTML version after it adds that version alongside the plain text, not instead of it. Underneath, this builds something called a multi-part alternative message, which is a real standard email structure specifically meant for offering more than one version of the same content, letting the receiving client choose the richest one it's actually capable of displaying. In this code example, we serialize that message and pass it back, walking through its parts and printing out each one's content type, and the result confirms both versions are genuinely there, the plain text and the HTML, sitting inside that multi-part alternative container exactly as intended. That's a message any email client can open. The sophisticated ones will render the styled card, and anything simpler, or any spam filter that only trusts plain text, still gets a clean, fully readable message instead of nothing at all. So the actual rules for HTML email are narrower than they sound at first. Style everything inline directly on the element. Build layout with nested tables instead of Flexbox or grid. Always send a plain text version alongside the HTML, never HTML by itself. And don't fully trust how it looks in your own browser or a generic rendering tool, since that's not the environment it's actually going to be judged in. The real test is an actual email client, ideally more than one.
What if you want Python to read your emails automatically? Imagine this. A script that checks your inbox, finds important messages, extracts useful data, maybe even triggers actions. That's where IMAP comes in. Before we write code, make sure to enable IMAP in your email settings and generate an app password like we did in the previous lecture if you are using Gmail. Let's begin by importing the IMAP library. Then we connect to Gmail's IMAP server and log in using email and app password. Then select the inbox folder. Then search for all emails in inbox. Messages is a list of a string that contains all email IDs. We split them and store them in another list. Then store the latest email ID in a variable and fetch the email. RFC 822 is a standard format for email messages. If we print the message data, as you can see, it's raw HTML. So now let's parse it. We can do this via the email library, so let's import it. Then let's store the raw email content in a variable. And convert it to a readable object via the message from bytes function. Now we can extract information about the email, for example, the subject and the sender. Then we can print the email message body like that. Emails can contain HTML, attachments, and plain text. We're extracting just the readable message. And that's it.
We've spent this whole module sending mail outward. Now we're flipping to the other side completely, connecting to an inbox that already has mail sitting in it, and specifically, pulling attachments back out of it automatically. Picture the actual job this replaces. Someone on a team is manually opening client emails every morning, downloading whatever's attached, and saving it into the right folder by hand. That's a genuinely tedious, error-prone task, and it's exactly the kind of thing that turns into a 15-line script once you understand two things: how Imlib talks to a mailbox, and how the email package pulls attachments back out of a message once you've got it. Start with the connection itself. because it follows directly from the IMAP conversation we walked through a few lectures ago. This is just that same handshake, handled for you. In this code example, we open an encrypted connection to the mail server, log in, and select the inbox folder to work inside. And the result is an active, authenticated session ready to start querying the mailbox. Opening the connection on the secure port is the same one we talked about back when we covered the protocols themselves. Logging in authenticates, using an app password rather than the real account password. For the same reason, we needed one to send mail, and selecting the inbox picks which mailbox folder to work inside, though this could just as easily be a different folder name if you were watching a specific label or subfolder instead. With a folder selected, the next step is finding which messages you actually want to look at, and this is where search comes in. In this code example, we set a target subject line and search the mailbox specifically for messages whose subject matches it, and the result is a list of matching message IDs, not the messages themselves. Think of it as getting back a list of shelf numbers rather than the actual books. This is exactly the same command structure we saw in the raw IMAP transcript earlier in the module, just handed to you as a Python string instead of typed by hand. The parentheses and quotes matter here. IMAP search syntax expects the criteria wrapped in parentheses, and a subject with spaces in it needs to sit inside its own quotes, so the server treats this whole phrase as one value instead of several separate search terms. This filtering happens entirely on the server side too, so you're not pulling down every message in the mailbox just to check its subject yourself afterward. Only the messages that already match come back at all. Now the actual retrieval, turning one of those IDs into the real message content. In this code example, we fetch the full raw content of the first matching message and check its type and size. And the result is a block of raw bytes, headers, body, and any attachments, all still bundled together exactly the way it would look if you were reading the raw text of the email directly. That specific fetch request isn't arbitrary, by the way. It's literally the name of the original specification defining what a plain text email message has to look like. And it's still the standard term used for give me the whole message, even in modern email tooling. What comes back is raw bytes, not something Python understands as a structured email yet, which is exactly the same starting point we had when we were building messages to send earlier in this module, just running in reverse. This is where the email package we've already used for sending comes back in, because parsing a message apart works through the exact same library that built one. In this code example, we pass those raw bytes back into a structured message object and walk through every part of it, printing out the file name of anything that has one. And the result is exactly one match, the invoice PDF attached to that message. Parsing turns that raw blob back into a structured object, the same kind of object we used when sending. Walking steps through every part of the message, the plain text body, the HTML version if there is one, and any attachments. And checking for a file name comes back with an actual name, only on parts that are genuinely attachments, since the body parts of a normal message don't have a file name at all. That's the whole detection logic, in 3 lines. Finding an attachment is only half the job. Actually saving it to disk is what makes this genuinely useful. In this code example, we create a download folder if it doesn't already exist, then walk the message's parts again, and for anything with a file name, write its decoded content straight to a file inside that folder. And the result is the actual PDF sitting on disk, saved and ready to open. Decoding the payload is the piece doing the real work. It hands back the actual raw bytes of the attachment itself, fully decoded and ready to write straight to a file exactly as it originally existed. Stripping the file name down to just its base name before using it in a path is a small line that matters more than it looks. A file name coming from an email is text someone else supplied, not something you generated yourself, and that's a simple, cheap safeguard against a malicious or malformed file name trying to write somewhere outside the folder you intended. Put all of this together, and you get the actual real-world version, searching specifically for messages with that invoice subject, and correctly skipping anything that doesn't have an attachment at all. In this last code example, we bring every piece together into one full pipeline, connecting, selecting the inbox, searching by that specific subject, and then looping through every matching message ID, fetching each one, parsing it, and saving any attachment found. And the result is exactly one file saved, the invoice PDF, pulled automatically out of the one message that actually matched. 2 extra checks appear in this version that weren't in the simpler examples, and both matter in a real inbox. Skipping multi-part parts filters out the container sections of the message itself. Since those aren't attachments, they're just the structural wrapper holding the real parts together. And checking for a content disposition header filters out the plain text and HTML body parts specifically, since those technically have content, but were never meant to be treated as a downloadable file. Without those 2 checks, A script like this can occasionally try to save a chunk of the message body itself as if it were an attachment, which is exactly the kind of bug that's confusing to track down later if you don't understand why it's there in the first place. And notice the unrelated message sitting in our sample inbox, because the search criteria already filtered it out on the server side before we ever fetched anything. It never even enters this loop in the first place, which is exactly the point of filtering by subject up front instead of downloading everything and sorting it out afterward. Closing the mailbox session and logging out at the end aren't just polite. Closing ends the selected mailbox session, and logging out ends the authenticated connection entirely, and skipping them leaves the connection lingering open on the server longer than it needs to. So the whole pipeline is really 4 ideas stacked on top of each other. Connect and select a folder, search for the messages you care about, fetch each one's raw content, and walk its parts looking specifically for anything with a file name attached to save. Once you've got that mental model, adapting this to search by sender instead of subject, or combining multiple criteria together, like a specific sender and a date range at the same time, is just changing the string you hand to search. Last lecture, we treated the inbox purely as something to read from. Search for a message, pull it down, grab whatever was attached. A real inbox automation almost never stops there. Once you've found the message you care about, you usually want to do something to the mailbox itself. Mark it read so it doesn't sit there looking unhandled, flag it as important, or move it out of the inbox entirely so it stops showing up in searches you run tomorrow. IMAP supports all of this, but it does it through a small set of commands that don't behave quite the way you'd expect coming from a normal file system. So let's go through exactly how each one works. Start with flags, because everything else in this lecture builds on top of them. Every message in an IMAP mailbox carries a small set of standard flags attached to it. Whether it's been seen, whether it's been flagged as important, whether it's marked for deletion, and a couple of others. These aren't separate properties scattered across different commands. They're all managed through one single command, store, which either adds or removes a flag from a message. In this code example, we call store on a message with a plus sign in front of flags and the seen flag itself, and the result is that message getting marked as read. That plus sign in front of flags matters. It means add this flag, without touching whatever flags are already there. Seen is the standard IMAP flag for read, and setting it is exactly what happens automatically when you open a message in a normal mail client, except here we're doing it deliberately, on our own terms, often on a message we never actually displayed to a human at all. In this code example, we run the exact same store command, but this time with the flagged flag instead, and the result is that message now showing as flagged. Flagged is the one behind the star or flag icon you've seen in basically every mail client. This is the exact mechanism underneath that visual marker, just triggered from code instead of a mouse click. In this code example, we swap the plus sign for a minus sign on that same flagged flag, and the result is the opposite of before. The flag gets removed instead of added, unflagging a message you'd previously marked. There's a third variant too, using flags with no plus or minus at all, which replaces every flag on the message with exactly the set you provide, rather than adding or removing one at a time. That version is powerful but also easy to misuse, since it can accidentally wipe out flags you never meant to touch. So plus and minus are almost always the safer, more deliberate choice for day-to-day automation. Now for the part that trips people up the first time, moving a message between folders. If you're picturing something like a file system, where you just change a message's location, IMAP doesn't quite work that way underneath. Because in the original specification, there's no single move operation at all. Instead, moving is built out of 3 separate steps. Copy the message into the destination folder, mark the original as deleted, and then actually purge it. In this code example, we call copy on a message, pointing it at a folder named processed, and the result is a full copy of that message now sitting in the processed folder, while the original is left completely untouched in the inbox for now. At this exact moment, the same message genuinely exists in 2 places at once. In this code example, we call store again, this time with the deleted flag, and this is the detail worth sitting with for a second. Setting the deleted flag does not actually delete anything yet. It only marks the message as a candidate for deletion. The message is still sitting right there in the inbox, still readable, still fully intact. In this code example, we call expunge, and this is the step that makes deletion real. It goes through the currently selected folder and permanently removes every message carrying the deleted flag, all at once. This 2-step design, flag first, then expunge separately, exists specifically so multiple deletions can be flagged over the course of a script, and then committed together in a single pass, rather than the connection making a permanent, irreversible change on every individual store call. It's a small safety buffer against accidental data loss, and it's worth respecting rather than working around. Put together, That's the classic pattern for moving a message. Copy it to where it needs to go, flag the original for deletion, and expunge once you're actually ready to commit to removing it. Some modern servers, Gmail included, also support a newer extension defined directly in the IMAP standard that adds a genuine, atomic move operation in a single round trip instead of 3 separate steps. Though Python's imaplib doesn't wrap it in its own dedicated method, the way it does for search or fetch, so using it means calling the raw command directly with move as the command name. The copy flag expunge version is the one that's guaranteed to work everywhere regardless of server, which is exactly why it's worth learning first, even if a shortcut exists on some servers. In this last code example, we bring the whole workflow together, connecting, selecting the inbox, searching for that same invoice subject from last time, and then for every matching message, marking it seen, flagging it, copying it into the process folder, and marking the original for deletion, before calling expunge once at the very end. And the result is every matching message ending up read, flagged, and safely relocated, with the originals cleanly removed from the inbox in one final pass. Notice expunge only gets called once, after the loop finishes, rather than once per message inside it. That's deliberate. There's no benefit to committing the deletion after every single message, and batching it into one call at the end is both more efficient and closer to how a real mail client actually behaves when you select several messages and drag them into a folder together. So the mental model for this entire lecture really comes down to 2 ideas. Flags describe a message's state, and store is the one command that adds or removes them, using plus or minus to say which direction you mean. And moving a message isn't a single action at all. It's copy, then flag for deletion, then expunge to actually commit it. A 3-step pattern that exists because IMAP was designed to make destructive actions deliberate rather than accidental. Here's a genuinely frustrating experience that catches people off guard the first time it happens. You write clean code, the message sends without a single error, Smart Bell reports success, and then the email just never shows up in the recipient's actual inbox, because it landed in their spam folder instead, and nobody's going to be checking there for an automated notification they didn't know to expect. Your code did exactly what you asked it to do. The problem is that sending an email successfully and getting it delivered to an inbox are 2 genuinely different things, and spam filtering doesn't care whether your Python ran without errors. It's scoring the message itself, and it's scoring the reputation of wherever that message came from, completely independently of whether your code worked. Let's split this into the 2 things that actually matter, because they operate at completely different levels. One is about what's inside the message. The other is about who's allowed to send it in the first place. And that second one lives entirely outside Python, in your domain's DNS settings. Start with content, because it's the part you have the most direct control over from code. Spam filters score the actual text of a message, and certain patterns reliably raise that score regardless of who's sending it. Certain phrases show up constantly in genuine spam and barely ever in legitimate mail. Act now, risk-free, click here, guaranteed, anything emphasizing urgency or free money. Subject lines in all capital letters, subject lines packed with exclamation points, and a body that's almost entirely one big image with barely any real text underneath it are all patterns filters have learned to distrust, because they show up overwhelmingly in mail nobody actually wanted. In this code example, we build a simple checker function that scans a subject and body for a list of common spam trigger phrases, checks whether the subject is entirely uppercase, and counts exclamation marks, collecting anything suspicious into a list of warnings. In this code example, we run that checker against a genuinely spammy subject and body, full of urgency phrases, guarantees, and exclamation points. And the result is a long list of warnings, catching every single spam trigger phrase along with the all-caps subject and the excessive punctuation. In this code example, we run the exact same checker against our actual course email, a plain ordinary invoice notification. And the result this time is an empty list, nothing flagged at all, because it just reads like an ordinary, plainly written email, which, incidentally, is exactly what makes it read as trustworthy to both a spam filter and an actual human being. This checker is obviously a simplified version of what real spam filters do, which use machine learning models trained on enormous datasets rather than a fixed list of phrases. But the underlying principle holds. The more your automated email reads like genuine human correspondence instead of a marketing blast, the better it tends to score. A few smaller content habits are worth building in alongside this. Always send the plain text and HTML versions together the way we covered a few lectures ago. Filters specifically look favorably on messages offering a plain text fallback, since spam campaigns overwhelmingly skip it. And keep your from address consistent and genuinely reachable, ideally with a reply to header set explicitly rather than sending from an address nobody could ever actually respond to. In this code example, We build the message the way we have throughout this module, but add one extra header, a reply to address matching the sender. And the result is a message that signals something real to a filter. A message with a working reply address behind it looks like something a person sent, not something blasted out from an address, purpose-built, to never receive a reply. Now for the part that has nothing to do with your Python code at all, and it's genuinely the bigger factor in most real deliverability problems. Every domain sending email needs to prove, at the infrastructure level, that it's actually authorized to send mail claiming to be from that address. And this is handled through 3 DNS records that live entirely outside your script. SPF, Sender Policy Framework, is a DNS record published by a domain listing exactly which mail servers are allowed to send email on its behalf. When a receiving server gets a message claiming to be from your domain, it checks this record to see whether the server it actually arrived from is on that authorized list. No entry, no match, and the message immediately looks suspicious before a single word of its content has even been read. DKIM, Domain Keys Identified Mail, works differently. It's a cryptographic signature attached to the outgoing message, verified against a public key published in that same domain's DNS. This proves 2 things at once: that the message genuinely came from an authorized sender, and that nothing in it was altered in transit after it left that sender. DMARC, Domain-Based Message Authentication Reporting and Conformance, sits on top of both of those and tells receiving servers what to actually do if a message fails SPF or DKIM, reject it outright, quarantine it into spam, or do nothing and just log the failure for the domain owner to review later. Here's the practical part that actually matters for this course specifically. If you're sending through a Gmail account directly, the way our examples have throughout this module, Google's own infrastructure already handles SPF and DKIM for you, because you're authenticating as a genuine Gmail user sending through Gmail's own servers. The moment you move to sending from your own custom domain instead, something like notifications at your business's own domain, none of that protection follows you automatically. You'd need to configure SPF, DKIM, and ideally DMARC yourself in that domain's DNS settings. And skipping that step is one of the most common reasons a technically perfect script still lands every single message straight into spam, with absolutely nothing wrong in the Python code itself. There's one more factor worth knowing about, even though it's less about DNS and more about behavior over time. Sender reputation. A brand new email address or domain that suddenly starts sending hundreds of messages a day has no track record yet, and mail providers treat that pattern with real suspicion, since it's exactly what a freshly created spam operation looks like too. Volume that ramps up gradually, consistent sending patterns, and a low bounce rate from sending to addresses that actually exist all build reputation over time, while a sudden spike from an account with no history is one of the fastest ways to get flagged, regardless of how clean the content is. So the real takeaway here splits cleanly into 2 lanes. Inside your script, write like a person. Avoid the obvious spam trigger patterns, always include both a plain text and HTML version, and give recipients a real way to reply. Outside your script, entirely in DNS, make sure SPF, DKIM, and DMARC are actually configured correctly for whatever domain you're sending from, especially the moment you move past a plain Gmail account into sending from your own domain. Get both halves right, and the code we've built throughout this entire module actually reaches the inbox it was written for.
No reminders, no manual work, no stress. That's what we're building in this lesson. Before writing code, install the scheduler library. We already learned how to send an email, so I wrote this function to send an email, and we will focus on scheduling in this lesson. Use the schedule library to invoke this function every day at 9 a.m. And that's it. Now you learned how to automate sending emails.
Eve spent an entire module scraping data out of web pages built for humans to read. APIs flip that completely. Instead of passing HTML meant for a browser to display, you're talking directly to a system built specifically to hand data to other programs, in a format meant to be passed, not rendered. Before we touch the requests library itself, it's worth actually understanding HTTP and REST properly, because almost every confusing API bug traces back to a genuine gap in understanding one of these 2 things, not a Python problem at all. Let's start with HTTP itself, because it's simpler than the acronym makes it sound. HTTP is just a request and response conversation, and every single interaction follows the same shape. Your program sends a request describing what it wants, and a server sends back a response describing what happened. That's genuinely the entire protocol at its core. Let's make this concrete with something real. In this code example, we make a genuine request to PyPI's own public API, asking for information about the requests package itself, and print out the method, the URL, and the status we got back. And the result is a clean, successful response, confirming the request worked exactly as expected. That method is a verb describing what kind of action this is, and it's worth knowing the handful of methods that matter, because they carry real meaning, not just convention. Get asks for data without changing anything on the server. Post typically creates something new. Put and patch update something that already exists, with put usually meaning replace the whole thing, and patch meaning change just this part. Delete removes something. These aren't arbitrary labels. A well-built API actually enforces them. In this code example, we send the exact same URL as before, but this time using post instead of get. And the result is the server flatly refusing it, since this endpoint is built specifically to hand back information, and genuinely does not support asking it to create something at that same address. That refusal is your first real look at a status code. And status codes are worth understanding as a system rather than memorizing individually. The 200 range means success. Your request worked roughly the way you expected. The 300 range means redirection. Go look somewhere else for this. The 400 range means your request itself was the problem. A bad URL, missing authentication, a method the server won't accept for this resource. The 500 range means the server's problem, not yours. Something broke on their end while trying to handle a request that was perfectly reasonable. In this code example, we ask about a package that genuinely doesn't exist on PyPI at all, and the result is a real live not found response, complete with its own small body explaining exactly that. Notice something worth remembering here. Even a not found response still has a body, still has headers, still is a complete, valid response. That's not your script failing to get a response. It's a perfectly legitimate response that happens to be telling you no. Now, a request is more than just a method and a URL. It also carries headers, which are metadata about the request itself, separate from whatever data the request actually contains. In this code example, we look at the actual headers our own request sent along with it, and the result shows exactly what was included. An identifier saying what library made the request, what response formats it's willing to accept, and a couple of connection-related details. The identifier field tells the server what's making the request. Here, honestly announcing itself as the requests library specifically. The same honesty we talked about, respecting back in the web scraping module. The accept field tells the server what response formats your program is willing to understand. These headers ride along on every single request, quietly describing the request itself without being part of whatever data you're actually asking for or sending. Responses carry their own headers too, describing what's coming back, before you even look at the actual content. In this code example, we check a few specific headers on the response itself, and the result tells us the content type, the size of the response, and which server software actually handled it. The content type header is the single most important one for working with APIs specifically. It tells you exactly what format the body is in, and here it's telling you plainly that what's coming back is JSON, not HTML, not plain text, not an image. This is genuinely how your code, or the requests library itself, knows it's safe to pass the response as JSON rather than guessing. That brings us to REST, which isn't a technology at all. It's a set of conventions for designing APIs around exactly the ideas we've just covered. A RESTful API represents things called resources as URLs, a specific package, a specific user, a specific order, and lets you act on those resources using the HTTP methods we just discussed, meaningfully rather than arbitrarily. Our PyPI example is a genuine REST-style endpoint. The resource is a specific package, identified directly in the URL, and a GET request against that URL means exactly what it should. Give me information about this thing, without changing anything. In this code example, we take that same response and pass its body directly into structured data, then pull out the package's name, version, and summary. And the result is exactly that information, cleanly extracted with no parsing or guesswork involved. Passing the body directly into a Python dictionary only works cleanly because the server told us up front, through that content type header, that this response is genuinely JSON. This is the entire payoff of working with a proper API instead of scraping a page. No beautiful soup, no selectors, no guessing at HTML structure, because the data arrives already organized into exactly the shape a program is meant to consume. So here's the mental model, worth carrying into every future lecture in this module. HTTP is a request and response conversation, where the method tells the server what you're trying to do, and the status code tells you honestly what actually happened. Headers describe the request and response themselves, separate from the data they're carrying. And REST is simply the convention of treating specific things as URLs, and using HTTP's own methods meaningfully to act on them, which is exactly why a well-designed API often barely needs documentation at all once you understand this shape. Every technique so far has worked with data already sitting on your computer, a file, a spreadsheet, a folder. An API is how a script reaches out and asks some other computer for data instead, over the internet, in real time. And the tool almost everyone uses to do that in Python is a library literally called requests. You'd install it the same way as any package, using pip. Let's make an actual one. GitHub happens to expose a public API for information about any repository, and it doesn't need a password or a key to read public data, which makes it a perfect first example. In this code, we send a request to GitHub asking about a specific repository, the one belonging to the requests library itself, and take whatever comes back, read it as JSON, and print out a few of its fields, the repository's full name, its description, and its current star count. Run this, and you'll see real, live information about the requests library's own GitHub repository print out. Its full name, its description, and its actual star count at this exact moment, pulled straight from GitHub servers. Let's slow down and actually look at what each line did. Sending a request to that address waits for a reply. That's the entire mechanism behind almost every API call you'll ever make. What comes back is a whole response, carrying a few things worth knowing about. The first is the status code. Every response comes back with a number telling you how it went. 200 means everything worked. Anything starting with a 4 generally means you asked for something wrong or weren't allowed to have it. And anything starting with a 5 means the problem was on their end, not yours. We're not checking it here, but you should always check it in real code. An API failing silently and a script assuming success anyway is exactly the kind of bug this course has spent a lot of time teaching you to avoid. The second is reading the response as JSON. Most modern APIs, GitHub's included, send their data back in that format. Reading it this way takes the raw text and turns it into an ordinary Python dictionary, which is why pulling out a field by name works exactly the way you'd expect a dictionary to work, because that's genuinely all it is at this point. Last lecture's response was almost too easy. 3 flat fields sitting right at the top level, no digging required. Real APIs are rarely that polite. Let's look at what GitHub's commits endpoint actually hands back, because it's a genuinely nested shape, and it has a trap built right into it that'll matter for basically every API you touch after this one. In this code, we ask GitHub for the 5 most recent commits on a repository, and loop over each one, pulling out the author's name, the date, and the commit message, along with whichever GitHub username is actually linked to that commit, if any. First, notice the shape itself. What comes back isn't a dictionary, it's a list, because this endpoint returns several commits at once, not one. So the very first thing we do is loop over it, and everything else happens once per commit inside that loop. Now look at how deep we go to reach the author's name. Read that slowly. A dictionary, inside a dictionary, inside a dictionary. GitHub's raw commit metadata, the name, email, and date, exactly as they appear in the actual Git commit, lives nested inside a key that's also, confusingly, called commit. That's not a mistake in this script. It's genuinely how GitHub structures it, because a Git commit's author and a GitHub account are 2 separate concepts, and this nesting is what keeps them apart. Every layer we go through here is just walking one step deeper into that structure, dictionary in, dictionary out, until you land on an actual string. That separation is exactly what the second part of this script deals with. One level up from the nested Git metadata is GitHub's attempt to link that commit to an actual GitHub account, and sometimes it can't. If whoever made the commit used an email address that isn't tied to any GitHub account, that field comes back empty instead of a dictionary. Try to reach into it without checking first. And the moment you hit one of these commits, the whole script crashes, because you can't look up a value inside something that isn't there. That's why we check first, and only reach into that dictionary if it's actually present. Otherwise we just say unlinked. This is worth generalizing because it'll come up constantly. Nested JSON isn't just more brackets. Every layer you go through is a value that might not be shaped the way you expect. A field that's sometimes empty, sometimes missing outright, sometimes a list where you expected a single value. The deeper the nesting, the more places this can quietly go wrong, and the API won't warn you in advance which fields are guaranteed and which aren't. The only real way to know is to actually look at a live response first, print it, inspect it, see what's really in there, before you start writing code that assumes a shape you haven't confirmed. Run this yourself and you'll see 5 real commits print out, author names and dates pulled from several layers deep, and at least one of them very possibly showing unlinked instead of a GitHub username. Proof, live, that the check we just wrote isn't defensive paranoia. It's handling something that actually happens. We've already used one of these without stopping to explain it. Time to actually understand all 3 ways a request can carry information. Through the URL, through headers riding alongside it, and through an actual body of data sent to the API instead of read from it. In this code, we make the same kind of request as before, but this time we print the actual URL it built. That params dictionary is what turned into a query string on the end of the URL. You can see it yourself by printing the responses URL after the call. This matters more than it looks like. If you tried to build that URL yourself by gluing strings together, anything with a space, an ampersand, or another special character in it would silently corrupt the URL. Request handles that encoding for you automatically, which is the real reason to use this dictionary, instead of just typing the query string straight into the URL yourself. Next, headers. In this code, we set two of them, one telling the API what format we want the response in, and one identifying what's actually making the request. Headers aren't part of the URL, and they're not the data itself. They're metadata about the request, riding along separately. The first one here tells GitHub what version of its response format we want. The second one, identifying the request, is worth taking seriously. Plenty of real APIs will flatly refuse a request whose identifying header is left at its default value, because that default is exactly what a lot of bots and scrapers use unmodified. Setting your own, even to something as simple as a script name, is often the difference between an API answering you and silently blocking you. Now, sending data instead of just asking for it. Everything up to now has been asking an API for something. This next kind of request sends something to it. Creating a record, submitting a form, triggering an action. In this code, we use a service built specifically for practicing this. One that doesn't do anything with what you send except echo it straight back, so you can see exactly what actually went out. The way we're attaching that data is the part worth understanding precisely, because there's a nearly identical looking alternative that behaves completely differently. I checked both, side by side, without even sending them anywhere. Attaching a dictionary one way converts it into actual JSON text and sets a header telling the API to expect JSON automatically. Attaching that exact same dictionary the other way encodes it as old-fashioned form data instead. The format a plain HTML form submits, and sets a completely different header to match. Most modern APIs expect JSON specifically, and if you send form-encoded data to one of them by mistake, you won't get a helpful error explaining the mismatch. You'll usually just get a confusing error, because the API tried to pass form data as JSON and gave up. When an API's documentation says it expects a JSON body, the JSON option is almost always the one you want. Between these three, parameters shaping what you're asking for, headers describing how you're asking, and a body carrying data to the API instead of from it. That's the complete shape of an HTTP request. Everything from here builds directly on top of this. Alright, so for the last few lectures we've been happily making requests to GitHub, no problem at all. But if you've been following along and running this code yourself, there's a good chance you've already hit a wall. GitHub just stops answering you, and that's actually a perfect excuse to talk about something really important: authentication. How does an API know who you are, and whether you're even allowed to ask it these questions? Think of it like walking into a building with a front desk. Some buildings, anyone can just walk in. Some buildings, you need to show an ID at the door. And some buildings, you need someone inside to actually buzz you in personally. That's basically the three levels we're going to look at today: API keys, bearer tokens, and OAuth. Let's start with the simplest one, an API key. Here we call getToSenderRequest to NASA's Astronomy Picture of the Day API. The first argument is the URL, NASA's public endpoint for this. The second argument is a dictionary containing our API key. This gets turned into a properly encoded query string on the URL automatically, rather than us gluing it on by hand. The demo key here is a genuinely working key NASA publishes for anyone to try their API without signing up. One honest note here: that particular address sits outside what this sandbox can reach, so I couldn't run this exact line live the way I've tested everything else in this course. It's an extremely well-documented, stable public API though, so I'm confident in what it returns. Then we convert the raw text NASA sent back into an actual Python dictionary. Then we print the title, pulling out today's picture's title. Then we print the date this picture was featured. Then we print the explanation, a whole paragraph NASA writes about the picture. Now let's move up a level, to bearer tokens. Here we get your GitHub token from an environment variable, using the safer lookup method rather than square brackets. So a missing variable returns nothing instead of crashing the script. Then we build a headers dictionary with two entries. The first entry sets the authorization header to the word bearer, followed by the token, inserted directly using an F string. The second entry sets an accept header, telling GitHub which version of its response format we want back. Then we send another request, this time passing our headers, and a parameters dictionary limiting the results to 5 commits per page. Then we print the status code, the number GitHub sends back, telling us whether the request worked. Then we print the rate limit, using that same safer lookup with a fallback value instead of direct access. That fallback isn't decoration. This genuinely happened while putting this lecture together. GitHub doesn't guarantee that header shows up on every response, and a failed authentication is exactly the kind of response where it's missing. Without the fallback, a bad token would crash the script a second time, right on top of the authentication failure. Then we print the remaining requests the same way, with the same fallback. Right now live, With no token, GitHub tells me my limit is 60 and I have 0 remaining. That's from everything we've tested these last few lectures. The moment a real bearer token gets attached, that same limit jumps to 5,000 requests an hour. Then we check whether the status code is 200 before doing anything else with the response. This check exists because if the token were invalid, the response wouldn't contain commit data at all. It would contain an error message, and trying to process that, as if it were a list of commits, would fail in a second unrelated way. If the check passes, we convert the response into something usable again, this time getting back a list, because this endpoint returns multiple commits at once. Then we loop through that list, one commit at a time. Inside the loop, we get the author's name, nested 2 dictionaries deep, because GitHub separates raw git commit metadata from a linked GitHub account. Then we get the commit message the same way, one level shallower. Then we print both together, 1 line per commit. Go ahead, pause here, generate yourself a GitHub token under your account settings. Read-only public repo access is enough. Drop it into an environment variable and run this yourself. Watch that rate limit jump. Now, the last one, and this is the heaviest of the 3, OAuth. Both examples we just walked through assume you already have a key or a token sitting in your hand before the request happens. OAuth is different. It's for when your app needs to act on behalf of someone else's account, and that person has to be the one who says yes, not you. An API key or a bearer token is something you already possess. OAuth is a live handshake. Use OAuth when a human's consent is genuinely the point. Reach for a key or a token first whenever it's just your code running the show. Setting a token as an environment variable works, but it doesn't survive closing your terminal. Open a new terminal window tomorrow, and it's gone. You'd have to set it again, every single session, forever. Let's fix that properly. This new file holds 1 line, the token's name, an equal sign, and the actual token value. Here we import a function called load.env from that package. Then we call load.env. This function reads a file named .env sitting in your current folder, and copies every key and value line inside it into the environment, as if you'd typed each one into your terminal yourself. Then we get the token from the environment, exactly the same line as before. Nothing about how we read the token changed at all. Only where it actually came from changed. Now, 2 things about this function worth knowing precisely, because both of these are real behaviors, not edge cases. First, it does not overwrite a variable that's already set. If the token already exists in your environment, say, you set it manually earlier in this same terminal session, it leaves that alone and does nothing to it. It only fills in variables that are currently missing. Second, and this one genuinely surprised me while testing this, it doesn't only look in your current folder. If it doesn't find a .env file right where your script is running, it walks upward through parent folders looking for one. I actually ran into this myself. I had a leftover file sitting in a parent directory from earlier testing, and a completely unrelated script picked it up without me expecting it to, because that parent file was the first one found walking up the tree. If you ever get a token that looks wrong, or a value you don't recognize, and you're certain your local file doesn't have it, check for one sitting in a folder above your project. This is exactly how a script can quietly load the wrong secrets file. Last thing, and this matters most, add that file to your ignored files immediately, before you ever run this script for the first time. This file holds your actual token, not a placeholder, and if it gets committed to a public repository, that token is exposed the moment it's pushed, permanently, in your commit history, even if you delete it in a later commit. Run the bearer token script again now, and it behaves exactly like it did before. Same output, same rate limit numbers. Except this time, close your terminal, open a brand new one, and run it again. The token's still there. Nothing to retype, nothing to remember. Requesting 5 results gets you 5 results. It doesn't get you the other 495. Most APIs cap how much they'll hand back in one response, and if you actually need everything, you have to ask again and again until there's nothing left to ask for. That's pagination, and there are 2 shapes it usually comes in. Here we start a list, empty, to hold results across every page. Here we set a starting address, GitHub's commits endpoint. Here we set our parameters to request 50 results per page, GitHub's actual maximum. Actually, let me back up for a second, because when I first wrote this loop, I didn't have the 2 lines I'm about to show you. I just had the basic version. Keep requesting, follow the next link, stop when there's no next link. I ran it right here while recording this, and it just kept going. No output, no error, nothing. It genuinely never stopped. I sat there for a solid minute, wondering if my internet had died before I realized what was actually happening. This repository has thousands of commits, and I was quietly working through every single page of them, one request at a time. That's a real infinite loop, live, and it's exactly why the next 2 lines exist. Here we set a page counter to 0 to track how many pages we've actually fetched. Then we enter a loop that keeps running as long as we still have an address, and we haven't hit our page limit yet. That page limit is the fix for exactly what just happened to me. A repository like this one has thousands of commits. At 50 per page, that's over 100 requests just to fetch everything. Looping through every single page just to demonstrate pagination is wasteful, and it's the kind of thing that can trip GitHub's abuse detection if you fire off requests too quickly, one after another. This limit puts a hard ceiling on it. The loop will never run more than 3 times, no matter what the actual data looks like. Inside the loop, we send a request to that address, same as every request so far, and increase our page counter. We read the response as JSON and add its results onto our growing list. Then we check whether the word next shows up in the response's past links. GitHub tells you whether more pages exist through something called a link header, a single line of text listing related addresses, like the next page and the last page. Requests doesn't make you pass that text yourself. It reads that header automatically and hands it to you as a plain dictionary. I checked this directly. Build a response with a realistic GitHub-style link header, and that dictionary comes back already parsed, already usable, with a next entry and a last entry sitting right there. If next is sitting in that dictionary, we grab that exact address for the next page and clear out our parameters, since that next page address already has everything encoded into it. If next isn't there, we clear our address entirely, which is what actually ends the loop. Finally, we print how many results we collected and across how many pages. This particular pattern, a link telling you where the next page lives, is common, but it's not the only shape pagination takes. Plenty of APIs skip headers entirely and put a field like next page token or next cursor directly inside the response body instead. The mechanics change slightly. You'd check a key inside the response data instead of the past links, but the actual idea driving the loop is identical either way. Keep going as long as the response tells you there's more, and stop the moment it says there isn't. And regardless of which shape you're dealing with, the 2 safeguards here, a hard cap on iterations and a status check before trusting the response, belong in every pagination loop you write, not just this one. Before we write a single line of scraping code in this module, we need to have an honest conversation. Because, can my Python script technically pull this data off this web page, and am I actually allowed to, are 2 completely different questions, and a lot of people only ever ask the first one. This is not legal advice, and I'm not a lawyer. The rules here genuinely vary by site, by jurisdiction, and by exactly what you do with the data afterward. What I can walk you through is the 3 things that consistently matter across nearly every real scraping project. So, you at least know what questions to be asking before you point a script at someone else's website. Start with robots.txt, because it's the most concrete of the 3, and it's something Python can actually check for you automatically. Almost every website publishes a file at its root that lays out, in a simple plain text format, which parts of the site automated bots are and aren't welcome to crawl, and how quickly they're allowed to do it. It's worth being precise about what this file actually is, though. It's not a lock. Nothing on the server technically stops your script from ignoring it entirely. It's a voluntary convention, respected by well-behaved bots like search engine crawlers, and treated as a serious social and often legal signal of the site owner's intent by everyone else. Ignoring it doesn't automatically mean you've broken a law, but it does mean you've deliberately ignored the one place a website operator explicitly told automated visitors what they're comfortable with, and that matters both ethically and, if things ever escalate, as evidence of intent. Look at the sample file for this lecture, and it reads almost like plain English once you know the structure. The user agent line identifies which bot the following rules apply to, with an asterisk meaning everyone, unless a more specific rule exists below. The disallow lines list specific paths that group of bots shouldn't access. Here, anything under the admin or private folders is off limits to general bots. The crawl delay is a suggested number of seconds to wait between requests, which is the site telling you directly how fast it's comfortable being hit. And notice the second block. A specific named bot gets its own separate rule with an empty disallow, meaning that particular bot is allowed everywhere, an exception some sites grant to crawlers they've specifically vetted or partnered with. Python doesn't check any of this automatically just because you're making a request. You have to explicitly ask, which is exactly what the standard library's robot parser module is for. In this code example, we load that exact sample robots file as text, parse it, and then check whether a couple of different URLs are allowed for a generic bot, along with the crawl delay it specifies. And the result matches exactly what a human reading that file by eye would conclude. A products page comes back allowed, the admin dashboard comes back blocked, and the crawl delay comes back as the number 10, ready to be used directly in a wait call rather than something you'd have to read out of the file yourself. In a real script, this check belongs right before you make any request at all, not as an afterthought. If that check comes back false for a URL, the correct response is not requesting it, full stop. Now, robots.txt is only one layer, and it's specifically about crawling behavior. A completely separate layer sits in a website's actual terms of service, which is a legal agreement, not a technical file, and it can restrict things robots.txt says nothing about at all: automated data collection in general, republishing scraped content, using data for commercial purposes, or creating an account specifically to scrape behind a login. Violating a robots file is largely a norms question. Violating a terms of service is potentially a contract question, and the legal exposure there depends heavily on things like whether you agreed to those terms at all, what jurisdiction applies, and what you actually did with the data afterward. Genuinely unsettled territory that's been the subject of real, high-profile court cases with outcomes that have gone different directions depending on the specifics. This is exactly the kind of thing where check the actual terms for the actual site you're working with, and when it matters, talk to someone qualified to give you real legal advice, is the honest answer, not a technical shortcut. The third layer is rate limiting, and this one's less about permission and more about being a considerate, non-disruptive visitor to someone else's server. Every request your script sends costs the target server real computing resources, and a script firing off hundreds of requests a second looks, from the server's point of view, uncomfortably close to the exact pattern used in a denial of service attack, even when that's nowhere close to your actual intent. Beyond the ethical dimension, this has a very practical consequence for you too. Most sites will simply block an IP address, making requests that fast, which means an aggressive scraper often doesn't just risk a legal or ethical problem, it usually just stops working within minutes. In this code example, we loop through a small list of URLs, printing each one as we fetch it, and pause for the crawl delay we read from robots.txt before moving on to the next. And the result is a slow, steady sequence of requests spaced exactly as far apart as the site itself asked for. There's genuinely nothing complicated in this loop. And that's the point. Pausing between each request, set to whatever delay the site itself asked for, is most of what respectful rate limiting actually requires. This is also exactly why scraping a large site properly is slow by design, and treating that slowness as a bug to optimize around rather than a deliberate constraint is a common way people end up getting blocked, or worse, ending up in the kind of grey area we just talked about with the previous two. A few smaller habits are worth folding into this same mindset. Send an honest user agent identifying your script rather than pretending to be a regular browser, since misrepresenting what's making the request undermines the entire good faith argument that you're operating transparently. Cache pages you've already fetched instead of re-requesting the same URL repeatedly while you're still developing and debugging your script. And genuinely check first whether the site offers an official API. A huge number of sites people reach straight for scraping on actually publish a proper API for exactly this kind of programmatic access, and using it sidesteps basically every concern in this entire lecture at once, since it's explicitly sanctioned access, instead of something you're inferring permission for. So here's the actual mental checklist worth running before scraping anything. Check robots.txt programmatically and genuinely respect what it says. Read the site's actual terms of service for anything explicitly restricting automated access, and treat genuine uncertainty there as a reason for real legal advice rather than a technicality to route around. And rate limit deliberately, treating the site you're scraping in the way you'd want your own server treated by someone else's script. Last lecture was all about whether and how carefully to scrape. Now that the ground rules are actually in place, let's build the thing itself. Every scraping task, no matter how complicated it eventually gets, breaks down into exactly 2 steps done one after another. Get the raw HTML of a page onto your machine, and then pick the specific pieces of information out of it. Start with requests, because it's the simpler of the two conceptually. It's just fetching a page, the same thing your browser does the instant you type a URL and hit enter. In this code example, we fetch a page and print out its status code along with the first 200 characters of its raw content. Status code tells you whether the request actually succeeded before you waste any time trying to pass a failed response. 200 means OK. 404 means the page doesn't exist. 403 often means the site is actively blocking you. Checking this before doing anything else is worth building into every scraper you write, because trying to pass an error page as if it were real content is a common source of confusing bugs. The raw text that comes back is the HTML itself as a plain string. At this point, Python has no idea that this string represents a structured document with headings, paragraphs, and links. It's just text, exactly the way requests would return the raw HTML of any page on the internet. One honest note before we go further. The address in that example is a placeholder, standing in for wherever your real target page actually lives, since this lecture obviously can't fetch a live external site as part of a repeatable course example. So for the rest of this lecture, We'll work directly with the sample page delivered alongside this script. Loading it the way you would once requests has already handed you the page's text. Everything from here on runs exactly the same either way. Beautiful Soup has no idea and doesn't care whether the HTML it's given came from a live fetch or a file you opened yourself, since both are just strings of HTML to it. In this code example, we simply open that sample file and read its contents into a string, standing in for what a real fetch would have handed us. That string is where Beautiful Soup takes over, because turning a big blob of text into a structure I can actually query is its entire purpose. In this code example, we hand that HTML string to Beautiful Soup along with the parser it should use and print out the page's title, and the result confirms it worked. The title comes back cleanly, pulled straight out of the head of the document. Handing that HTML string to Beautiful Soup gives you back a soup object that actually understands the page's structure. Tags nested inside other tags, attributes like class and ID, text content sitting inside each element. Printing the title is the simplest possible proof this worked. Now for the part that actually matters in a real scraping task. Pulling out the repeated pieces of content, not just one single value. Our sample page has 3 product cards, each with the same internal structure, and that repetition is exactly the pattern find all is built for. In this code example, we ask the soup object to find every div carrying the product card class, and print out how many it found, and the result is exactly 3, 1 for each product on the page. Find all takes a tag name and, optionally, narrows it down further by attributes like class. It comes back as a list, 1 entry per match, in the same order they appear on the page. This is the single most useful method in the entire library, because almost every scraping task boils down to find every element matching this pattern, rather than find one specific thing. With the cards isolated, pulling the actual fields out of each one just means repeating the same search, scoped to inside each card instead of the whole page. In this code example, we loop through each product card and pull out its name, price and description, printing all 3 together. And the result is a clean line of text for each of the 3 products, showing the name, the price, and the description exactly as they appear on the page. Notice we're finding just one match inside each card rather than every match, because inside a single card there's only ever one product name, one price, one description. Grabbing just the first match is the right tool once you've already narrowed down to a specific card, and pulling the text out of each result strips away all the surrounding HTML tags, giving you back just the plain readable text sitting inside that element. Printing to the console is fine for testing, but the real point of scraping is almost always to get the data into a structure you can actually use afterward. A list of dictionaries, ready to hand straight to pandas the same way we did with tables pulled out of PDFs earlier in this course. In this code example, we build an empty list and loop through the product cards again, this time appending a dictionary of name, price, and description for each one instead of just printing them. And the result is a clean list of dictionaries, 1 per product, genuinely ready to be handed straight to pandas to build a data frame. Exactly the same move we've made with other structured data throughout this course. One more thing worth knowing, since you'll see it constantly in other people's scraping code. Beautiful Soup also supports CSS selector syntax directly, as an alternative to the find methods, for anyone who already thinks in terms of the same selectors used in actual CSS style sheets. In this code example, we use that selector syntax to grab every element carrying the product name class directly and print each one's text, and the result is the same 3 product names as before, retrieved with a different syntax entirely. This selector approach is exactly the same targeting logic as before, just written the way you'd target that same element in a style sheet. Neither approach is more correct than the other. Pick whichever reads more naturally to you, since they're solving the exact same problem with different syntax. So the entire mental model for scraping a static page really comes down to 2 libraries doing 2 separate, well-defined jobs. Request turns a URL into raw text, and Beautiful Soup turns that raw text into something you can actually search and extract from. Everything else in this lecture was just applying find and find all repeatedly to pull out the specific pieces a real page happens to contain. Last lecture, our sample page was clean enough that a simple class name got us everything we needed. Real pages are rarely that cooperative. Class names get auto-generated by build tools and change on every deploy. The exact text you're looking for shows up in more than one place on the page, and sometimes the thing you actually need to select is the parent of the thing you can easily find, not the thing itself. This lecture is about handling all 3 of those situations deliberately, instead of guessing at a selector, running it, and hoping it happened to match the right thing. Start with a trap that's extremely common on modern websites, targeting a class name that isn't actually meant to be stable. In this code example, we load our sample catalog page and select an element using one of those odd, auto-generated looking class names sitting on a product card. and the result is a single match, which technically works right now, today, against this exact page. But a class like that is almost certainly generated automatically by whatever tool built this site's front end, and those generated names frequently change the next time the site gets redeployed, even if nothing about the visible page changed at all. Building a scraper around a class name like this means your script can silently break on a site update that a human visitor would never even notice happened. The fix is picking a more stable target in the first place. Two options tend to hold up far better: a semantic class that's clearly handwritten and tied to meaning, or even better, a data attribute specifically meant for this exact purpose. In this code example, we select elements using a data attribute instead of any class name at all, and the result is all 3 product cards matched cleanly through an attribute that exists specifically so automated tools, whether that's a test suite or a scraper, have something reliable to grab onto that isn't tied to styling at all. Not every site includes them, but when one does, they're almost always a safer bet than any class name sitting next to them, since changing a tested would break the site's own automated tests too, giving the site's own developers a reason not to casually rename it. CSS selectors can do more than plain class matching too, and it's worth knowing the toolkit rather than reaching for a loop every time. In this code example, we select an element by combining 2 class names together with no space between them, targeting the one card that's specifically marked as featured, and the result comes back as exactly that one card, since no space between 2 class names means both classes have to be present on the exact same element. This is how you'd isolate a specifically flagged card from the rest. In this code example, we use an attribute selector to grab every link whose href begins with a specific path, and the result is all 3 course links, filtered purely by that URL pattern. That caret symbol inside the selector means starts with, and the same syntax family includes a way to match ends with and contains anywhere, covering most of the filtering you'd want to do based on a URL pattern rather than a class. There's also a genuinely newer CSS capability worth knowing, because it solves a problem CSS traditionally couldn't handle at all: selecting an element based on what's inside it, rather than what class it carries directly. In this code example, we select a product card specifically by describing a link that exists somewhere inside it, rather than by any marker on the card itself, and the result correctly isolates that one card. This lets you select the outer element by describing something specific about its inner content, without needing the card itself to carry any special marker at all. This is exactly the situation where you know what makes a specific item unique, but that unique detail lives one level deeper than the element you actually want to grab. Now for the situation CSS still can't handle cleanly even with that, and this is exactly where XPath earns its place. Notice our sample page has the word next in 2 completely different places, the actual pagination link and a sentence buried in the footer. CSS has no concept of selecting an element by its exact text content at all. XPath does directly as one of its core features. In this code example, we use XPath to find a link whose text is exactly next, and the result is exactly one match, the pagination link, and nothing else, because requiring the element's text to match that string precisely, not just contain it somewhere, rules out anything that merely mentions the word. Compare that to a looser version of the same idea. In this code example, we switch from exact matching to a contains check for the same word, and the result this time is 2 matches instead of 1, the pagination link, but also the footer paragraph, purely because its sentence happens to start with the word next. This is exactly the kind of bug that passes a quick test and then quietly grabs the wrong element the moment a real page has slightly more text on it than your test page did, which is precisely why exact text matching, not contains, should be your default whenever you actually know the exact text you're targeting. XPath has one more capability worth knowing, because it comes up constantly in real scraping work: navigating upward to a parent element, something CSS selectors fundamentally cannot do at all. In this code example, we find a specific price first, since it's the one unique, easy to locate value, then step up to its parent element using 2 dots, and from there search back down into that same parent to find the course name sitting right next to it. And the result is the correct course name, found entirely by walking from a value we could easily locate to something sitting right next to it. This find the easy thing, then walk to what's actually near it pattern comes up constantly in scraping. And it's something XPath handles natively, while CSS simply has no equivalent for it all. So here's the actual decision to make between the two. CSS selectors, through Beautiful Soup Select, cover the overwhelming majority of real scraping tasks, and they read closer to something a web developer already knows from writing style sheets. Reach for XPath specifically when you need to match on exact text content, or when you need to navigate upward from a child to a parent instead of only ever searching downward. Beautiful Soup itself doesn't speak XPath at all, by the way. That's what LXMs is for. And it's common to use both libraries side by side in the same project, Beautiful Soup for the everyday lookups, and Ling for the specific situations that genuinely need it. And the bigger habit underneath all of this, regardless of which selector language you're using, is picking targets that are actually meant to be stable. Semantic classes and data attributes over auto-generated ones, exact text matches over loose contains checks, and a clear mental model of page's structure over a selector you copied and hoped would keep working. Every technique in this module so far has quietly depended on one assumption, that the data we want is already sitting in the HTML the instant the page loads. Requests fetches that raw HTML, Beautiful Soup and LXM search through it, and neither one has any concept of JavaScript at all. That assumption holds for a huge number of sites. It falls apart completely the moment a page loads its actual content afterward, through JavaScript, which describes an enormous share of the modern web. Let's prove that gap exists first, concretely, before we look at what actually fixes it. In this code example, we load our sample page's raw HTML and search it for product cards the exact same way we have throughout this entire module. And the result is 0. Not because our selector is wrong. It's exactly the same selector that worked fine in earlier lectures, but because the product cards genuinely do not exist yet, at the moment this HTML was captured. All we actually get back is a loading message. The JavaScript on this page hasn't run yet, because nothing in requests or Beautiful Soup ever executes JavaScript at all. They only ever see whatever was already sitting in the document the instant it arrived, and on this particular page, that's just a loading message. This is exactly the gap Playwright closes. Playwright controls an actual browser engine, genuinely the same rendering engines behind Chromium, Firefox and WebKit, programmatically, from Python, letting JavaScript run exactly the way it would for a real visitor, and only then handing you back the fully rendered result. It's the modern successor to older browser automation tools, and it's used for testing real websites just as often as it's used for scraping them, which tells you something about how seriously it treats actually behaving like a real browser. In this code example, we start a Playwright session, launch an actual browser, open a new tab, and navigate it to our sample page, then immediately check what text is showing inside the product list. And the result is still just loading courses, because the navigation step only waits for the page to finish its initial load, not for whatever JavaScript on that page decides to do next. This is worth sitting with for a second, because it's the single most common mistake people make the first time they use a browser automation tool, assuming that once the page has loaded, everything on it is already there. The fix is telling Playwright specifically what to wait for before you try to read anything. In this code example, we wait specifically for a product card element to actually exist on the page, then grab the fully rendered HTML and search it with Beautiful Soup the same way we always have. And the result this time is all 3 product cards, found completely, with the correct names and prices for each one. Waiting for that specific element pauses the script until something matching it genuinely exists on the page, which in this case means waiting exactly as long as it takes the page's own JavaScript to finish injecting the product cards. Once that's done, grabbing the page's content gives you back the complete, fully rendered HTML, not the original static file, but the DOM exactly as it looks after every script has finished running. And notice we're handing that content straight to Beautiful Soup afterward, using the exact same method we have throughout this entire module. That's a genuinely important point. Playwright's job is only getting you a fully rendered page. Once you actually have that HTML, everything you already know about parsing it stays exactly the same. Playwright can do considerably more than just wait and read, since it's controlling a genuine browser rather than simulating one. A capability worth knowing about even in a scraping context is taking an actual screenshot of what the page looks like at any given moment. In this code example, we call a single screenshot method and save the result to a file. And the result is an actual image of the page, exactly as it currently appears in the browser, which is genuinely useful for debugging a scraper that isn't behaving the way you expect. Sometimes the fastest way to figure out why your selector isn't matching anything is to just look at what the page actually rendered rather than guessing from the HTML alone. It's worth being honest about the trade-off here too, because Playwright is a meaningfully heavier tool than requests, and reaching for it by default instead of only when needed is a common mistake. Launching an entire browser process, loading every script and style sheet on the page, and waiting for JavaScript to finish executing is dramatically slower and more resource-intensive than a plain HTTP request, which returns in a fraction of the time and uses a fraction of the memory. The practical rule worth following is this. Always try requests and Beautiful Soup first, the way we did at the very start of this lecture, and only reach for Playwright once you've actually confirmed the data you need genuinely isn't present in the raw HTML. Reaching for Playwright as a default habit means paying that performance cost on every single page, even the enormous number of sites that never needed it in the first place. So the mental model for this entire lecture comes down to one gap and one tool that closes it. Requests and Beautiful Soup only ever see whatever HTML existed the instant the page loaded, with no awareness that JavaScript exists at all. Playwright runs an actual browser, lets that JavaScript execute exactly as it would for a real visitor, and only then hands you back the finished result, at which point every parsing technique from the rest of this module applies exactly the same way it always has.
Have you ever had to fill out the same web form over and over again? Or maybe you needed to check a website every day for a price drop? Or download hundreds of files from a portal, one by one? That's the kind of work that makes you want to flip your desk. But here's the good news. Your computer can do all of that for you, and today I'm going to show you exactly how. We're going to learn Selenium, a Python library that lets you take control of a web browser, just like a robot sitting at your keyboard. It can click buttons, fill in forms, scroll pages, and extract data automatically. Before we write any code, we need two things installed. First, the Selenium library itself. Second, something called a web driver. This is a small program that sits between your Python script and your browser. It's what actually sends commands to the browser. The easiest way to handle this today is with a package called WebDriver Manager. It automatically downloads the right driver for your browser version, so you never have to do that manually. First, we need to import what we need from the Selenium and WebDriver Manager packages. Then start the browser via the WebDriver. Now we are ready to open a website. We can call the get method from the driver and pass the website URL. For example, let's open wikipedia.org. Then let's keep the browser open for 3 seconds so we can see it, then close the driver. Go ahead and run this. Watch a Chrome window pop open, navigate to Wikipedia, and then close itself. It works, right? That's your first automated browser action.
Last lecture, we used a wait for a specific element once to solve one specific problem and moved on. This lecture is about the fact that waiting properly is actually a small decision tree, not one universal fix, and picking the wrong wait strategy is one of the most common reasons a scraper works perfectly in testing and then fails unpredictably once it's actually running against a real site. Let's start with the mistake almost everyone makes first, because it's the most intuitive one. Just waiting a fixed number of milliseconds and hoping that's enough. In this code example, we load our sample bakery order feed, wait a fixed 650 milliseconds, and then count how many order items actually appeared. I ran this exact script 3 separate times against our sample page, and every single run came back with 0 items found, even though the content genuinely does load, every time, within a second and a half at most. The problem is exactly what the sample page was built to expose. Its actual delay is randomized between 600 and 1400 milliseconds, deliberately mimicking the kind of variance a real network request has, and a fixed 650 millisecond wait simply isn't long enough, often enough to be reliable. You could fix this particular test by guessing a longer number, but that's not actually a fix, it's just a slower version of the same fragile guess, and it still has no actual relationship to when the content is genuinely ready. The correct fix is waiting for a condition, not a duration, telling Playwright specifically what state you're waiting for, and letting it check as often as needed until that state is real. In this code example, we load the same page, but instead of waiting a fixed amount of time, we wait specifically for an order item to actually exist, timing exactly how long that takes. I ran this exact version 3 times too, and every single run found all 3 items, regardless of whether the actual delay that run happened to be closer to the fast end or the slow end of the range. Waiting for a specific selector isn't guessing at all. It's genuinely polling the page repeatedly until an element matching that selector actually exists, however long that takes, and only then letting your script continue. That's the entire philosophy shift this lecture is built around. Stop asking, how long should I wait, and start asking, what specific thing am I actually waiting for? Sometimes the thing you're waiting for isn't new content appearing, it's existing content disappearing. A spinner that needs to go away before you trust the page is actually ready. In this code example, we load the page and wait specifically for the loading spinner to become hidden, rather than waiting for the order items themselves to appear. And the result is all 3 items found successfully once that spinner disappears. Same underlying mechanism, just describing a different condition. Instead of waiting for something to exist, we're waiting for something that currently exists to stop being visible. This matters because on a lot of real pages, the loading indicator disappearing and the actual content appearing happen as 2 genuinely separate changes, not one atomic swap. and picking whichever one is actually most reliable to detect on a given page is worth more than always defaulting to the same wait pattern out of habit. There's a wait strategy that sounds like it should solve everything, and it's worth knowing exactly why it doesn't always work, because I hit this directly while testing this lecture. In this code example, we load the page and wait for network activity to go quiet instead of waiting for any specific element, and the result was 0 items found every single time I ran it. Waiting for network activity to settle, wait specifically for actual network requests to quiet down. No in-flight requests for a short stretch of time. Our sample page's content isn't loaded through a real network request at all. It's injected by a plain JavaScript timer, the same way plenty of real single-page apps update their own internal state without necessarily firing a new network call every time. From the browser's perspective, there was never any network activity to wait for in the first place. So that wait considered, the page settled immediately, well before the timer had actually finished and the content existed. This is a genuinely common trap. That strategy is about network requests specifically, not is the page done doing things. And assuming those are the same thing is exactly how a script ends up reading a page before it's actually ready. Waiting isn't only about reading content either. It matters just as much when you're about to interact with something, like clicking a button that only just became available. In this code example, we load the page and immediately click the Load More button, with no explicit wait beforehand at all, then wait for one of the newly loaded orders to appear by its text. And the result is all 5 items present, the original 3 plus 2 more pulled in after the click. Notice there's no explicit wait before that click call, even though the Load More button doesn't exist in a clickable state until after the initial feed items load. That's not an oversight. Playwright's click, along with most of its other interaction methods, automatically waits for an element to actually be visible and ready for interaction before attempting the click at all. This is a genuinely different category from the manual selector-based waits we just covered. Those are for reading a page's state, while this auto-waiting behavior is built into the actions themselves, so you don't need to defensively wrap every single click and fill in its own manual wait call. So here's the actual decision tree worth carrying forward. Never reach for a fixed wait as your default, because it's either too short and unreliable or too long and wastes time on every single run. Wait for the specific element or piece of text you actually need, choosing visible or hidden, depending on which direction the change you care about is moving. Don't assume that network activity settling means the page is fully ready, since it only tracks real network requests, not JavaScript timers or client-side state changes. And trust Playwright's own actions to handle their own waiting when you're clicking or filling something, rather than adding a redundant manual wait around every interaction out of habit. Everything so far in this module has been about reading a page, finding elements, waiting for content, extracting text. Filling out and submitting a form is a different kind of task entirely, because now you're not just observing the page, you're actually changing its state the way a real visitor would, one field at a time, and the order and correctness of those actions genuinely matters. Get a step wrong, or move too fast, and the flow breaks exactly the way it would for a confused human user, except a script won't necessarily notice. Start with the individual field types, because each one needs a slightly different method, and using the wrong one either fails outright or silently does nothing. In this code example, we load our sample bakery order form, select a product from the drop-down, type a quantity into the number field, and click Next, then check which step is actually visible afterward. And the result confirms the transition worked correctly. Step 2 is visible, Step 1 is not. Selecting a drop-down option is specifically for drop-down menus, and it takes the underlying value of the option you want, not the visible text sitting next to it. Filling a field works for ordinary text and number inputs, clearing out whatever was there first and typing in the new value. And clicking Next behaves exactly the way it did in the last lecture, transitioning the page from Step 1 to Step 2, which we can confirm directly by checking which section is actually visible afterward. Step 2 introduces 2 field types we haven't touched yet, radio buttons and checkboxes, plus the actual submission of the form. In this code example, we fill in the customer's name and email, choose delivery instead of pickup, tick the gift wrap checkbox, and click the Place Order button. Then wait for the confirmation section to become visible before reading its text. And the result is a confirmation message that correctly reflects every single choice we made. The right product, the right quantity, delivery instead of pickup, and the gift wrap addition. Checking is the method for both radio buttons and checkboxes, and it's deliberately named for what it does, rather than how you'd do it with a mouse. You're not clicking a checkbox from Playwright's point of view, you're asserting it should be in a checked state. And this method handles that regardless of whether the element underneath happens to be a checkbox or a radio button. Notice we waited for the confirmation section specifically, using the same visible state check from last lecture, since placing the order triggers its own short delay before the confirmation actually appears. Clicking Submit and immediately trying to read the confirmation text without that wait would read an empty string for exactly the same reason a fixed guess-based wait failed us last time. That confirmation message is worth looking at closely, too, because it correctly reflects every single choice we made, which confirms the whole sequence of fills, selections, and checks actually landed correctly, rather than just appearing to. Now, here's a genuine trap worth knowing about before it costs you a debugging session, because it comes directly from testing this exact lecture. This form has real client-side validation on step 1. Clicking Next without selecting a product doesn't silently fail. It pops up a plain JavaScript alert box asking you to pick something first. In this code example, we register a handler for the page's dialog event before doing anything else, then click Next without selecting a product at all. And the result shows the alert's exact message captured in our list, along with confirmation that step 2 never actually became visible, since the validation correctly blocked it. This matters more than it might look like at first. A plain JavaScript alert box genuinely blocks the entire page until it's dismissed, and Playwright, by default, doesn't know what to do with one. If you don't explicitly register a handler for that dialog event before it fires, your script will simply hang, waiting indefinitely for something to close a pop-up it never even acknowledged existed. Registering that handler is what lets you both capture the alert's message for your own logging and accept it programmatically, exactly the way clicking OK would. This is exactly the kind of validation you'll run into constantly on real forms, and the fix is always the same shape. Register the dialog handler before you take the action that might trigger one, not after. Put together, filling out a multi-step form is really just applying the right method to each field type, in the same order a human would naturally move through the page. With weights inserted anywhere, the page needs a moment to react before the next step becomes available. In this last code example, we bring the entire flow together from start to finish. Selecting the product, setting the quantity, clicking through to step 2, filling in the customer details, choosing delivery, checking the gift wrap box, submitting, and waiting for the confirmation before reading it. And the result is the same complete, accurate confirmation message we saw before, produced this time by one continuous script rather than separate pieces. Every line here maps to something a real person would do. In the same order they'd do it: pick a product, set a quantity, move forward, fill in details, choose an option, tick a box, submit, and then wait for confirmation before considering the job done. That last step matters as much as any of the ones before it. A script that fires off every action correctly, but doesn't confirm the final result actually appeared, hasn't really verified anything at all. It's just hoped that everything worked. So the mental model for this entire lecture comes down to matching the method to the field, selecting for drop-downs, filling for text and numbers, checking for both checkboxes and radio buttons, moving through a multi-step flow in the same order a human naturally would, registering a dialog, handler ahead of any action that might trigger a native alert, and always waiting for genuine confirmation that the final step actually completed rather than assuming it did. Last lecture, we filled out and submitted a form. Logging in is a specific case of that same pattern, but it introduces a genuinely new problem the moment it succeeds. Now what? If your script logs in at the start of every single run, you're not just wasting time waiting on a login form every time, you're also hitting the site's login endpoint repeatedly, which is exactly the kind of repeated automated behavior that a site's own bot detection is specifically built to notice. The fix is logging in once, saving whatever the browser was given to prove you're authenticated, and reusing that saved proof on every future run instead of logging in again from scratch. One setup note before we start. Everything in this lecture runs against our sample dashboard page served over a real local address, not opened directly as a file. That's not just a testing preference, it's a requirement, because what we're persisting only gets tracked against a genuine web address, not a plain file on disk. If you want to follow along yourself, open a terminal in the same folder as the sample file and run Python's built-in web server module on it. Then point your script at that local address instead of the file directly. Let's start by actually logging in, the same way we filled out any other form last lecture. In this code example, we open a new browser context, navigate to our dashboard page, check that the dashboard is hidden before logging in, then fill in the username and password, click the login button, and wait for the dashboard to actually appear. And the result confirms the transition worked. Hidden before, visible after. Nothing new here mechanically. Fill the fields, click the button, wait for the result. Exactly the pattern from last lecture. The new piece is the context we created explicitly, rather than letting Playwright default one for us. A context is the actual container holding cookies, local storage, and everything else that makes a browsing session what it is. And having a direct handle on it is what lets us do something with it once we're done logging in. In this code example, we call one method on that context, saving its current state out to a file, and the result is a genuinely readable JSON file containing exactly what our sample dashboard relies on to know you're logged in. The local storage values it checks on every page load. This export captures everything the context is currently holding onto for that site, cookies if the site uses them, and in our case here, those local storage values specifically. This is genuinely just a JSON file sitting on disk once it's saved, readable, inspectable, and completely portable to a future script run. Now for the part that actually saves you the repeated login. Starting a brand new browser context from scratch and handing it that saved file instead of ever touching the login form again. In this code example, we create a new context, but this time pass in the saved state file as we create it, then navigate straight to the dashboard page without touching the login form at all. And the result is the dashboard showing up immediately, with the login form nowhere in sight. This is a genuinely new browser context, with no memory of the previous run at all. And it's showing the dashboard the instant the page loads, never once touching the username field, the password field, or the login button. Passing that saved state directly into the new context restores exactly what the earlier context had saved. And as far as the page itself is concerned, this is indistinguishable from a returning visitor whose browser already remembered them. In practice, you don't want to hardcode always log in or always reuse the saved file. You want the script to check for itself which situation it's actually in, and only log in when there genuinely isn't a saved session yet. In this last code example, we check whether a saved session file already exists on disk. If it does, we reuse it and skip straight to the dashboard. If it doesn't, we run the full login process and save a fresh copy for next time. And the result, the first time this runs with no saved file present, is exactly what you'd expect. No saved session found, logging in fresh, and the dashboard still ending up visible either way. That's the shape a real scraping script should actually take. Check whether a saved session file exists first, reuse it if it does, and only fall back to an actual login when there's genuinely nothing to reuse yet. Run this exact script a second time, now that the file exists on disk, and it takes the other branch entirely, skipping the login form completely. It's worth being honest about the limits of this technique too. Saved sessions eventually expire, the same way they would if you left a real website logged in for months without visiting. Most sites invalidate a session after some period of inactivity, or after a fixed amount of time regardless of activity, for their own security reasons. A script relying on a saved session file should be ready to detect that the saved session no longer works by checking for the logged out state after loading the page, and fall back to logging in fresh and saving a new file when that happens, rather than assuming a saved file is valid forever. So the whole idea in this lecture comes down to treating a login the way it actually deserves to be treated, as an expensive, occasionally necessary action, not something to repeat on every single run. Log in once, save the session the context gives you afterward, reuse that saved state in every future, run through a fresh context, and only log in again when the saved session has actually gone stale. Every scraping example so far in this module has worked on exactly one page at a time. Real catalogs, real search results, real listings almost never fit on a single page. They're split across dozens or hundreds of pages, and a scraper that only handles page 1 is only ever getting a small fraction of the actual data. The good news is that automating pagination isn't really a new skill. It's the same find and click pattern from earlier lectures, just wrapped in a loop that keeps going until there's nowhere left to go. Let's build this one piece at a time, starting with scraping a single page the same way we have throughout this whole module. In this code example, we load the first page of our sample bakery catalog and print out each product's name and price. And the result is exactly the 3 products sitting on that first page. Nothing new here at all. This is exactly the same fetch and pass pattern from earlier lectures. The only thing missing is any awareness that pages 2 and 3 even exist. The piece that actually makes this a pagination scraper is detecting whether a next page exists, and stopping cleanly the moment it doesn't. In this code example, we look for a next page link on the current page and check whether anything was actually found, and the result confirms one exists on this page, along with the URL it points to. That lookup method is specifically built to return nothing instead of raising an error when nothing matches, which makes it the right tool for exactly this situation. You don't know in advance whether a next link exists on any given page, and checking for an empty result is a clean, deliberate way to ask, does this exist at all, without your script crashing the moment it doesn't. Put those 2 pieces together, scrape the page, check for a next link, click it if one exists, and wrap the whole thing in a loop that keeps running until that check comes back empty. In this code example, we bring the whole pagination loop together, scraping the current page, appending every product into a running list, checking for a next link, and either clicking through and looping back around, or breaking out entirely once there isn't one. And the result is all 3 pages scraped in sequence, printing which page it's on each time, and finishing with all 8 products collected across the entire catalogue. That's the entire technique. Scrape the current page's data into a running list, look for a next link, and either click it and loop back around, or break out the moment there isn't one. Notice we wait for the page to finish loading after each click. Clicking a link that navigates to a genuinely new page is a bigger state change than clicking a button that reveals content on the same page, so waiting for the new page to finish loading before scraping it again matters here the same. Waiting mattered for JavaScript-rendered content earlier in this module, and that running list keeps accumulating across every iteration of the loop, rather than getting reset each time, which is exactly what turns 3 separate per-page results into one single combined dataset by the time the loop finishes. 2 things are worth adding to make this genuinely production-ready, rather than just a working demo. First, a safety limit on how many pages you're willing to follow, in case a site's pagination ever misbehaves. A broken next link that points back to itself, for instance, would otherwise send this loop running forever. In this code example, we add a maximum page count as a ceiling on the loop, and once scraping finishes, convert the entire collected list into a proper table using pandas. And the result is a clean data frame with all 8 products, names and prices lined up in columns exactly the way we've built tables from other data sources throughout this course. That maximum page count is a cheap, easy insurance policy. Real pagination almost always terminates correctly, but almost always isn't a guarantee you want to bet an unattended script on, and capping the loop costs nothing when it's never actually needed. And building a data frame out of that flat list of dictionaries is exactly the same move we've made with data pulled from Excel, PDFs, and single-page scrapes throughout this entire course. Once the data is a list of dictionaries, everything downstream works identically no matter where it originally came from. One more thing worth knowing, since it comes up constantly on real sites, not every pagination pattern looks like a next link, taking you to a whole new URL. Plenty of modern sites use a load more button that injects additional content into the same page instead, which is exactly the pattern from a couple of lectures ago when we waited for new content after a click, rather than for an entirely new page to load. The detection logic is nearly identical either way. Look for whatever element represents there's more, click it if it exists, and stop when it doesn't. The only real difference is whether you're waiting for a full page navigation afterward, or waiting for a specific new element to appear on the same page, and that distinction should already feel familiar from the waiting lecture earlier in this module. So the mental model for pagination really comes down to one loop with 2 honest exit conditions. A does more exist, check that returns something real or nothing at all, and a safety ceiling in case that check is ever wrong. Everything else, the actual scraping of each individual page, is every technique this entire module has already covered, just running once per page instead of once total.
In the last lesson, we learned how to open a browser and control it with Selenium. That's powerful, but right now we're just moving around. To actually automate something useful, we need to find things on the page. Buttons, links, input fields. The most common ways to find elements are by ID, by name, by class, and by something called XPath. Don't worry about memorizing all of them right now. We'll start simple. Let's begin with ID. Why? Because IDs are usually unique. That makes them the easiest and most reliable. So again, as we did in the previous lecture, we start by importing Selenium and the WebDriver, then we start the browser and open a website. Then we use find_element function and pass 2 pieces of information. First, how to search, by .yd. Second, what to look for, the actual ID value. If Selenium finds it, great. If not, it throws an error. Now we have learned how to find elements in a web page. In the next lecture, we will use that to click on buttons and handle inputs. See you there. All right, now that we can open and control a browser, let's actually do something useful with it. In real-world automation, we don't just open websites. We interact with them, clicking buttons, filling forms, submitting data. And that's what we will do in this lecture. Let's continue with the previous example. We typed Python automation in the search text box. Now let's simulate hitting the Enter button to start the search. We do this also via the sendKeys function. This time we send keys.enter. And that's how we simulate clicking on elements. In this lesson, you'll learn how to extract data from web pages. Not just view them, but actually pull the information out and use it in your own programs. First, a quick concept. Websites are just structured text written in HTML. You can think of it like a tree of elements, with titles, paragraphs, links, and more. Our job is to navigate that tree and pick out exactly what we need. To do that, we'll use two tools. The first is requests, to fetch the web page, and the second is beautiful soup, to parse and understand it. Let's install and import them. Now, let's build our first scraper. We'll start by downloading a web page. First, we send a GET request to the website. Then we print the raw HTML content. At first glance, it looks messy. But this is exactly what we need. This is the raw structure of the page, and now we need to make sense of it. And that's where beautiful soup comes in. We create a beautiful soup object and pass in the raw HTML, along with a parser, in this case, the HTML parser. Now, when we print the formatted HTML, it looks much cleaner, much easier to read and understand. Now let's extract something useful. For example, the page title. And just like that, you've completed your first real web scrape. You didn't just download a web page, you extracted data from it. All right, let's talk about downloading files automatically with Python. This is one of those skills that feels small at first, but saves you hours later. Imagine this. You visit a website every day, you click a link, you download a file, again and again. That's not work. That's a robot's job. So today we're building that robot. Let's begin by importing the requests library to make a GET request for downloading the file. Then we store the URL of the file we want to download in a variable. We will use a sample PDF file. Then we send a GET request to the URL and store the file content in a variable. Now let's create a file via the open function and set the mode to write binary. Then write the downloaded content to it. That's it. You just automated a download.
Every API we've touched so far in this module has been refreshingly simple to access. A public endpoint, maybe an API key, and you're making requests within minutes. Google Workspace doesn't work that way, and it's worth understanding why before it feels like unnecessary bureaucracy. Gmail, Sheets, Drive, and Calendar all hold genuinely sensitive personal data, and Google's entire access model is built around one core idea. Before any piece of code gets to touch a real inbox or a real spreadsheet, Google needs to know exactly which application is asking, exactly what it's asking permission to do, and in most cases, exactly which human being agreed to let it do that. That's a meaningfully bigger setup cost than a plain API key, but it's also the entire reason Workspace data is as protected as it is. Let's walk through this step by step, because every later lecture in this module assumes it's already done. Step 1 is creating a Google Cloud project. Everything in this setup lives inside a project, really just a named container that holds your enabled APIs, your credentials, and your usage together in one place. Go directly to the project creation page on Google Cloud's console, signed into whichever Google account you actually want to automate. You'll land on a simple form asking for a project name and, if your account belongs to an organization, a location for it. Give it a genuine, specific name, something like Personal Automation Project, rather than the random default name Google suggests. Because you'll be looking at this name again later, and a meaningful one saves you from second-guessing which project is which if you ever end up with more than one. Click Create, and Google Cloud takes you to that project's dashboard within a few seconds. One thing worth checking immediately afterward, the project selector sits in the top navigation bar of every single page in the console, and it's genuinely easy to end up performing the next several steps against the wrong project if you don't glance at it first. Get in the habit of checking that drop-down before every major step in this setup. Step 2 is enabling the specific APIs you actually need. With your project created and selected, head to the API library section of the console. This part surprises people the first time because it's not one single Google Workspace API. You flip on once. Gmail, Sheets, Drive, and Calendar are each separate APIs, and each one has to be individually enabled inside your project before your code can touch it, even though they're all part of the same broader product family. Use the search bar on that library page to find each API by name. For example, search for the Gmail API, click into the result, and click the blue Enable button. Then go back to the library and repeat the exact same search click enable sequence for Sheets, Drive, or whichever other Workspace API a later lecture in this module actually needs. If a future lecture throws an error saying an API hasn't been enabled for your project, this is almost always the actual cause, and the fix is coming back to that same library page and enabling the specific API that lecture depends on. Step 3 is configuring the OAuth consent screen. This is the part that trips people up most, so it's worth slowing down here. This screen is what a real user sees when your application asks to access their Google account. The actual permission prompt showing your app's name and exactly what it wants access to. From the left-hand menu inside APIs and Services, click into the OAuth consent screen section. Google will redirect you into what it now calls the Auth Platform Overview page, and from there you'll click Get Started. You'll be asked for an app name, which shows up on that consent screen itself, and a support email, which is just an address Google can use to reach you about your own app. The single most important decision on this screen is the audience setting, and it's worth understanding exactly what each option actually means before picking one. Internal restricts your app to users inside your own Google Workspace organization specifically. This only applies if you're on a paid Workspace account tied to a company domain, not a personal Gmail account, and it skips a lot of the verification overhead since Google already trusts everyone inside that organization. External means any Google account at all can potentially use your app, which is what you'll pick if you're working with a personal Gmail account, the way most automation scripts for personal use actually do. Picking external doesn't mean the whole public internet suddenly has access to your script, though. While your app sits in what Google calls testing status, only specific email addresses you explicitly add as test users are actually allowed to authenticate against it at all, which is exactly the right setting for a personal automation script that only you, or a small handful of people, will ever actually run. After the consent screen is configured, look for a test users section within that same setup flow and add yourself as a test user, using the exact Google account whose Gmail, Sheets, or Drive data your scripts are actually going to touch. Skip this step and your own script will fail to authenticate against your own account, which is a confusing error to hit the first time since it looks like a bug rather than a missing entry in a list. Step 4 is creating the right kind of credentials. Now for credentials themselves. And this is where a genuine fork in the road shows up. 2 different credential types exist for 2 genuinely different situations, and picking the wrong one is a common source of confusion later. Head to the credential section of the console and check that project drop-down one more time before continuing. An OAuth client ID is what you need when your script is going to act on behalf of a specific human's account. Reading your own Gmail inbox, writing to a spreadsheet in your own Drive, the kind of thing where a real person needs to explicitly grant permission the first time the script runs, through an actual browser-based consent screen. This is almost certainly the one you want for personal automation. Click Create Credentials, choose OAuth Client ID, select Desktop App as the application type for a script running on your own machine, give it a name, and create it. A service account, by contrast, is meant for genuinely unattended, server-to-server access, with no specific human logging in at all. Think of it as a robot identity with its own email address. Useful for something like an automation that manages files in a shared Drive folder without ever being tied to one particular person's login. It's worth knowing this option exists specifically because it's the wrong choice for most personal automation. If you find yourself trying to force a service account into a workflow that's really about your own personal inbox or your own personal spreadsheets, an OAuth client ID is almost certainly what you actually needed instead. It's also worth knowing that some Google accounts, especially ones inside a managed workspace organization, have service account key creation restricted by an administrator's policy entirely. So this path isn't always even available depending on whose account you're working with. Step 5 is downloading and protecting the credentials file. Whichever credential type you create, the last step is downloading it as a JSON file, and this file deserves real respect. It genuinely contains either a client secret or a private key, depending on which type you created, and either one is functionally equivalent to a password for whatever access it grants. Save it somewhere outside any folder you'd ever commit to version control. And if you're using something like Git for these scripts, add its file name to your ignore file immediately, before you forget, and it ends up committed somewhere it shouldn't be. So here's the actual checklist this entire lecture boils down to. Create a project and give it a name you'll actually recognize later. Enable each specific Workspace API you intend to use individually, since there's no single switch that turns them all on together. Configure the OAuth consent screen, choosing external for a personal account and explicitly adding yourself as a test user. And create the right credential type, an OAuth client ID for anything acting on behalf of your own personal account, a service account only for genuine, unattended server-to-server access, then download and protect that credentials file the way you would any other secret. Every remaining lecture in this module assumes this setup already exists. Next, we're going to actually use that downloaded credentials file from Python for the first time, walking through the OAuth flow that turns it into a real, working connection to your own Google account. Turning a downloaded credentials file into an actual, working connection from Python, and then reading and writing real data in a real spreadsheet, is what this lecture is all about. 3 libraries do the work here. One handles the login flow itself, one manages the resulting credentials afterward, and one actually talks to the Sheets API once you're authenticated. Let's start with authentication, because nothing else in this lecture works until this succeeds. In this code example, we read in the credentials file downloaded last lecture and define the specific scope we're requesting, full read and write access to Sheets specifically. Not Gmail, not Drive, not anything else, which ties directly back to the consent screen concept from last lecture. If you only ever needed to read data, you'd use a narrower read-only scope instead. And it's worth requesting the narrowest scope your script actually needs, rather than defaulting to the broadest one out of convenience. Running the local server step is where the actual human part happens. It spins up a temporary local web server on your machine, opens your real default browser, and shows you the real Google consent screen you configured last lecture, asking you to log in and approve exactly the access those scopes. This describe. Once you click Allow, Google redirects back to that local server with an authorization code, and the library exchanges it behind the scenes for the actual credentials your script needs. Doing that entire browser dance every single time you run a 2-line script would be exhausting. And this is exactly the same problem we solved with saved browser sessions back in the web scraping module, just applied to a different kind of credential entirely. In this code example, we take those credentials and serialize them out to a token file on disk, and the result is a genuine, reusable file containing everything needed to reuse this session, including a refresh token, which is what actually makes this durable rather than a one-time convenience. Saving this to a file means future runs can skip the browser entirely, the same underlying idea as the saved session file from the persistence lecture, just Google's own version of it. In this code example, we bring the whole authentication pattern together into the shape almost every real script using this library ends up with. Check for a saved token first. If one exists and it's still valid, skip authentication entirely. If it's expired but there's a refresh token attached, quietly refresh it without bothering a human at all. Only fall back to the full browser-based flow when there's truly no usable saved session. Exactly the same 3-way branch we built for browser sessions earlier in this course, just with Google's own credential objects instead of a JSON storage file. With credentials actually in hand, connecting to Sheets itself is a single line. In this code example, we build a connection to the Sheets service specifically. That single call is a general-purpose entry point shared across every Google API this library supports. The same call works for Drive, Calendar, or Gmail just by swapping which service you actually want, and which version of that particular API you're targeting. Everything else in this lecture happens through this one connection object. Reading data needs 2 things to actually locate what you're asking for: the spreadsheet's ID and a range describing exactly which cells you want. In this code example, we specify a spreadsheet ID and a range, then call get on the spreadsheet's values, finishing with the execute call that actually sends the request. And the result is a dictionary containing the actual cell data. The spreadsheet ID isn't something you type in by hand from memory. It's the long string of letters and numbers sitting in the URL itself, right between the D and the edit portions when you have the sheet open in a browser. The range uses the exact same A1 notation you already know from writing formulas by hand in the sheet itself. That final execute call is what actually sends the request. Everything before it is just building up the request's shape, and nothing actually happens over the network until execute runs. What comes back is a dictionary, and the actual cell data lives specifically under its values key. As a list of lists, each inner list is one row, and each item inside that row is one cell's value. Getting that with a default of an empty list, rather than assuming the key always exists, matters more than it looks like. A completely empty range in the sheet comes back with no values key at all, and reaching for a key that isn't there would throw an error instead of just giving you back nothing, to loop over. That list of lists shape is exactly the same structure we've built pandas data frames from throughout this entire course. In this code example, we split the first row off as a header and turn everything after it into a data frame using that header as column names. Treating the first row as a header and everything after it as data is a genuinely common pattern, since most real spreadsheets have exactly that shape, and from there it's the same data frame call we've used on data from Excel files, scraped web pages, and everywhere else in this course. Writing data back follows a similar shape to reading, just with an update call instead of get, and an actual payload to send along with the request. In this code example, we build a small table of new data and call update on the spreadsheet's values, specifying the range to write into and a value input option, finishing with execute the same way as before. The payload carries the actual data you're writing, in that same list of lists shape, wrapped inside a dictionary under a values key, mirroring exactly what you got back when reading. That value input option is worth understanding specifically, because the two choices genuinely behave differently. One option tells Sheets to treat the data the way it would if you'd actually typed it into a cell yourself, meaning a string that looks like a formula gets calculated and a date-shaped string gets recognized as an actual date. The other option instead stores everything exactly as literal text, with no interpretation at all, which matters if you're deliberately writing something that looks like a formula, but is genuinely meant to just sit there as plain text. If you specifically want to add rows onto the end of existing data rather than overwrite a known range, there's a method built for exactly that. In this code example, we call append instead of update, pointing at just a single starting cell rather than a full range. Notice the range here is just a single starting cell, not a full range. Append figures out where the actual existing data currently ends and adds the new row immediately after it, which is exactly the behavior you want for something like logging a new entry, without needing to first check how many rows already exist. So the whole shape of working with Sheets from Python comes down to a handful of pieces fitting together. Authenticate once, using the save token pattern so you're not repeating a browser login on every run. Build a single connection object, shared across every call you make. Locate data with a spreadsheet ID and an A1 notation range, and choose the right method for the job. Get for reading, update for overwriting a known range, append for adding on to the end, always finishing with execute, since nothing actually happens until that call runs. Reading and writing values only ever touches what's actually inside a cell, the text, the number, the formula. It has no concept of bold text, background color, column width, or frozen rows at all. Asking a plain value update to make a header bold simply has no mechanism for that request, because formatting a sheet and writing data into it are handled by two genuinely separate parts of the same API. This lecture is about the part that handles appearance. That part is called batch update, and it works differently enough from plain value reads and writes that it's worth understanding the shape before writing any of it. One quick production note before we dive in. Every code example in this lecture is a complete standalone script, which means the same authentication setup you'll recognize from earlier lectures repeats at the top of each one. That's deliberate. It means you can copy any single example straight into its own file and run it immediately, without needing to piece together imports or setup from several different places. Once you've seen it the first time, feel free to skim past it in the examples that follow. In this code example, we authenticate, build a connection to the Sheet service, and then send a formatting request that bolds and shades the very first row of the sheet. And the result, once it runs, is a header row that's genuinely bold with a light grey background, confirmed by a simple printed message once the call completes. A few things here look nothing like plain value reads and writes, and each one is worth slowing down on. The range here isn't A1 notation at all. It's described with plain row and column indices instead, and those indices are zero-based and end-exclusive, meaning a start index of 0 and an end index of 1 describes exactly one row, the very first one, not two. This trips people up, constantly coming from A1 notation where row 1 means row 1, not row 0. Color is expressed as red, green, and blue values between 0 and 1 rather than the 0 to 255 scale you'd see almost everywhere else. So a light grey sits close to the top of that range on all three channels rather than close to 0. The fields entry is the one piece with no equivalent at all in a plain value write, and skipping it is the single most common reason a formatting request silently does nothing. It's a field mask, explicitly telling the API which specific properties inside your cell object you actually want applied. Google Sheets won't assume you meant everything you included just because you included it. You have to explicitly list out which properties you're touching. Or the request executes successfully and changes nothing at all, which is a genuinely confusing failure mode the first time you hit it, since there's no error telling you what went wrong. Notice something else too. The sheet ID used inside that range is not the same thing as the overall spreadsheet ID. A spreadsheet can contain multiple sheets or tabs, and a sheet ID identifies one specific tab inside it. as a small internal integer, completely separate from the long string identifying the whole file. 0 happens to be the sheet ID of the very first tab in any spreadsheet, which is why it works without an extra lookup. But if you're working with a tab other than the first one, here's how to look it up directly. In this code example, we authenticate the same way as before, then request the spreadsheet's metadata and loop through every tab it contains, printing each one's title next to its internal sheet ID. And the result is a clean list showing you exactly which ID belongs to which visible tab name. That metadata call returns a description of the whole spreadsheet structure, including every tab it contains, and this is exactly how you'd find the specific one you actually meant on a spreadsheet with more than one tab. Match on the title you can see in the browser, and use the ID sitting right next to it in every request from here on. Freezing a header row, the same concept we covered back in the Excel automation module, exists here too, just through this same batch update mechanism instead of a single property assignment. In this code example, we authenticate again, then send a request that sets the frozen row count on the sheet's properties to 1. And the result is a header row that now stays locked in place while scrolling, confirmed once the call finishes. Same pattern as before, a request describing what to change, and a fields mask specifying exactly which property inside it actually applies. Now let's bring formatting together with appending, because there's a genuinely useful technique here worth knowing, and it depends on paying attention to what append actually hands back rather than treating it as fire and forget. In this last code example, we authenticate once more, append a new row of data, then read back exactly where that data landed, convert that location into the row index format batch update expects, and send a follow-up request that highlights precisely that row. And the result is a newly appended row that ends up visually flagged in a soft green, entirely automatically, regardless of how many rows existed before it ran. Append doesn't just silently succeed, its response tells you exactly where the new data actually landed, using ordinary A1 notation. This matters because you genuinely don't know in advance which row a new entry will end up on, since that depends entirely on however much data already existed before this call ran. Passing that returned location is how you'd figure out precisely which row to format next, rather than guessing or hard-coding a row number that'll be wrong the next time this script runs against a sheet with different existing content. That's the whole trick. Pull the row number out of the location append handed back, convert it from A1's 1-based counting to the 0-based indices the formatting request expects, and use that to highlight exactly the row that just got added, automatically. This is a genuinely practical pattern for something like a live log or a running list of new entries, where every newly appended row gets visually flagged the moment it's added, without ever needing to know in advance how many rows already existed. So the mental model for this entire lecture comes down to recognizing that formatting lives in a different part of the API than data does, and accepting its more verbose shape as the cost of it. Batch update takes a list of requests, each one a dictionary describing a specific change. Ranges inside those requests use 0-based end-exclusive row and column indices, not A1 notation. Every request needs an explicit fields mask, naming exactly what should actually apply, or nothing happens at all. And append's own response tells you precisely where your data landed, which is exactly the information you need to format the row you just added, rather than guessing. Sheets and docs live inside Drive, but Drive itself is really just a file system in the cloud, and the API reflects that directly. Almost everything you'll do revolves around one single resource type called a file, whether that file happens to be a PDF, a photo, a folder, or even a Google Sheet. 4 operations cover the overwhelming majority of what you'd ever want to automate here: uploading something new, downloading something that already exists, listing or searching for files, and moving files between folders. Let's build all 4. One quick production note before we start. Every example in this lecture is a complete standalone script, so the same authentication setup from earlier lectures repeats at the top of each one. That's intentional, so you can copy any single example into its own file and run it immediately without hunting down imports from somewhere else. Feel free to skim past that opening block once you've seen it the first time. Start with uploading, since it's the most immediately useful and the one you'll reach for constantly. In this code example, we authenticate, build a connection to the Drive service, describe a file's name as metadata, point at a real PDF sitting on disk as the actual content to upload, and hand both to a single create call. And the result is a brand new file living in Drive, with its ID printed back to confirm it worked. 2 objects are doing distinct jobs here, and it's worth telling them apart. The metadata dictionary is plain descriptive information, the name this file should have inside Drive, and optionally which folder it belongs in. The upload object is the actual content itself, pointed at a real file sitting on your local disk, along with its type so Drive knows what kind of file it's actually receiving. Both get handed to the same create call together, and the response coming back is deliberately sparse. We ask specifically for just the ID field, since that's usually the only thing a script needs afterward to keep working with the file it just created. Downloading works in the opposite direction, and it looks a little different from a plain file read, because drive downloads happen in chunks rather than all at once. In this code example, we authenticate again, request a specific file's media content, create an in-memory buffer to hold it, and then loop, pulling down one chunk at a time and printing the progress until the whole file has arrived. Once that's done, we write the buffer's contents out to an actual file on disk, and the result is a real downloaded file sitting locally, matching exactly what was stored in Drive. Requesting the media content builds the download request, but notice it doesn't return the file's content directly. The chunk downloader is what actually pulls that content down, piece by piece, writing each chunk into that in-memory buffer, which is exactly why large files download reliably, instead of needing to fit entirely into memory in one single transfer. The loop keeps pulling chunks until it's genuinely finished, at which point the buffer holds the complete file, ready to be written out. One exception worth knowing about: this exact pattern only works for ordinary files, things like PDFs, images, and so on. A native Google Doc, sheet, or slide deck doesn't have raw file bytes sitting on Drive servers at all. It exists purely as Google's own internal format, and pulling it out as an actual file requires a different method entirely, one that converts it into a real format like PDF or Excel on the way out, rather than the plain media request, which only works for files that already have real bytes to hand over as is. Before you can move or download a specific file, you usually need to find it first, and that's what listing files is for. In this code example, we authenticate once more and call list with a search query looking for files whose name contains a specific word, explicitly excluding anything sitting in the trash, then print each match's name, ID, and type, and the result is a clean list of exactly the files matching that description. That query argument is a small query language of its own, purpose-built for searching Drive specifically. Matching part of a file name is one condition, and excluding trashed files is worth including deliberately, since Drive search will otherwise happily hand back files sitting in the trash, alongside everything else, which is rarely what you actually want. You can combine several conditions together the same way this example does, filtering by file type, by parent folder, by modification date, and more, all directly on Google servers rather than pulling down every file and filtering them yourself afterward. Now for organizing, moving a file from one folder into another. And this is the part that behaves a little differently than you might expect coming from a normal file system. In this code example, we authenticate, first ask the file for its current parent folder, join that into a string, and then call update, adding the new destination folder as a parent while removing the previous one in that same call. And the result is a file that's now sitting in a completely different folder, confirmed by printing its updated parent list. There's no dedicated move method at all in this API, and that surprises people the first time. Drive doesn't think of a file as living in one folder that you simply reassign. It thinks in terms of parent relationships, and moving a file actually means adding a new parent and removing the old one in the very same request. That's why this script first asks the file for its current parents before doing anything else, then hands both the new parent and the old one to update together. Skip fetching the existing parent first, and you genuinely won't know what to remove, potentially leaving the file sitting in two folders at once, instead of moved cleanly from one to the other. Creating a folder in the first place uses the exact same create call as uploading a file, which makes sense once you know that a folder in Drive's model is really just a file with a specific type and nothing else. In this last code example, we authenticate, describe a folder by name and a special folder type instead of a regular file type, and call create with just that metadata, no actual content attached at all. And the result is a brand new folder in Drive, with its own ID printed back the same way a regular file upload would return one. That single type value is the entire distinction between a file and a folder as far as this API is concerned. Swap it out, and the create call builds a folder instead of an ordinary file, and that returned ID is exactly what you'd pass in as a parent the next time you upload something and want it to land inside this new folder directly, or as the destination the next time you move an existing file the way we just did a moment ago. So the whole shape of automating Drive comes down to 4 calls fitting together around one shared idea. Everything is a file, including folders themselves. Upload with create, handing it both metadata and actual content. Download with the chunked media request, working piece by piece rather than all at once, and reaching for the export version instead whenever the target is a native Google Doc, sheet, or slide deck rather than an ordinary file. Search with list and its own dedicated query syntax rather than pulling everything down to filter locally. And organize with update, remembering that moving a file always means adding one parent and removing another in the same call, since there's no single move operation waiting to be found. Email automation already got a full module of its own earlier in this course, built entirely on SMTP and IMAP, the raw protocols underneath essentially every mail provider on Earth. Gmail has its own API too, and it's worth being clear about why that's not redundant. The Gmail API authenticates through the exact same OAuth flow as Sheets and Drive, rather than an app password over a raw socket connection, and it models your inbox as REST resources. Messages, threads, labels, the same shape as everything else in this module, instead of a sequence of plain text, protocol commands. If you're already deep into Workspace automation and want Gmail to fit the same authentication and calling pattern as Sheets and Drive, this is genuinely the more consistent choice. If you just need to send a simple notification from a script with no other Workspace involvement, plain SMTP is often still the simpler path. This lecture isn't replacing that module. It's giving you the alternative that fits naturally alongside everything else we've built in this one. There's one specific quirk to the Gmail API worth understanding before writing any code. Every message you send or receive through it is wrapped in a base 64 URL encoded string, sitting inside a field literally called raw. That single detail shapes almost everything in this lecture. One production note before we go further, the same one from earlier lectures in this module. Every example here is a complete standalone script with its own authentication setup at the top, so you can copy any single one into its own file and run it immediately. In this code example, we authenticate with a scope specifically for sending mail, build a plain text message the same way we would for an ordinary SMTP send, then encode it and hand it to the Gmail API's send method. And the result is a real sent message, with its ID printed back to confirm it went through. Look closely at where that plain text message class shows up. It's the exact same class from Python's own email library that we used to build messages for plain SMTP, back in the email automation module. Building the actual message content hasn't changed at all. What's different is what happens to it afterward. Instead of handing that message straight to an SMTP connection, it gets converted to bytes, base 64 URL encoded, and decoded back into a plain string, which is precisely the string the API expects inside its raw field. That encoding step deserves a moment of attention, because it's a common source of a confusing crash the first time you write this from scratch. The encoding function itself returns bytes, not a string, so calling decode afterward is what turns it into the plain text the API's JSON body actually needs. Skip that final decode and you'll get a completely different, much less obvious type error the moment this request tries to serialize. And the user ID is always the literal string me here, when you're authenticated as a normal user acting on your own inbox, rather than an actual email address. Gmail resolves that automatically to whichever account the credentials belong to. Reading mail runs the same encoding idea in reverse, and it starts with search, since you almost never want to read your entire mailbox at once. In this code example, we authenticate with a read-only scope this time, and call list with a search query looking for unread messages from a specific sender, capped at 10 results. And the result is a list of matching message IDs, along with a count of how many were found. That search query is genuinely the exact same syntax you already know from typing into Gmail's own search bar: sender, unread status, attachment presence. And everything else you'd normally type by hand works identically here. And just like Drive's list call from last lecture, this only returns IDs, not the actual messages. A deliberately lightweight response, since fetching every full message just to check whether you wanted it would be wasteful, the moment your inbox has any real volume in it. Before we go further, here's a genuinely common snag worth knowing about in advance, because it comes up constantly with exactly this two-script pattern. If you run the sending script first, it saves a token file scoped only for sending. Then if you run the search script next, expecting a read-only scope, that saved token file already exists, so the script reuses it without checking whether it actually covers reading mail at all. And Gmail responds with a permission error, insufficient authentication scopes, because the token you're presenting genuinely never granted read access in the first place. The fix is either deleting that saved token file so a fresh login can request the right permissions, or better, requesting every scope you'll actually need across all your Gmail scripts together, upfront, in one combined list, so one saved token file covers sending and reading, both from the very first login. Turning one of those IDs into the actual readable content of a message is where the base 64 decoding from earlier comes back, and it's a bit more involved than encoding was, because a real message often isn't just one plain block of text. One more practical snag worth flagging before that final example, since it trips people up constantly the first time they try this. The message ID this next call needs has to come from that list call we just made, or another API response like it, not from the ID sitting in your browser's address bar when you have a message open in Gmail's own website. Those are two completely different identifiers. The one in the browser is something Gmail's web interface uses purely for its own internal routing, and handing it to the API instead of a genuine API-issued ID triggers a plain, unhelpful, invalid ID value error. Always grab your message ID from a list call's own output, never from a URL. In this last code example, we authenticate again with the read-only scope, fetch one specific message in full, and then walk through its structure recursively looking for a plain text part, decoding it the moment we find one. And the result is the message's actual readable body, printed out as plain text. The reason this needs a small recursive function, rather than one direct lookup, is that a message's payload isn't guaranteed to be flat. A simple plain text email has its content sitting directly in the payload's own body. But the moment a message has both a plain text and an HTML version, or an attachment alongside the text, Gmail nests those as separate entries inside a parts list instead, and any of those parts can themselves contain further nested parts. Walking through parts recursively, checking each one's type, and stopping the moment we find a genuine plain text block is the same fundamental idea as walking a parsed email message with Python's own email library back in the email automation module, just applied to Gmail's own structure instead of the standard library's message objects. And notice the decoding direction here is the mirror image of sending. Decoding instead of encoding, followed by turning those raw bytes into an actual readable string. So the entire shape of this lecture comes down to one recurring idea, applied in both directions. Content moving into Gmail gets built as an ordinary MIME message, exactly the way it always has, then base64 RL encoded into the raw field the API expects. Content coming back out gets base64 URL decoded out of wherever it's actually sitting inside a message's payload, which might be a direct, flat lookup, or might require stepping through nested parts to actually find it. Searching uses the exact same query syntax as Gmail's own search bar, and the user ID stays me throughout, whenever you're operating on your own authenticated inbox rather than someone else's. Calendar follows the exact same shape as Sheets, Drive, and Gmail before it. Authenticate with OAuth, build a service object, and call methods on a specific resource, which here is called an event. What makes Calendar worth its own lecture isn't the mechanics of the API itself, which are familiar by now, but a handful of details specific to describing time correctly. Since getting a date or a time zone subtly wrong is exactly the kind of mistake that doesn't throw an error, it just quietly puts something on the wrong day for someone. In this code example, we authenticate, build a connection to the calendar service, describe an event with a summary, a description, and a start and end time, then insert it onto the primary calendar. And the result is a newly created event, confirmed by a real clickable link printed back from the response. The calendar ID is almost always the literal word primary for a script acting on your own calendar, the same way the user ID was always me for Gmail. The response includes an actual link straight to the event inside Calendar's own web interface, which is a genuinely convenient way to verify a script actually did what you expected without having to open Calendar and search for it manually. The time zone field deserves real attention because it's the single most common source of a subtly wrong event. Notice the time zone in that example is a name zone like America, New York, not a fixed offset like -5 hours. That's a deliberate choice, and it's worth understanding why the API pushes you toward it. A fixed offset has no idea daylight saving time exists. A recurring event set with a fixed offset will start drifting an hour off from where it should be the moment clocks shift twice a year. A named time zone carries that entire rule set internally, so a 10 a.m. meeting stays at 10 a.m. local time regardless of which side of a daylight saving boundary the actual date falls on. This matters even more once recurrence enters the picture, which we'll get to shortly. Not every event has a specific time at all. An all-day event, like a holiday or a deadline, uses a completely different field to describe when it happens. In this code example, we authenticate again and create an event using a plain date instead of a specific time, for both the start and the end. And the result is an all-day event, correctly showing on just the one day it's meant to represent. A plain date replaces a specific date and time entirely here, with no time zone attached at all, since an all-day event isn't pinned to any specific hour to begin with. Notice the end date used is the day after the event actually occurs. Calendar's all-day events treat the end date as exclusive, the same end-exclusive convention we ran into with grid ranges back in the Sheets formatting lecture. So a single-day event genuinely needs an end date one day later than the day it's actually on, not the same day repeated. Inviting other people is where a real gotcha lives, and it's worth knowing about before you accidentally either spam a group of attendees or silently fail to invite anyone at all. In this code example, we authenticate once more, build an event with a list of attendee email addresses and a set of custom reminders, and insert it while explicitly requesting that update notifications go out to everyone involved. And the result is an event created with real invitations actually sent to both listed attendees. Attendees is a plain list, each one needing at minimum an email address. The genuinely easy mistake to make sits outside that list entirely, in the send update setting passed alongside the request itself. According to Google's own documentation, invitations are not sent to attendees unless you explicitly request it. Leave that setting out, and the event gets created with those people listed as attendees, but they never actually receive an invitation email telling them it exists. Setting it to send to everyone is what actually triggers real invitation emails going out to the whole list. There's also an option for notifying only attendees outside your own organization, and an option for creating the event without notifying anyone at all, which is exactly what you'd want while testing a script, before you're ready for real people to start receiving real invitations from it. Reminders work the same way calendar reminders always have, just expressed as data. Turning off the calendar's own default reminders means ignore whatever the calendar's default settings are, and a list of overrides describes exactly which reminders you actually want instead, each one specifying a method and how many minutes beforehand it should fire. Recurring events reuse this exact same event structure, adding just one new field that describes the repetition pattern using a real external standard rather than anything Google invented specifically for calendar. In this code example, we authenticate again and create an event the same way as before, but this time add a recurrence rule specifying that it repeats weekly, capped at 10 total occurrences. And the result is a single event that actually represents 10 separate weekly meetings, all created from one single request. That recurrence string follows a real recurrence rule syntax used across calendar software generally, not something specific to Google's own API. Specifying weekly frequency means it repeats every week, and capping the count at 10 limits it to 10 total occurrences. You could swap that for a specific end date instead, to repeat until a cutoff rather than a fixed number of times. This is exactly where a named time zone earns its keep. A weekly 9 a.m. stand-up needs to stay at 9 a.m. local time for all 10 weeks, even if a daylight saving shift happens to fall somewhere in the middle of that run. Reading events back requires one specific flag most people miss the first time, because without it, a recurring event doesn't behave the way you'd expect at all. In this last code example, we authenticate, then list upcoming events starting from right now, asking for individual events to be expanded and sorted by their start time, and the result is a clean, chronological list of upcoming events, each one printed with its actual date or time next to its title. Expanding individual events is the one easy to overlook here, and skipping it changes the results in a way that's genuinely confusing to debug. Without it, the list returns a recurring event as a single master record describing the whole repeating series, not each individual occurrence, meaning a weekly stand-up would show up exactly once in the results, not 10 times, regardless of how many actual instances exist on the calendar. Turning that expansion on is what breaks that single recurring definition out into every actual individual occurrence, which is almost always what you actually want when you're trying to see what's really on the calendar. Sorting by start time is only even available once that expansion is turned on in the first place, since a series without expansion has no single meaningful start time to sort by. And notice the way we check each event start in that final loop handles both event types in one line. A specific time for a timed event, falling back to a plain date for an all-day one, since a single event will only ever have one of those two fields present, never both. So the mental model for calendar comes down to a small set of details layered on top of the same request and response pattern from every other Workspace API in this module. Use a specific date and time with a named time zone for timed events, and a plain date alone for all-day ones, remembering that all-day end dates are exclusive. Explicitly request that updates go out whenever attendees are involved, since invitations don't go out silently on their own. Describe recurrence with a real recurrence rule string, not a custom Google format. And always turn on event expansion when listing, or a recurring series will show up as one confusing record instead of the actual individual occurrences sitting on the calendar. Think back over everything this course has covered so far: reading formulas out of Excel, extracting tables from PDFs, parsing emails, scraping HTML, calling REST APIs, automating Sheets and Gmail. Every single one of those techniques rests on the same hidden requirement. The task can be described completely, in advance, as an explicit set of rules. If the cell contains a number, do this. If the response status is 404, do that. If the HTML has a class called product card, extract it. That style of automation is genuinely powerful, and it's also completely deterministic. Given the same input, it does the same thing, every time, forever. That reliability is exactly why it's trustworthy enough to run unattended. But it only works at all because someone was able to write the rule down in the first place. And there's an entire category of real tasks where that turns out to be much harder than it sounds. Picture something concrete. A small business gets emails from customers all day, some asking about an order status, some complaining, some just saying thanks, some asking a completely unrelated question about hours or location. Automating, read this email and figure out what it's actually about. The traditional way means writing rules. If the subject contains the word refund, treat it as a complaint. If it contains where is, treat it as an order status question. That works for exactly the phrasings you thought to write a rule for. The moment a real customer writes, "This still hasn't shown up and I'm getting worried," none of those keyword rules fire at all. Because there's no single word doing the work, the meaning lives in the whole sentence, expressed in one of a functionally unlimited number of ways a person might actually phrase it. You can keep bolting on more keywords forever, and you will never actually catch up, because the space of things people might say is not something you can exhaustively list, no matter how much time you spend trying. This is precisely the gap a large language model fills, and it's worth understanding in plain terms what's actually different about it, without needing a machine learning background to get the idea. A traditional rule matches specific patterns you wrote down ahead of time, specific words, specific structures, specific conditions. A language model instead has been trained on an enormous volume of real human writing, and what it learned from that isn't a list of rules. It's a very good internal sense of what words and ideas tend to go together, and what a reasonable continuation of a piece of text looks like given everything that came before it. Practically, that means you can hand it, "This still hasn't shown up and I'm getting worried," with no keyword matching involved at all, and ask it directly, in plain English, to classify what kind of message this is, and it genuinely handles that correctly, along with thousands of other phrasings, expressing the same underlying concern, without you ever having to enumerate them. You're not writing more rules to cover more cases. You're describing the task itself, once, in the language you'd use to explain it to a new employee, and letting the model generalize the rest. That reframes what automatable actually includes. Classification and routing. Is this email urgent, angry? A simple question. Spam become genuinely practical even when the categories are fuzzy and the phrasing is unpredictable. Extraction from messy, inconsistent text becomes tractable in a way it fundamentally wasn't with the tools from earlier in this course. Think back to reading tables out of PDFs, where a borderless table or an unusual layout needed a specific fallback strategy, and a genuinely irregular one needed manual cropping. An invoice from a vendor who changes their template every few months is exactly this problem. And it's exactly the kind of thing a language model handles by actually reading the text the way a person would, rather than depending on consistent visual structure to detect where a field starts and ends. Summarization, drafting a first-pass reply, rephrasing something into a different tone, all of these involve genuine language understanding and generation, not pattern matching, and that's precisely the category of task. None of the deterministic tools in this course were ever built to handle it all. Now, here's the honest part. Because this capability doesn't arrive for free, and pretending otherwise would set you up to build something fragile. Everything else in this course has been deterministic. The exact same input produces the exact same output, every single time, which is what let us write tests, trust the results, and run scripts unattended with real confidence. A language model's output is fundamentally not that. Ask it the same question twice, and you can get two different, both individually reasonable sounding answers. It can also state something confidently that simply isn't true. A failure mode specific to this kind of tool that has no real equivalent in a pandas data frame or a parsed HTML tag. There's a real cost per call, in both money and time, completely unlike a local Python function that runs in microseconds for free. And a response comes back over a network round trip, not instantly, which matters if you're chaining several calls together in a single workflow. None of that means the capability isn't worth using. It means it needs a different engineering posture than everything before it in this course. Where deterministic code earned your trust through testing and predictable output, an LLM's output earns trust through validation after the fact. Asking for a specific structured format like JSON and actually checking the response matches it, setting up a fallback path for when it doesn't, and keeping a human in the loop specifically for the steps where being wrong is genuinely costly, like actually sending a reply versus just drafting one for a person to approve first. The right mental model going forward isn't "the model is always right." It's "the model is very likely useful and worth checking before anything consequential happens because of it." So the actual shift this module is built around isn't replace everything you've learned with an LLM call. It's adding a genuinely new tool for exactly the piece of a workflow where writing an explicit rule was never realistic in the first place. A real, well-built automation often ends up combining both halves of this course directly. Deterministic code doing the reliable, structural work this entire course has already covered. Reading the spreadsheet, calling the API, moving the file, sending the message, and a language model doing specifically the one step in the middle that actually requires understanding language, or making a judgment call, classifying the message, drafting the reply, pulling a field out of text that refuses to follow a consistent format. Knowing where that boundary sits, and building the surrounding pipeline with the same discipline as everything else in this course, is genuinely the whole skill. Underneath everything in this lecture is something you already understand completely. This is just another REST API, the same request and response from the HTTP and REST module earlier in this course. You send a request, it comes back with a status code and a body, and that body happens to be JSON. What's actually new here isn't the mechanics of the call. It's what you're asking for in the request and what you get back in the response, since the entire point of this API is generating language rather than returning rows from a database or files from a drive. Let's set up the connection first. Google's current SDK is a single unified package, and it's worth being specific about the name because an older, now deprecated package shares an almost identical name and will conflict with it if both end up installed. Before we touch any code, you'll need a real API key. Go to Google's AI Studio website and sign in with a normal Google account. No separate Google Cloud account or billing setup is required to get started at all. In the left sidebar, click Get API Key, then click Create API Key. You'll be given a choice between creating the key in a brand new project or an existing one. For a first key, creating it in a new project is the simplest path, and Google sets that project up for you automatically behind the scenes. Copy the key once it appears. Google AI Studio does let you view it again later if needed, unlike some providers, but it's still worth treating it as a real secret from the moment it's created. One small current detail worth knowing. Google now automatically creates every new key as a more restricted key type rather than the older unrestricted style. This happens automatically, so it's nothing you need to configure, just something to be aware of if an older tutorial you find elsewhere shows an extra restriction step that no longer applies. A genuinely honest note on rate limits specifically. Google no longer publishes one fixed, guaranteed table of free tier request limits per model. What you'll find quoted around the internet are commonly cited figures, but your own actual limits are tied to your specific account and shown live in AI Studio's own dashboard. Treat any specific number you read as indicative rather than guaranteed, and check your own dashboard if you need the real current figure. Storing that key in a .m file rather than pasting it directly into your script matters for the same reason keeping the Google Workspace credentials file out of version control mattered earlier in this course. A key sitting in plain text inside a script is one accidental commit away from being exposed. A .m file keeps it in one small separate, easy-to-exclude file instead. In this code example, we load a package specifically built to read that file, call its load function once, and then read the key back out of the environment exactly as if it had been set at the system level. And the result is a simple confirmation that the key was actually found and loaded successfully. That load call reads the file and copies each line into the environment for the duration of the script's run, without you ever needing to touch your operating system's actual environment variables at all. Calling it once, right at the top of a script before anything else happens, is the pattern worth building as a habit. Everything after that point can read the key exactly as if it had been set at the system level. And this same one-time setup works identically whether you're on Windows, macOS, or Linux. In this code example, we load the key the same way, create a client, and send a single plain text question to the model, printing back whatever it says. And the result is a short, direct answer, generated live by the model itself. Notice the API key isn't hard-coded anywhere in this script. It's read out of that .m file instead, the exact same instinct behind keeping the Google Workspace credentials file out of version control back in that module. An API key is directly tied to your account, and treating it with the same care as any other secret in this course is worth building into the habit from the very first script you write, not something to clean up later. Compare the plain text response you get back here to what a lot of other providers' APIs hand back, and it's refreshingly direct. No list of typed content blocks to loop through, no checking a type field before reading anything. This particular SDK collapses that down to a single plain text property in the common case, which is worth appreciating precisely because it's simpler than it strictly needs to be, not something to distrust just because it's convenient. The model name is worth pausing on, because Gemini offers several tiers, and which one you reach for genuinely matters for whether this stays free. The specific Flash tier model used in these examples is one of the ones covered by the free tier. Fast, capable enough for most everyday automation tasks, and available without ever entering a payment method. The larger Pro tier models sit behind actual billing, so if you swap the model string here for one of those, you've quietly left the free tier without necessarily noticing until a bill shows up. It's also worth knowing that the exact model name is something you can freely swap out for whatever the latest version happens to be by the time you're actually building this. Google's AI Studio website lists every model currently available, along with which ones are free versus paid, so it's worth checking that list directly rather than assuming the specific model name used in these examples will still be the newest option later on. Since this is free, but not unlimited, it's worth understanding what free actually means here before writing anything that calls this in a loop. Google's free tier caps how many requests you can make per minute and per day, and going over that limit doesn't cost you money. It just returns an error instead of a response. In this code example, we wrap the same kind of request in a function that catches a specific error, waits a little longer on each retry, and tries again, up to a small maximum number of attempts. And the result is a script that quietly handles a rate limit by waiting it out, rather than crashing the moment it hits one. That specific error is the one you'll see when you've hit the free tier's request limits, and treating it as something to wait out and retry rather than a hard failure is exactly the right posture for a tool with real published usage caps. The waiting time doubling on each attempt, 1 second, then 2, then 4, is called exponential backoff. And it's a genuinely standard pattern anywhere a service asks you to slow down rather than rejecting you outright. Hammering the same request again immediately just triggers the same limit a second time, while waiting a little longer on each retry gives the actual limit window a real chance to reset. A system instruction is the mechanism for giving the model standing behavior that should apply throughout a conversation, kept separate from whatever specific question shows up in the actual request. In this code example, we send the same kind of question as before, but this time attach a system instruction describing a specific persona and style the model should follow. And the result is an answer written in that requested style, plain prose with no bullet points or headers, rather than, however, the model might have chosen to format it by default. Think of the system instruction as the role and ground rules, who the model should act as, and what constraints its answers need to follow, while the actual question carries the specific request itself. Separating these two matters in practice, because the system instruction stays fixed and reusable across many different questions, while the question itself is what actually changes from one call to the next. Last piece, an actual back-and-forth conversation. Since a single question and answer exchange is really just the simplest possible case of what this API supports. And this is a spot where Gemini's SDK genuinely does more of the work for you than you might expect. In this last code example, we create a chat object, send it a first message, print the reply, then send a follow-up question with no repeated context of our own, and print that reply too. Finally, we loop through the chat's own history and print each turn, and the result is a natural back-and-forth exchange, where the second answer clearly builds on the first question, without us ever having to remind it what we were talking about, followed by a clean printed record of the whole conversation so far. This is worth contrasting directly with how a lot of other providers' APIs handle conversation, since the underlying reality, that the model itself has no memory between individual requests, is exactly the same here too. What's different is who's responsible for carrying that history forward. Some APIs make you manually rebuild and resend the entire conversation list yourself on every call. Gemini's chat object does that bookkeeping on your behalf, sending a second message on the same chat object automatically includes everything said before it, without you manually appending anything to a list yourself. Looking at its history afterward is how you can actually inspect what's being carried forward under the hood. And seeing both a user role and a model role alternating in that output is the concrete proof that context is genuinely being maintained across calls, not just discarded and rebuilt from nothing each time. So the actual shape of using an LLM API from Python comes down to a handful of pieces that map directly onto ideas from earlier in this course. It's a REST call, exactly like the ones from the requests module, just with a request and response shape suited to generating language rather than returning records. A free tier is genuinely free in terms of cost, but it comes with real rate limits that a production-minded script needs to handle gracefully rather than ignore. A system instruction sets standing behavior separate from the specific question being asked. And a chat object can carry conversation history for you automatically, which is worth knowing about specifically because not every provider's SDK offers that same convenience. This is precisely the scenario that made structured, reliable model output worth caring about in the first place. Back when we first talked about why large language models change what's automatable. Go back to the PDF module earlier in this course, and pulling a table out of an invoice meant handling its specific layout directly. A bordered table needed one approach, a borderless one needed a completely different strategy, and a genuinely irregular layout needed manual cropping. That works when a vendor's invoice format holds still. It breaks the moment a different vendor sends something in a completely different shape because the underlying technique was built around visual structure, not the actual meaning of the words on the page. Our 3 sample invoices for this lecture all have that meaning in common. None of them have the same structure at all. A language model can read all 3 the way a person would. Not by matching a layout, but by actually understanding that different labels across all 3 are all pointing at the same underlying idea. The part that needs real engineering discipline isn't getting the model to understand that at all. It's getting it to hand that understanding back to you in a shape your code can actually rely on. Every single time, regardless of which invoice it happened to read. Start with the naive version and see concretely why it isn't good enough for an automated pipeline on its own. In this code example, we load one of our messy invoices, build a plain language prompt asking the model to extract the vendor, invoice number, date and total, explicitly requesting only JSON back with no other text, and print whatever comes back. This can genuinely work plenty of the time. It can also come back wrapped in a markdown code fence the model added out of habit, or with a stray sentence of commentary in front of the JSON, or with the total formatted as a currency string instead of a plain number, none of which your code was told to expect. Asking nicely in the wording of a prompt is a request, not a guarantee, and an automated pipeline built entirely on a request that's usually honored is exactly the kind of fragile thing this course has spent its entire runtime teaching you to avoid. The fix is telling the model exactly what shape to return, at the API level rather than only in the wording of the prompt, and then genuinely validating whatever comes back before trusting it at all. In this code example, we define a small data model describing exactly the fields we expect: a vendor name, an optional invoice number, a date, and a total that must be an actual number. This is an ordinary validation tool, the same one a lot of real Python applications already use for data checking outside of any AI context at all. Each field states its expected type directly, and the invoice number is marked optional specifically because not every invoice or receipt will have one, and forcing it to be required would break on legitimate documents that simply never had that field to begin with. In this code example, we hand that exact schema directly to the model alongside our messy invoice text, explicitly telling the API itself that the response format needs to be JSON, and that it needs to match our schema precisely, then read back an already validated object rather than a raw string. 2 things are doing real work here. Telling the API the response format needs to be JSON is a genuinely different and stronger guarantee than hoping a plain language instruction gets followed, and handing over the schema directly constrains the model's output to match that exact shape at generation time. The past result coming back is worth noticing specifically. It comes back as an already validated instance of our data model itself, not a raw string you still need to pass yourself. Google's own documentation is specific about one thing worth respecting here too. Don't also paste an example JSON output into the wording of your prompt on top of this, since that duplicates information the schema already provides, and can actually make output quality worse rather than better. Even with the schema doing real work at generation time, still validate what actually comes back, because a schema constrains what the model is asked to produce. It doesn't retroactively guarantee every possible edge case is handled perfectly. This is exactly where testing the validation layer directly, independent of any live model call, becomes genuinely useful. In this code example, we take a clean, correctly shaped piece of JSON, exactly the kind of thing a well-behaved response should look like, and run it through our data model's own validation. And the result is a fully parsed, correctly typed object, with a total already converted to an actual number, ready for real arithmetic downstream without any further conversion needed at all. That's a real tested result, not a hypothetical one. In this code example, we take a deliberately broken piece of JSON, one that's missing the total field entirely, and try to validate it the same way, wrapped in a try and except block this time. And the result is a validation error, caught cleanly, naming the exact missing field by name. This is exactly the failure you want caught here, rather than 3 steps further downstream in your pipeline, where a missing total might otherwise silently become a 0, or crash a completely unrelated line of code, with an error message that gives you no hint the actual problem was a field that never arrived in the first place. In this last validation example, we test something more subtle, a piece of JSON where every field is present, but the total came back as a currency-formatted string with a $sign still attached, instead of a clean number, and the result is another validation error, this time naming the exact reason, a string that couldn't be passed as a valid number. This one's worth sitting with, because it's exactly the kind of realistic model quirk that a schema alone doesn't fully eliminate. The model returned something JSON-shaped, and even returned it in the right field, but still included a symbol as part of the value instead of a clean number. Catching this with a real try and except block rather than letting it crash somewhere unrelated later, is what makes the difference between a script that fails loudly and specifically right at the point something went wrong, and one that fails mysteriously somewhere else entirely. Put together, this is the actual pattern worth carrying forward anytime a workflow needs structured data out of genuinely unstructured, inconsistent text. Define the exact shape you need as a data model first. Hand that model directly to the API, constraining generation itself rather than only hoping a written instruction gets followed. And then still wrap the actual parsing in a try and except block. Because a schema narrows the space of likely failures, it doesn't eliminate the need to check. So the mental model for this entire lecture comes down to treating a language model's output the same way you'd treat any other external, not fully trustworthy input to your program. Exactly the same instinct behind checking a web form's submitted data or validating a row pulled from a spreadsheet, someone else filled in by hand. Constrain what you're asking for as specifically as the tool allows. Validate what actually comes back before your code assumes it's correct. And when validation fails, let it fail loudly and specifically right at the point of the actual problem, rather than somewhere else downstream where the real cause is much harder to trace back. Getting one single invoice safely turned into one single validated object is where we left off last time. A real workflow almost never stops at one. It's a folder of 40 scanned receipts, or an inbox that's been forwarding invoices for a month. And the actual goal was never extract this one invoice. It was always turn all of these into rows in a spreadsheet I can actually total up and hand to someone. That shift, from one to many, introduces exactly one new problem worth taking seriously. What happens the moment one invoice in that batch doesn't extract cleanly, and whether that one failure is allowed to take the rest of the batch down with it. Start with the loop itself, processing each invoice the same way as last lecture, but this time catching failures individually instead of letting the whole script stop at the first one. In this code example, we loop through a list of invoice texts, sending each one to the model with our validation schema attached, and wrap each individual call in its own try and except block, appending successful results to one list and any failures to a separate list along with their error. And the result is a clean summary showing exactly how many succeeded and how many failed. The structural change from last lecture is small but genuinely important. The try and except now sit inside the loop, wrapped around a single invoice, rather than around the whole batch from the outside. That placement is the entire difference between one bad invoice quietly ending the whole run and one bad invoice landing in a separate list while everything else keeps going. Two genuinely different failure categories can show up here too, worth telling apart, even though this example catches both together for simplicity. A validation error means the model responded, but what it returned didn't match the schema, while a broader exception could mean the request itself failed outright, a rate limit or a connection problem, the same category of failure from the API call lecture a few lectures back. Here's the part that's actually testable directly, independent of any live call at all, because once you have a list of successfully passed objects, everything from here on is ordinary Python that behaves identically no matter where those objects came from. In this code example, we simulate a realistic batch of 4 responses, 3 genuinely valid ones and one that's deliberately not valid JSON at all, and run the exact same success and failure loop against them directly, without touching the live API. And the result is exactly 3 successes and 1 failure, with that failure's real error message captured and printed. That broken entry is deliberately not real JSON at all, standing in for the kind of response a real batch will occasionally produce, a network hiccup, a genuinely unusual invoice the model misread, or any of a dozen other real-world causes. It landed cleanly in the failures list with its actual error message attached, while the 3 legitimate invoices sailed through untouched, which is precisely the behavior worth building toward. A bad input becomes a logged, inspectable failure, not a crashed script, and not a silently dropped row nobody notices went missing. Now for turning the successful half of that batch into an actual spreadsheet, and this is where every structured object we've been building finally earns its keep. In this code example, we convert each successfully validated object back into a plain dictionary and hand the whole list straight to pandas to build a table. And the result is a clean table with every vendor, invoice number, date, and total lined up in matching columns, despite the 3 original invoices looking nothing alike. Converting each object back to a dictionary turns a validated object back into a plain Python dictionary, and a list of those dictionaries is exactly the shape a data frame has, expected every single time we've built one throughout this entire course. The same pattern used for cleaning messy spreadsheets, for data scraped off web pages, for rows pulled out of PDFs. Everything genuinely dissolves into the same shape the moment it's validated, regardless of how differently formatted the 3 original invoices actually were. In this code example, We write that table straight out to a real Excel file with a single call. And the result, confirmed by reading the file back afterward, is a real spreadsheet holding all 3 invoices, with a verified total sum across all of them. That one line, and the exact 3 vendors from 3 completely different original formats, sit side by side in identical columns, ready for an actual sum, a pivot, or anything else a human would do with a real spreadsheet. Reading that same file back afterward confirms it round-tripped intact, total column and all, which is worth actually checking rather than assuming a write succeeded just because no error appeared. It's worth knowing this destination isn't fixed to a local Excel file at all. The exact same rows list feeds just as naturally into a Google Sheet using the Values API from the Workspace module earlier in this course, or into any database or downstream system your own work actually needs. The model and the validation step did the genuinely hard part, understanding wildly inconsistent source text, and everything after that is just ordinary, already familiar data plumbing. The failures list deserves the same respect as the successes, rather than quietly vanishing the moment the script ends. In a real workflow, that list is exactly what should get written somewhere a person will actually see it. A separate sheet, a log file, an alert, specifically so a genuinely unreadable invoice gets a human's attention, instead of just disappearing from the batch with no record it was ever there at all. So the actual shape of this entire lecture comes down to one structural habit, layered on top of everything from the last 2 lectures. Wrap each individual item in its own try, and accept inside the loop, not around it, so one failure becomes a logged entry rather than a stopped script. Let successes and failures grow as 2 separate, clearly labeled lists throughout the whole run. And once you're holding a list of validated objects, treat it exactly like any other structured data this course has already taught you to work with. A table, an Excel file, a sheet, whatever the actual destination happens to be, since the hard, genuinely new part was already finished the moment validation succeeded. This is precisely the example that opened this entire module, back when we first talked about why language models change what's automatable. A business getting emails all day, needing to sort them by what they actually are, in a world where customers phrase the same underlying concern in a functionally unlimited number of ways. Now that this module has actually built the tools to handle that reliably, it's worth coming back and finishing the job for real, connecting it directly to the IMAP mechanics from the email automation module earlier in this course. Start with the classification itself, defining exactly what sorted needs to mean before writing anything that touches a real inbox. In this code example, we define a small data model describing exactly what a classification result should look like, a category restricted to one of 5 specific options, and a short explanation alongside it. This particular kind of restriction is doing genuinely important work here, distinct from a plain text field used for something like a vendor name in earlier lectures. It doesn't just describe the type as text, it constrains that category to exactly one of 5 specific values and nothing else, which matters enormously for a routing decision, since downstream code that checks which category came back needs to trust that field will never quietly contain some 6th value the model happened to invent. The explanation field is included deliberately too, not because a routing script strictly needs it to function, but because a one-line reason sitting next to every classification is exactly what makes a wrong one debuggable later, rather than a category with no context behind it at all. In this code example, we simulate the model trying to invent a category outside that allowed set entirely, and run it through validation anyway, and the result is a validation error, naming the exact allowed options and showing precisely which invalid value was rejected. That's a real tested result, and it's exactly the failure worth catching here rather than 3 steps downstream, where an unexpected category string might otherwise fall through every single routing rule silently, leaving an email unrouted with no error and no explanation at all. Now connect that classification to an actual live inbox, reusing the exact IMAP pattern from the email automation module. In this code example, we log into a real inbox, search for unread messages, and for each one, fetch its full content, walk through its parts to pull out the plain text body, and collect the subject and body together into a list. And the result is a list of real messages, each one ready to be classified. Nothing here is new. Searching, fetching, and walking a message's parts to pull out the plain text body are exactly the techniques from the downloading alanchums and filtering and flagging lectures, just extracting body text this time instead of an attached file. With a real message's subject and body in hand, classifying it is a single call, using the exact structured output pattern from the last 2 lectures. In this code example, we build a function that takes a subject and body, constructs a prompt asking the model to classify the email, and sends it off with our classification schema attached, returning the passed result. Same shape as extracting fields from an invoice, just pointed at a different kind of unstructured text, And that's genuinely the point. The model doesn't need a different technique for classification versus extraction. It needs a different schema, describing a different question. Routing is where this actually pays off, reaching back into the exact flagging and moving mechanics from the email automation module. In this code example, we build a function that looks at a message's classification and takes a different action depending on what it finds, flagging urgent messages, marking spam for deletion, and copying everything else into a category-specific folder before marking the original for deletion too. Every single one of these actions is exactly the flagging, copying, and delete then expunge pattern from the filtering and flagging lecture, with nothing new about the mechanics at all. What's actually new is that the decision about which action to take is no longer a keyword rule someone wrote by hand. It's whatever the model's classification came back as, which is precisely the shift this whole module has been building toward. An urgent message gets flagged, so it's visually impossible to miss. Spam gets marked for deletion outright. Everything else gets copied into a category-specific folder, following the same copy then flag for deletion pattern from that earlier lecture, with the actual deletion still committed later through a single expunge call once the whole batch is done. Putting the full loop together and handling one email's classification failing without derailing the rest of the inbox scan follows the exact batch pattern from last lecture. In this last code example, we loop through every fetched email, classify and route each one inside its own try and except block, and only call expunge once after the entire loop finishes. And the result is a script that quietly skips over anything it couldn't classify, leaving it untouched in the inbox, while everything else gets sorted and handled normally. Notice that final cleanup call only runs once after the entire loop finishes. Exactly the same batching reasoning from the flagging and moving lecture. No benefit to committing a deletion after every single message. And one message failing to classify cleanly just leaves it sitting untouched in the inbox rather than crashing the whole run, which is exactly the same safety habit from processing a batch of invoices last lecture, just applied to messages instead of documents. So the actual shape of this lecture is genuinely just 3 pieces this course has already built, connected together for the first time. IMAP handles reading a message's content and later acting on it, exactly as covered in the email automation module. A schema with a restricted set of allowed categories handles turning that message's free-form text into a routing decision your code can actually trust, and wrapping each message's classification in its own try and except keeps one unreadable email from taking down an entire inbox scan. The same discipline from processing a batch of invoices a lecture ago. Every technique this module has covered so far, extracting a field, classifying a message, has worked on a relatively short piece of text handed to the model in one single call. A real document doesn't always cooperate with that. A long report, a lengthy contract, a stack of several separate documents that all need to feed into one combined overview, feeding all of that into a single prompt at once, tends to produce a summary that's noticeably vaguer than a shorter, more focused one. Since the model is being asked to compress an enormous amount of material in one pass rather than genuinely working through it piece by piece. The fix is a pattern with a name worth knowing because it shows up constantly in real LLM-powered pipelines. Split the document into manageable pieces, summarize each piece on its own, and then summarize those summaries together into one final result. That's usually called map-reduce summarization, borrowing the name from the same general idea in data processing. Map a function across many pieces independently, then reduce the results down into one. Start with the part that doesn't need a live model call at all, because splitting a document into sensible pieces is a genuinely testable, deterministic problem on its own. In this code example, we build a function that splits a document into paragraphs, then groups those paragraphs together into chunks, starting a new chunk only once adding the next paragraph would push it past a size limit. We run it against our real sample operations report, and the result is 4 clean chunks, each one a genuine, complete grouping of whole paragraphs, never a fragment cut off mid-thought. The important design choice here is splitting on paragraph boundaries first, rather than just cutting the raw text at a fixed character count. Cutting blindly at a fixed length would happily slice straight through the middle of a sentence, handing the model half a thought with no way to know it was ever cut off. Grouping whole paragraphs together instead, and only starting a new chunk once adding the next paragraph would exceed the limit, guarantees every chunk the model actually sees is a complete, coherent piece of the original document, never a fragment. In this code example, we run that same function again on the same document, but with a larger size limit this time, and print out how many paragraphs landed in each resulting chunk. And the result is just 2 chunks this time, each one now holding several whole paragraphs grouped together, instead of being split into as many separate pieces. Same document, same function, just a larger limit, and it correctly grouped more whole paragraphs into each chunk instead of splitting into as many pieces. That's the entire map steps input sorted out, and it's worth having confidence in this part specifically because it's the one piece of the whole pipeline you can verify completely without spending a single API call. Now the map step itself, summarizing each chunk independently. In this code example, we define a function that sends one chunk to the model with a short instruction to summarize its key points in a couple of sentences, then run that function across every chunk we just produced. Each chunk gets summarized with no awareness of the others at all, which is precisely why this scales. A chunk deep into a 50-chunk document costs exactly the same, individually, as the very first one, and none of them need to see the whole original document at once to do their job well. The reduce step is where those individual summaries actually become one coherent digest, rather than just a pile of disconnected bullet points sitting next to each other. In this code example, we join all of the chunk summaries together and send them back to the model one more time, this time asking it to combine them into one cohesive paragraph, explicitly naming which report they came from. This reduce call is doing something genuinely different from the map step, and it's worth being clear about the distinction. The map step summarized content the model had never seen before. This step is summarizing summaries, text that's already been compressed once, being compressed again into something a person could read in 10 seconds rather than working through section by section. Labeling the source explicitly in the prompt, rather than just handing over the combined text with no context, is what keeps the final result readable as a coherent piece of writing, instead of a set of loosely related fragments stitched together. A genuine digest almost never comes from just one document, though. It's usually several separate reports arriving from different parts of a business, all needing to land in one person's inbox as a single readable overview. In this last code example, we wrap the entire chunk summarize combine process into one function that handles a whole document from start to finish. Then run that function once for our operations report and once for our marketing report, and join both resulting summaries together into one final, combined digest. Every one of these documents runs through the exact same map, then reduce pipeline independently, regardless of which department it came from, or how long it originally was, and the results get stitched together at the very end into one combined weekly digest. That final digest is genuinely just plain text at this point, which means it can go anywhere. Plain text can go printed to a log, saved to a file, or handed straight to the email sending pattern from earlier in this course, wrapped in a message object, and delivered through SModel to land in someone's inbox as an actual daily or weekly digest email, without a person ever needing to read the original reports at all. So the mental model for this entire lecture comes down to a pattern worth recognizing anywhere a document is too long or too numerous to reasonably hand to a model in one single call. Split first, respecting the document's own natural structure rather than cutting blindly at a fixed length. Summarize each piece independently, since none of them need the others to do their own job well. And combine those summaries in a second, distinct pass that's explicitly told what it's actually looking at, rather than assuming the model will automatically understand a pile of already condensed fragments as one coherent whole. Here's an uncomfortable thing worth saying directly. After 10 modules building genuinely real, working automation, every single script this course has built so far shares one quiet, unexamined flaw. Every one of them still needed a human being to sit down, open a terminal, and actually type the command that runs it. And that single fact means, in the fullest sense of the word, none of them were actually automated at all. Think through what that word is actually supposed to mean. Automated means something happens without a person needing to remember it, decide to do it, or be present for it, on its own schedule, in response to its own trigger, whether or not anyone in the building is thinking about it that day. A script sitting on a laptop, technically capable of generating a perfect invoice report the moment someone runs it, but only ever actually running when a specific person remembers to open a terminal on the 1st of the month, hasn't automated the invoice process at all. It's replaced manually pull the numbers together with manually remember to run the thing that pulls the numbers together, which is arguably a worse problem to have, since now there are two things that can fail instead of one: the task itself and a human's memory of when to trigger it. Walk back through this course, and the examples pile up fast. The weekly digest, built out of long, messy reports, was designed around the idea of someone getting a clean summary without reading 5 documents themselves. But a digest that only gets generated when someone remembers to run the script isn't really a digest. It's an occasional, manual export that happens to look impressive when it does happen. The scraper checking a competitor's prices was built entirely around the idea of knowing the moment something changes. But if a person has to remember to run it every morning to find out, the person is still doing the actual monitoring, and the script is just speeding up one small step in a process. A human is still fully responsible for carrying. Even the GUI automation from the last module, built specifically for legacy software that offers no other way in, doesn't save anyone real time if it still needs a person sitting there, watching, ready to launch it, and babysit it through to completion. This isn't a criticism of anything built so far in this course. Every technique from every previous module is genuinely necessary. You cannot schedule a script that doesn't reliably do its actual job first. But reliability while a human is watching and reliability while nobody is watching turn out to be two different bars entirely, and this entire module is about closing that specific gap. Making a script genuinely safe to run unattended, with no one watching the terminal at all, means revisiting several habits this course has already touched on, and taking each one seriously in a way that only matters once a human stops being present to catch a problem. Every print statement this course has used, throughout every single module, was implicitly written for a person sitting there watching it scroll by. The moment nothing but a scheduler triggers a script, nobody's watching that terminal at all, which means anything printed to it effectively vanishes into nothing. Logging to an actual file, something a person can check later, without needing to have been staring at a screen at the exact moment something happened, is the real replacement for print in anything meant to run unattended. Error handling changes meaning too. Throughout this course, catching an exception and printing a clear message was treated as good practice, and it genuinely is, but a clear error message printed to a terminal that closed itself the moment the scheduled run finished is a message nobody will ever actually read. An unattended script needs its failures to reach an actual person somehow, an alert email, a message to a monitored channel, a log a person genuinely checks, rather than a perfectly well-written error sitting silently in a window that closed itself 5 minutes after the problem occurred. Credentials need to survive without a human ever typing them in at the moment of use. Every pattern this course built around environment variables, saved OAuth tokens, and app passwords stored outside of any script itself was already preparing for exactly this. A script triggered by a scheduler at 3 in the morning genuinely cannot pause and wait for someone to type a password, so anything still requiring interactive login at the moment it runs isn't actually ready to be scheduled at all yet. And a script running on its own needs to survive being run more than once safely, which is a genuinely different bar than working correctly the one time you personally ran it while watching. The saved session and token patterns from browser automation and Google Workspace alike, all of that existed specifically so a script could be safely run again without redoing work or sending the same email twice. An unattended script might run twice by accident, might overlap with a previous run that hadn't finished yet, or might need to pick up cleanly after being down for a day. And a script that assumes it's only ever running exactly once, at exactly the moment a human decided to trigger it, breaks in exactly the situations where nobody's there to notice it happening. So the actual preview for the rest of this module is genuinely just closing this one gap, using tools this course hasn't needed until right now. The operating system's own built-in scheduler, whether that's cron on Linux and macOS or Task Scheduler on Windows, and cloud-based options for a script that needs to run somewhere other than your own personal machine, which itself isn't switched on and connected every single hour of every single day. None of that works safely though, until a script actually earns the right to run with nobody watching, which is exactly the checklist worth carrying forward from here. Log to a file, instead of printing to a terminal nobody's watching. Make failures reach an actual human, rather than die quietly in a closed window. Keep every credential loadable, without a person typing anything at the moment of use. And design for being run more than once safely, because an unattended script eventually will be, whether that was the plan or not. Here's a script that works perfectly. It reads a bakery's daily sales, calculates the revenue, finds the best seller, and writes a clean report to a file. The only problem is that it only runs when someone opens a terminal and types the command. Right now, that someone is you, and that someone has to remember, is exactly the kind of dependency we want to get rid of. Let's look at the script first, and then we'll take the human out of the loop. In this code example, we start by opening a sales file, a CSV file called bakery sales, and reading each row into a list, converting the quantity and price into numbers as we go. Then we calculate 3 things: the total number of items sold, the total revenue, and the best seller, which is just the item with the highest quantity. We build all of that into a short text report with today's date and time at the top. Finally, we create a folder called reports if it doesn't already exist, and save the report inside it as a text file named with today's date. And the result is a script that, every time you run it, drops a fresh, time-stamped report into that reports folder. Save it, run it, and check the reports folder. You'll see a new file appear with today's date in the name. Notice the 2 things this script depends on. The sales file and the reports folder are both referred to by name only, not by their full location on the computer. That's completely normal for a script you run yourself, because your terminal is already sitting in the right folder. It's about to become important, so keep it in mind. Now let's schedule it. Open the Start menu and search for Task Scheduler. You'll get the built-in Windows app, no installs, nothing to download. On the right-hand side, click Create Basic Task. This launches a wizard, which is the friendliest way to do this the first time. Give it a name, something like Bakery Daily Report, and an optional description. Then hit Next. Now you'll choose a trigger. This is the schedule itself, daily, weekly, monthly, or a few other options like when the computer starts or when I log on. For a report that needs to run every single day, choose Daily, then Next, and set the time you want it to fire, say 11 p.m. after the shop has closed for the day. Next is the action. Choose Start a Program. This is the part people usually get wrong, so let's go slowly. In the Program/Script field, you do not put the path to your Python file. You put the path to the Python interpreter itself, a file called python.exe tucked inside your Python installation folder. If you're not sure where that is, open a terminal and ask Windows to find it for you, and it'll print the exact path. It's fairly common for that command to print nothing at all, even though Python works perfectly fine. That almost always means Python isn't on your system's path, which happens if you installed it without checking the box that adds it during setup. There's a quick way to tell. Ask for Python's version using the launcher instead, by typing py_version. If that prints a version number, Python is there, it's just not on the path. The launcher registers itself a different way. If neither command works, close and reopen your terminal first, since path changes never apply to a terminal that was already open before you installed Python. And if you still get nothing after that, the interpreter genuinely isn't installed yet. Either way, none of this matters for Task Scheduler itself. You just need the full path to python.exe, which you can usually find inside your user folder under App Data Local Programs Python. Then, in Add Arguments, you put the path to your script, the Bakery Daily Report Python file. And here's the field almost everyone skips, Start In. This is the working directory the script runs from, and it's the fix for the relative paths we noticed earlier. Set this to the full folder path where your script and your sales file both live. If you leave Start In blank, Windows Task Scheduler runs your script from a completely different default folder. Your script will look for the sales file right where it's standing, won't find it, and crash with a file not found error, even though the exact same script ran fine 2 minutes ago from your terminal. This single empty field is the single most common reason a scheduled script mysteriously fails the first time. Set Start In, and this entire class of bug disappears. Click Next, review the summary, and click Finish. Your task now exists, but before you trust it to run at 11 p.m. tonight, right-click it in the task list and choose Run. This fires it immediately, exactly as Windows will later, so you can confirm it actually works unattended. Check the Reports folder. If a new report shows up, you're done. If it doesn't, that Start In field is the first place to check. We've already got the bakery report running on its own schedule on Windows, but most of the servers running Python in the real world are Linux, and every Mac ships with the same scheduling tool built in. So let's do the exact same job here, with a completely different tool, cron. Cron has been around since the 1970s, and it's still the default way to schedule anything on Mac or Linux. There's no app to open. It's a background process that's already running on your machine right now, quietly checking a schedule once a minute, waiting for something to do. That schedule lives in a file called a cron tab, short for cron table, and every user has their own. To open yours, you type cron tab -e. I'll list each command on screen as we go, exactly as you'd type it into your own terminal. The first time you run this, it might ask you to pick an editor. Nano is the friendliest option if you're offered a choice. Either way, you'll land in an empty file, ready for a schedule. A cron tab line has two parts, when to run something and what to run. The when is 5 numbers in this order, minute, hour, day of the month and day of the week, and a star means any value. So if we want our bakery report to run every day at 11 p.m, the timing looks like this, listed here, 0:23, ***, 0 minutes past, hour 23, any day of the month, any day of the week. That's every day at 11 p.m. in 5 characters. After that comes the command itself. And this is where cron has almost the exact same trap Task Scheduler had. Cron doesn't know about your terminal shortcuts, your usual folder, or most of your normal environment. If you just write Python 3 and the script's name, there's a real chance cron won't even know what Python 3 means, because it isn't using your regular path. So we spell everything out, in full. The complete path to the Python interpreter and the complete path to the script, both listed on screen here. You can find your own Python's exact location by running Python 3 in a normal terminal first. There's one more piece worth adding, and it solves a problem you can't even see yet. By default, cron throws away anything your script prints, and it does the same with any error message if the script crashes. It'll fail completely silently, and you'll have no idea why. The fix is to redirect that output into a log file by appending 2 greater than symbols after the command, followed by 2 greater than ampersand 1, which grabs error messages too, not just normal print statements. You can see the full line laid out here. Now anything the script prints and anything it fails with lands in a log file where you can actually go read it. Save and exit. In Nano, that's Ctrl-O, Enter, then Ctrl-X, and cron picks the new schedule up automatically. No restart needed. To confirm it's saved, the command is crontab, space, -L, listed here as well. That lists everything currently scheduled for your user. If your line's there, you're set. Now, waiting until 11 PM to see if this actually works is a bad use of your evening. Instead, open the cron tab again, and temporarily change the time to a couple of minutes from now, whatever your clock currently reads. Save it, wait, and then check 2 things. The reports folder, for a new report file, and the log file to see exactly what the script printed. If both show up, put the real 11 PM schedule back and you're done. If the report doesn't show up and the log file is empty or missing entirely, that almost always means one of the full paths is wrong. Check the Python path again and double-check the script's actual location. And if you see something in the log, but it's an error about a file not being found, the sales file specifically, that's the same relative path bug we ran into with Task Scheduler, just wearing a different hat. Cron doesn't run your script from inside its folder, so the sales file and the reports folder, both written as relative paths inside the script, won't resolve. The fix is to change into the right folder as part of the cron line itself, before running the script, using CD followed by 2 ampersands, meaning go to this folder, and only if that worked, run the next command. You can see that full version of the line here too. It puts the script back in the exact folder it expects to be in, relative paths and all. And that's a Python script running on its own schedule, on Mac or Linux, without a single line of the script itself changing. Same as Windows, same idea, different 5 characters doing the scheduling. Both Task Scheduler and cron have the exact same weak point. They depend on a machine that's turned on. If your laptop's asleep, or it's a Tuesday and you took it in for a repair, that 11 PM report just doesn't happen. No error, no warning, it simply never runs. GitHub Actions fixes that, because the schedule doesn't live on your computer at all. It lives on GitHub servers, and they're never off. And the best part, for a script like ours, this is completely free. Here's the idea. Our bakery script and its sales file already live in a folder. Let's put that folder in a GitHub repository. Once it's there, we can add one extra file that tells GitHub, run this script yourself, on this schedule, on a computer you provide. GitHub spins up a temporary Linux machine, runs our script on it, and then throws that machine away, every single day. That instruction file goes in a specific folder GitHub always looks for, called .github/workflows. Inside it goes a YAML file. YAML is just a plain text format for writing configuration, and we'll call ours dailyreport.yml. In this code example, we start with a name for the workflow, so it shows up clearly on GitHub. Then we define 2 ways this can start. A schedule, using the exact same 5-character cron pattern we already know. Minute, hour, day, month, weekday. And a second trigger called workflow dispatch, which adds a manual run workflow button right there on GitHub. So we're not stuck waiting on the clock to test this. There's a catch on that schedule line that trips up almost everyone the first time. GitHub Action schedules always run in UTC, never your local time zone. If your bakery closes at 11 PM Eastern Time, you can't just reuse the same timing we used on Windows and cron, you have to convert it. Eastern Time is a few hours behind UTC, so 11 PM Eastern lands around 4 AM UTC, the same cycle, which is exactly why the schedule in this example says 4 AM, not 11 PM. Get this wrong, and your report will fire at some seemingly random hour that makes no sense. Until you remember it's actually running exactly on schedule, just in a different time zone than the one you were thinking in. Next in this file is a permissions section, granting contents right access, and this one's a newer gotcha. By default, GitHub gives a workflow read-only access to your repository, which is a sensible default. Except our workflow needs to push a new report file back into the repo, and read-only access will make that push fail silently with a permissions error. This one line grants exactly the access needed, and nothing more. Then come the actual steps, read top to bottom. The first step checks out your repository, pulling a fresh copy onto that temporary machine. Without it, the machine wouldn't even have your script on it. The second step sets up Python for us. Our bakery script only uses the standard library, so nothing extra needs installing here. But if a script of yours needs outside packages, this is where an install step would go. The third step simply runs the script exactly the way we would locally. And here's the gotcha that catches people the hardest. That temporary machine gets deleted the instant the workflow finishes. Anything the script wrote, our report file included, vanishes along with it, unless we do something with it before that happens. That's the entire purpose of the last step. It commits the new report file straight back into the repository and pushes it, so it survives after the temporary machine is gone. Notice it sets a name and email first. GitHub requires every commit to have an author, and there's no human logged in here to supply one, so we invent a bot identity for it. The fallback message at the end of that step isn't decoration. It stops the whole job from failing on days the numbers happen to produce an identical report to yesterday's, when there'd be nothing new to commit. To try this yourself, push this file to your repository, then open the Actions tab on GitHub. You'll see Daily Bakery Report listed as a workflow. Click into it, and you'll find that Run Workflow button we added. Press it, and watch the job run in real time, step by step, right there in the browser. If it succeeds, check your repository's reports folder. A new commit should already be sitting there with today's file. If it fails, the very first two places to check are the ones we just covered. The permission section, if the failure happens on the push step, and the schedule line, if the job ran but seemingly at the wrong time. One last thing worth knowing, GitHub doesn't promise your scheduled job fires at the exact minute you asked for. During busy periods, it can be delayed by a few minutes. For a daily report, that's completely irrelevant. But it's worth knowing, this isn't a guarantee for anything that needs to the second precision. And with that, our bakery report now runs completely on its own, on a computer nobody has to own, keep charged, or leave turned on. The closest thing to true set it and forget it we've built yet. Picture this. The bakery report script works perfectly. You've scheduled it, tested it, even automated it 3 different ways. Now the bakery owner asks for a copy she can run herself on the one night a week you're not around. So you do the obvious thing. You email her the report script, a file ending in .py, and one of two things happens. Either nothing happens at all, or the file opens in a text editor, showing her a screen full of code she has no reason to understand. Either way, she calls you. It's tempting to treat this as a "she's not technical enough" problem. It isn't. The file you sent was never actually a finished product. It's a set of instructions, written for a machine that already has a very specific setup in place. Yours has that setup, hers doesn't. And every one of those missing pieces is something you stopped noticing a long time ago. Because your own computer quietly satisfies all of them without you ever having to think about it. Let's pull that apart, one piece at a time, because this list is exactly what we're going to eliminate for her over the next few lectures. First, Python itself has to be installed, and not just any version, but one compatible with what the script needs. You installed this once, months ago, and forgot about it the moment it worked. She's never installed it, doesn't know what it is, and has no reason to. Second, if the script imports anything beyond the standard library, those extra packages need to be installed too, with pip, and ideally the same versions you tested with. You probably did this inside a virtual environment you set up once and never think about anymore. She has no virtual environment, no packages, and no idea what either of those words mean. Third, and this is the one people forget, she needs to know that a file like this isn't something you just open. It's something you run, from a terminal, with a specific command, from inside the correct folder. That's an entire skill in itself, one you built up gradually, and one that has nothing to do with understanding bakery inventory. And fourth, if anything at all goes wrong, a typo in a file path, a missing package, a version mismatch, the script needs a human nearby who can read a Python error message and make sense of it. That's you. It has never once been her. Now here's what actually happens on her machine, mechanically, if she double-clicks that file anyway. On most Windows setups, a file like this is associated with either a text editor or the Python launcher, and it's genuinely a coin flip which one wins, depending on how Python was installed. If it opens in a text editor, she sees code and nothing runs. If the Python launcher grabs it instead, a console window can flash open and close in under a second, because the script finishes, or crashes, before she can read a single line of it. And, from her side, it looks like absolutely nothing happened at all. There's no error message she can screenshot and send you, because the window that would have shown her one is already gone. None of this is a flaw in her. It's a flaw in treating source code as if it were a finished application. Every one of those 4 requirements, the interpreter, the packages, the terminal fluency, the willingness to read an error, has to be true on her machine before this script becomes usable to her, and right now, none of them are. What she actually needs is something that doesn't ask any of that of her. A single file she can double-click that already carries everything the script needs to run bundled inside it, so it behaves exactly like any other app on her computer. Open it, watch it do the thing, done. That's precisely what we're building next. We're going to take this exact script, unchanged, and package it into a single standalone file using a tool called PyInstaller, one that runs on her computer with no Python installation, no pip packages, and no terminal required on her end at all. Same script, completely different coworker experience. The bakery owner still can't run a .py file and packaging it into an executable solves that, but it still hands her a black box that quietly does something and closes. What if, instead, she got something that actually looked like an app? A page with a button, a place to upload today's sales, and a report she can read right there on screen. That's what Streamlit gets us, and the surprising part is how little code it takes. Streamlit turns a normal Python script into an interactive web page. No HTML, no CSS, no JavaScript. You install it once using pip, and then you write Python the way you already know how, just calling Streamlit functions instead of print. Let's rebuild the bakery report as an actual app. In this code example, we start by giving the page a title and a short instruction line. Then we add a file uploader, so the bakery owner can browse for and select today's sales file herself, no folder path required. Once a file's been chosen, we open it as text and read it the same way we always have, row by row, converting quantity and price into numbers. Then comes a button labeled Generate Report. Once it's clicked, we run the exact same math as every bakery script before this one. Total items sold, total revenue, and the best seller. But instead of writing that to a file, we display it directly on the page. A subheading with today's date, a couple of clean little stat cards for the numbers, and a line naming the best seller. Underneath that, we add a download button, so she can save the finished report to her own computer with one click. And the result is a real clickable page, not a script running invisibly in the background. One line deserves a pause, the part that wraps the uploaded file using Python's I/O module before reading it, decoding it as UTF-8 text. When she uploads a file through Streamlit, what your script receives isn't a file path like we've used before. It's the file's contents held in memory, in binary form. Our reader expects text, not binary, so this line converts it to text first. Skip this step, and you'll get an error complaining about bytes versus strings the moment you try to read it. To run this, it's not the usual way we've run scripts so far. Streamlit has its own command. Streamlit space run and then the file name. This starts a small local web server and opens a browser tab automatically. Save it, run it, and try uploading the sales file. You should see the metrics and bestseller appear the moment you click Generate Report, and a working download button underneath. There's one behavior that catches everyone off guard the first time. Streamlit reruns your entire script from the top, every single time anything on the page is clicked. The upload, the button, all of it. It's not simply updating one part of the page. Behind the scenes, your whole script executes again, start to finish. For a script this size, that's invisible and completely harmless. But it explains something that looks like a bug the first time you see it. If you ever try to store a running total in a plain variable across multiple clicks, it'll reset to 0 every time, because the script is, quite literally, starting over from line 1. That's not a problem here, since we recompute everything fresh from the upload each time. But the moment you build something that needs to remember data between clicks, that's what session state is for, and we'll get there when we need it. Right now, this still needs Python and Streamlit installed on whichever machine runs it. So as it stands, it solves she has a nice interface to click. But not yet, she doesn't need Python installed at all. Next, we'll take this exact app and put it somewhere she can open with nothing but a link. No install, no terminal, not even Streamlit on her machine. Right now, this app only exists on your computer. Running it starts a server on your machine, for as long as your machine stays on. Which means the bakery owner still needs Python installed, still needs the terminal command, and still needs your laptop to be running at the exact moment she wants a report. We've solved that exact problem twice already, for 2 different tools. Let's solve it a third time, for this one. And this time, the fix is a single link she can open from her phone. We're going to use Streamlit Community Cloud, which hosts apps like this one for free, directly from a GitHub repository. First, this app needs its own repository, separate from the scheduled report and its workflow file, for the reason we've already touched on. Streamlit Cloud redeploys your app automatically every time something gets pushed to the branch it's watching. If this lived in the same repo as a bot that commits a new report every night, the live app would restart itself once a day for no reason connected to the app at all. A dedicated repository means the only thing that ever triggers a redeploy is an actual change to the app. So push your app file into its own fresh repository and add one more file alongside it, called requirements.txt. That file has just one line in it, Streamlit followed by 2 equal signs, followed by a version number. This is the file Streamlit Cloud reads to know what to install before running your app. It feels almost too small to matter, but skip it, and the deployment fails outright. The cloud service has no way to know your app needs Streamlit itself, or any other package it imports, unless this file spells it out. Pin the version, like we've done here, rather than leaving it blank. An unpinned install can quietly grab a newer Streamlit release next month that changes some behavior you tested against. With both files pushed, go to Streamlit's sharing site and sign in with your GitHub account, the same one the repository lives in. Click New App, and you'll be asked to pick 3 things. the repository, the branch, usually called main, and the file path to run, which is your app's file name. Before you click Deploy, click Advanced Settings and change the Python version to 3.12. Here's why that matters. Streamlit Cloud's default environment can occasionally land on a very new Python version before one of Streamlit's own under-the-hood dependencies. A package called Pillow has a ready-built version available for it, and when that happens, the build fails with a confusing error mentioning something called zlib. It has nothing to do with your code. Setting the version to 3.12 upfront sidesteps that entirely, so you'll never see that error in the first place. With that set, click Deploy. What happens next takes a minute or two. Streamlit Cloud pulls your repository, reads that requirements file, installs everything listed, and starts your app on its own servers. You'll see a build log scroll by, genuinely worth watching the first time, since if something's misspelled in the requirements file, this is exactly where you'll see it fail, with a clear reason why. Once it finishes, you get a real public web address. That address is the entire point of this lecture. Send that to the bakery owner, and she opens it exactly like any other website. No Python, no terminal, not even Streamlit installed on her end. Just a link and a browser. Two things worth knowing before you hand that link over. First, free apps on Streamlit Cloud go to sleep after a stretch of no visitors. The first person to open the link after that sees a message saying the app is waking up for several seconds before it loads. That's completely normal. But if nobody warns her about it, it looks exactly like the app is broken, so it's worth a one-line heads up. If it takes a few seconds the first time, that's normal. Just wait. Second, and this matters more than the sleep screen, that web address is genuinely public. Anyone holding the link can open the app, upload a file, and see whatever it calculates, including actual bakery revenue numbers. For a demo, that's harmless. For real for sales data, it's worth pausing on. Don't share the link outside the people who should see it. And if the data's sensitive enough to matter, Streamlit Cloud does offer viewer restrictions on paid tiers. Something worth knowing exists, even if it's out of scope for what we're building today. And that's the loop fully closed, for this tool at least. The same script, first tested locally, then wrapped in a UI, is now running on a computer neither of you owns, reachable from anywhere, with nothing installed on the other end but a browser. Back when we first ran into the problem of a coworker who can't run a .py file, we ended on a promise, a single file she can double-click, with nothing else required on her end. Streamlit solved that for something that lives on a web page. Now let's solve it for something that lives entirely on her own computer. No browser, no internet connection required, just a double click. The tool for this is called PyInstaller, and what it does is genuinely worth understanding, not just running. It takes your script, a full copy of the Python interpreter, and every package your script imports, and bundles all of it into a single executable file. She's not running Python. She's running a program that happens to have Python sealed inside it invisibly. Install it the same way as any package, using pip. Then, from inside the folder with our bakery script, you'd run PyInstaller with a flag called --1 file, followed by the script's name. That one file flag is doing real work. Without it, PyInstaller produces a whole folder full of support files instead of one clean executable. And a folder full of files isn't something you can casually hand someone. With it, everything gets packed into one file. This takes a minute or two, and it creates a few things. A build folder, which is just PyInstaller's own scratch space, ignore it. A spec file, which describes exactly how the build was configured. Useful if you rebuild this later, but not something to touch yet. And a dist folder, and inside that, the one file that actually matters. The finished executable. That single file is the whole product. Copy it anywhere. A USB drive, an email attachment, a shared folder, and it runs on a Windows machine with zero setup, zero Python installation, zero terminal. Before you hand it over though, there's a real gap between this works when I run it, and this works when she double-clicks it. And it's worth walking through, because each piece is a genuine teaching moment. First, our script reads the sales file from whatever folder it's sitting in. PyInstaller bundles your code and its dependencies. It does not automatically bundle a separate data file the script expects to find next to it. So the executable alone isn't the whole picture. The sales file has to travel with it, sitting in the same folder. Forget this, and she'll get the exact same file not found error we've already seen twice before, just wearing an executable's clothing instead of a script's. Second, try double-clicking the executable yourself right now, before shipping it anywhere. You'll likely notice the console window flashes open and closes almost instantly, because the script finishes running in a fraction of a second, and the window that was showing its output disappears the moment there's nothing left to show. From her side, that looks exactly like nothing happened at all, which is the one thing we're trying hardest to avoid. The fix is one line, added to the very end of the script, a line that asks for input and displays a message asking her to press enter to close the window. That single line pauses execution and keeps the window open until she actually presses a key, which means she gets a real moment to read that the report was saved before the window disappears. Add that line, rebuild with the same command as before, and this problem is gone for good. One more thing worth knowing, not a bug so much as a boundary. This only builds a Windows executable, because Pi installer packages for whatever operating system it's currently running on. If a coworker on a Mac needs the same thing, this exact command has to be run again on an actual Mac, producing a completely separate file. There's no cross-building one file that runs everywhere. Streamlit's browser link from a couple of lectures ago remains the one option here that genuinely works identically for everyone, regardless of what they're running. Weigh that against what a standalone executable gives you instead. It works completely offline, with no server, no internet connection, and no dependency on a service like Streamlit Cloud staying up. For a bakery owner who wants something reliable sitting on her own desktop, that trade-off is often exactly the right one. A link is more universal, but an executable is more hers. And that's the coworker problem solved a second, completely different way. Same script, same math, now sealed into one file that runs the moment she double-clicks it. Console window included, smart screen warning explained in advance, and nothing on her machine but the file itself. Here's what this project looks like when it's finished. I drop a supplier invoice into a folder, just drag it in, nothing else. A few seconds later, without me touching anything, a new row appears in a spreadsheet. The vendor, the invoice number, the date, the total, all correctly filled in. The original file has already moved itself into an archive folder. I never opened it. I never typed a single number. That's the whole project, running end to end. The problem this solves is one almost every small business quietly deals with. Invoices arrive constantly. Email attachments, scanned receipts, photos taken on a phone, and somebody has to open each one, find the right numbers, and retype them into a spreadsheet before anyone can see what's actually being spent. It's tedious, it's repetitive, and it's exactly the kind of task that's easy to fall behind on, because nothing forces it to happen the moment an invoice actually arrives. Riverside Bakery, our running example for this project, gets invoices from several suppliers, and none of them format things the same way. One supplier sends a clean, properly labeled invoice. The next month, that same supplier's invoice looks completely different. Lowercase name, a different date format, no line labeled total at all. A different supplier altogether sends one with no invoice number anywhere on the page, and a total that only makes sense once you subtract a loyalty discount from a subtotal. A rigid script that expects one exact layout falls apart the moment any of that changes. This project is built specifically to not care. Over the lectures ahead, we're building this in 6 stages, each one solving a distinct piece of the problem. First, a folder that notices the instant a new invoice lands in it, whether it's a PDF or a photo. Second, actually reading that file, pulling text out when it's there, and handing the image straight to an AI model when it isn't. Third, asking the AI to identify the vendor, the invoice number, the date and the total, even across wildly different layouts. Fourth, forcing that answer into a consistent, structured shape a script can actually rely on, instead of a paragraph that reads differently every time. Fifth, checking that shape for anything that looks wrong or missing before trusting it. And finally, logging the result to a spreadsheet and archiving the file, so nothing gets processed twice and nothing gets lost. By the end, this isn't a script you run when you remember to. It's a pipeline that runs on its own, indefinitely, and only asks for a human the moment something genuinely needs one. Let's start building it. Before any AI touches a single invoice, this project needs somewhere to live. And it needs test invoices messy enough to actually expose problems, not just prove the happy path works. Start with the folder structure itself, one main project folder, and inside it, 3 subfolders, incoming, processed, and sample invoices, plus a requirements file. 2 of these folders exist because of how this pipeline is going to work, not just for tidiness. Incoming is the folder we'll watch for new files. The moment a PDF or image lands there, that's the trigger. Processed is where a file goes once it's been handled, so the same invoice never gets read twice. We haven't written a line of watching or archiving logic yet. That's coming. But the folders exist now, so the rest of this project has somewhere to point to. Sample invoices is different, and it's worth explaining why it's kept separate from incoming at all. Once we start testing, we're going to drop files into incoming, watch them get processed, and then they'll move into processed, which means incoming won't hold on to them. If our only copies of test invoices live there, we'd be permanently moving them around just to run the same test twice. Sample invoices is an untouched, permanent set. Whenever we want to retest from scratch, we copy from there into incoming and the originals stay put. Now the environment. Same pattern as every other project. That file lists 6 packages. 1 for reading PDFs, 1 for handling images, 1 for calling the Gemini API, 1 for writing to Google Sheets, 1 for authentication, and one for watching a folder for changes. Notice we're listing packages for things we haven't built yet. We won't touch most of these for a few lectures, but installing everything up front means we never have to stop mid-project to reopen a terminal and install one more thing. The environment is fully ready, even though the code isn't yet. Now, the invoices themselves. And this is the part that actually matters most. There are 3 sample invoices, and every one of them is broken in a specific, deliberate way. This isn't sloppiness. Clean, uniform invoices would teach us nothing, because real invoices never look like each other. The first, from Golden Wheat Milling, is the well-behaved one. A clear invoice number, a clean date, a labeled total. This is our baseline. If the pipeline can't handle this one, nothing else matters yet. The second is from the same supplier, but nothing about it matches the first. The company name is lowercase and informal instead of properly capitalized. The date's written in a completely different format. The invoice number appears without any prefix and in a different position on the page. And there's no line labeled total at all. It says amount due instead. Every one of these is something a rigid, rule-based script would trip over immediately, and exactly the kind of variation we're about to ask an AI model to handle instead. The third, from a completely different supplier, is the trickiest one. It has no invoice number field at all. It simply doesn't exist on the page. The date is written out in words. And underneath the line items, there's a subtotal, a loyalty discount, and only then a final total, meaning the total isn't a single number sitting next to the word total, it's the result of 2 other numbers combining. There's also a handwritten style note at the bottom that has nothing to do with any of the actual data. This lecture's job is just to have the folders in place, the environment ready, and 3 genuinely different invoices sitting and waiting. Next, we teach the script to notice the moment one of them lands in the incoming folder. We already know how to watch a folder. We built that pattern back in the Files and Folders module. This lecture applies that same idea to the incoming folder, but with 2 problems that only show up once real invoices start landing in a real folder, not tidy test files copied in one at a time. In this code example, we set up a folder to watch and a short list of file types we actually care about, PDFs and a few common image formats. Then we build a handler that reacts every time something new appears in that folder. The first thing it does is ignore anything that isn't a file we recognize. The wrong file type, or a folder instead of a file, gets skipped immediately. If it's a type we care about, and we haven't already reacted to this exact file, we mark it as seen, then wait to make sure it's actually finished arriving before we do anything with it. Once it's confirmed stable, we print that a new invoice was detected, and hand it off to a function that will eventually process it. For now, that function is just a placeholder printing a line saying what it would have done. At the bottom, we start the watcher running continuously, checking once a second, until it's stopped with Ctrl+C. Run it, then drag one of our sample invoices into the incoming folder. You should see, new invoice detected, followed by that placeholder line. The processing function doesn't actually do anything yet. It's a stand-in for the extraction logic we build next lecture. Right now, this lecture is only about noticing a file arrived, correctly and exactly once. That exactly once is doing more work than it looks like, and it's the first real problem here. Watching for file-created events sounds like it should fire once per file, but depending on how a file actually lands in that folder, some tools trigger a created event, and then immediately a separate modified event for the same file. Without any protection against that, a single invoice drop could get processed twice, and 2 identical rows would end up wherever this data eventually lands. That's what our already seen set is for. It remembers which files we've already reacted to, so a second event for the same file gets silently ignored. It's a lightweight fix, not a permanent one. If the script restarts, that memory disappears, and true duplicate protection across restarts is exactly what we build a few lectures from now. The second problem is subtler, and it's the one that actually corrupts data instead of just duplicating it. A created event fires the instant the operating system creates the file entry, not when the file is finished being written. If someone's uploading a large scanned invoice or copying one in over a slow network drive, there's a real window where the file exists, has a name, and has 0 or partial bytes in it. Try to open and read that file immediately, and you'll either get an empty result or a permissions error, because whatever's still writing to it hasn't let go of the file yet. The stability check solves this the simplest way that actually works. It checks the file's size, waits half a second, checks again, and only calls the file ready once its size stops changing across a few consecutive checks. If it never stabilizes, the checks run out while the file's still growing, or the file vanishes entirely. We skip it and log Y, rather than crashing on a half-written file. One more small but deliberate choice. Notice the very first check inside our handler looks at whether the event is for a directory, and bails out immediately if so. The folder watching library fires events for folders being created too, not just files. And without that check, the moment someone makes a subfolder inside incoming, this handler would try to treat a directory as an invoice. And that's the watcher, doing exactly one job well, noticing a real, fully written PDF or image the moment it lands, and nothing else yet. Next, that placeholder function stops being a placeholder. That's where the actual reading starts. Time to make our processing function actually do something. Right now, we've got a folder that correctly notices when an invoice shows up. But noticing isn't the hard part of this project. Reading it is. In this code example, we start by loading our API key from a .m file using a small library called python.env, so the actual key never has to sit typed out inside the script itself. Then we set up a connection to the Gemini API, deliberately handing the key in ourselves rather than letting the client go searching for it on its own. More on why in a moment, and write one prompt we'll reuse every time. Read this invoice and tell me the vendor name, the invoice number, the key date, and the total amount due. Then comes the part that actually matters most. We write a function that pulls text out of a PDF using PDF Plumber, the same tool we used back in the PDF module. But before trusting that text, we check how much of it there actually is. If it's less than about 20 characters, that's a strong sign this PDF doesn't have real text inside it at all. It's actually a scanned image or a photo that got saved with a PDF file ending. In that case, instead of sending empty text to the model, we convert that page into an actual image and send that to Gemini directly, since it can read the picture itself with no separate step to pull text out first. And if the file was never a PDF to begin with, a phone photo saved as a JPEG or PNG, we skip straight to sending it as an image, since there was never any text to pull out in the first place. Back in the watcher, the placeholder function from last lecture finally gets replaced with the real thing. It hands the file off to our new extraction logic and prints back whatever comes out. Let's walk through why this is built the way it is, because two decisions here matter more than the API call itself. First, notice this doesn't treat every PDF the same way. Our two golden wheat invoices have real, selectable text sitting inside them, the kind you could highlight and copy in a PDF viewer. So we pull that text out and hand the model plain words. That's cheaper, faster, and more reliable than sending an image whenever real text is available. But not every PDF actually contains text. A scanned invoice, or a photo of a paper invoice someone saved as a PDF, is really just a picture wearing a PDF's file ending. The text extraction step will happily open it and hand back an empty result because there's no text layer to find. That's exactly the trap we flagged back when we built the sample invoices. And it's why we check the length of whatever text comes back before trusting it. Second, actual image files, a phone photo of an invoice, skip the text extraction step entirely and go straight to the model as an image. There was never any text to pull out in the first place. Go ahead and run the watcher now and drop the first golden wheat invoice into the incoming folder. You'll see it correctly pull real text and send that to the model. No scan fallback triggered, since this one has a genuine text layer. Try the dairy invoice too. Same path, different invoice. Now look closely at what actually comes back. It's a real, readable answer. The vendor, the invoice number, the date, the total, all correctly identified even with a company name in lowercase and a total buried under a subtotal and a discount. The model is genuinely handling variation a rigid script never could. But look at the shape of that answer. It's a paragraph. Maybe it says Vedder, Golden Wheat Milling Co., on one line this time, and the vendor is Golden Wheat Milling Co. If you run it again 5 minutes from now, that's not a mistake. That's just how a language model naturally talks. And it's a real problem the moment you try to do anything with this, besides read it yourself. We can't reliably pull a specific field out of a sentence that might be phrased 3 different ways across 3 different runs. That's exactly the gap we close next. Instead of asking for an answer we have to read, we're going to force the model to hand back something a script can actually pass, the same shape, every single time. Last lecture ended on a real problem. The model gives correct answers, but as a paragraph phrased slightly differently every time we ask. We can't build anything reliable on top of a sentence that might read 3 different ways across 3 different runs. What we actually need is the same answer, shaped the same way, every single time, and that's not something you get by asking politely in the prompt. It's something you have to force at the API level. In this code, we start by describing the exact shape we expect an answer to take. A vendor name, an invoice number, a date, and a total, each with a specific type. This description isn't doing anything on its own yet. It's the shape we're about to hand to Gemini and say, give me an answer that fits this, exactly. Then we update our 2 extraction functions to actually enforce that shape. 2 new settings are doing the real work here. One tells Gemini the reply must be valid JSON, not a paragraph, and the other tells it exactly which fields that JSON needs to contain, and what type each one is. This is a meaningfully different guarantee than just adding, please respond in JSON to the prompt text. A prompt is a request, and models sometimes still wrap a JSON reply in explanation. or in a formatting block, or invent an extra field you didn't ask for. A schema is enforced structurally by the ACE itself. The response gets validated before it ever reaches you, and what comes back is an actual usable object, not text you still have to interpret yourself. That's also why the prompt itself needed a small edit, worth pointing out, since it explains a value we'll actually see. The instruction now specifically says the total should come back as a plain number, no currency symbol. Without that, a model can technically satisfy "give me a number" by handing back the text $276.75, which fails the moment our code tries to treat it as an actual number. Back in the Watcher, we update how we print the result to match this new shape. Instead of printing one blob of text, we print each field on its own line: the vendor, the invoice number, the date, and the total. Run it against all 3 sample invoices now, one at a time. Golden Wheat's clean invoice comes back exactly as expected. The messier Golden Wheat invoice, lowercase name, different date format, amount due instead of total, comes back in the exact same shape as the first. Every field correctly identified despite looking nothing like it on the page. And the dairy invoice, the one with no invoice number field at all, comes back with its invoice number set to not found, because that's precisely the instruction we gave the model back when we wrote the prompt. And now that instruction has somewhere reliable to land. That last one is worth sitting with for a second. We haven't written a single line of code that checks whether an invoice number exists. The model handled that ambiguity itself, and we simply gave it a place to put the answer either way. But notice what we still haven't done. We're printing this, not checking it. If Gemini ever gets the total wrong, or somehow still can't produce a valid number, this code will happily print a broken result, or crash outright trying to format an empty response as a number, with no warning that anything went wrong. Getting a consistent shape back was the goal of this lecture. Trusting what's inside that shape is a different problem entirely, and it's the very next one we solve. One small housekeeping note. This lecture uses Pydantic directly in our own code for the first time, rather than it just riding along as something Gemini's package needed internally. Add it to your requirements file now, so the environment stays fully described for anyone setting this project up fresh. Last lecture ended with a warning. We're printing a nicely shaped result, but we've never once checked whether the values inside it actually make sense. A valid shape isn't the same thing as a correct answer. Getting the total back as a real number instead of a sentence tells you nothing about whether that number is right. In this code, we build the check we've been missing. It looks at 4 things: whether the vendor name is actually filled in, whether the invoice number came back as not found, whether the total is a sensible positive number, and whether the date can actually be understood as a real date. That last check does something extra worth noticing. It doesn't just check the date, it rewrites it. Using a flexible date parsing library, whatever format the date arrived in gets converted into one consistent format before we move on. Back in the Watcher, the processing function finally does something with the result besides print it. If nothing at all came back from extraction, it says so and stops there rather than crashing. Otherwise, it runs our new validation check, prints each field as before, and then either says everything looks good, or lists out exactly what needs a second look. Notice this doesn't reject anything outright. The validation step doesn't crash the script or refuse to continue when something looks wrong. It collects a list of concerns and hands them back. That's a deliberate choice. An empty invoice number isn't necessarily an error. It might genuinely be true of that invoice, the way it is for our dairy supplier. The right response to that isn't to block the pipeline. It's to flag the row so a human glances at it before it gets treated as final. Validation here means earn my trust, not pass or fail. Run this against all 3 sample invoices, and each one tells a different story. Golden Wheat's clean invoice sails through with no problems. Vendor present, invoice number present, a positive total, a date that passes cleanly. The messier Golden Wheat invoice also passes clean, even with its lowercase name and unusual date format, which is exactly the point of everything we built the last 2 lectures. Correct data, however oddly formatted on the page, still validates. And the dairy invoice gets flagged, specifically and only for the one thing actually missing from it. No invoice number. Everything else about that invoice. The total that required subtracting a discount from a subtotal. The date spelled out in words. Passed cleanly, because the model got all of it right. That date parsing step deserves a second look, because it's quietly doing something beyond validation. It's normalizing. 3 completely different looking dates, written 3 different ways, all come out the other side in the exact same format. That matters a lot the moment this data lands somewhere like a spreadsheet a few lectures from now. A column that's supposed to hold dates is far less useful if a third of its entries are unsortable text in 3 incompatible formats. Now, an honest limitation worth naming rather than hiding. This validation can't actually verify that the total is arithmetically correct, because we never asked the model to extract the individual line items it added up to get there. We're checking that the total is a real positive number, not that it's the right one. If Gemini ever misreads a quantity or fumbles a percentage on a discount line, nothing here would catch it, because there's no second number to check it against. That's a genuine gap, and it's exactly why a project like this should never fully remove a human from reviewing what gets extracted, particularly on anything involving real money. Validation catches missing and malformed data reliably. It does not replace judgment on numbers that merely look plausible. For now, flagged for review versus looks good is our line, and it's a real one. Even without full arithmetic verification, we've gone from blindly trusting whatever came back to actually knowing which invoices deserve a second look before anyone acts on them. We've got clean, validated data sitting in memory, and every time this script finishes, that data disappears with it. Time to give it somewhere permanent to live. A running log the bakery owner can actually open and read without ever touching Python. In this code, we set up a connection to a specific Google Sheet by its ID, using a service account rather than a personal login. Then we write one function that takes the extracted data, the list of problems from validation, and the name of the file it came from, and turns all of that into a single new row appended to the sheet: the date, the vendor, the invoice number, the total, whether it needs review, why, and which file it came from. Back in the Watcher, this slots in right after validation, immediately after we decide whether something needs a second look. First decision worth explaining. Authentication here uses a service account, not the login flow we used elsewhere in the Google Workspace module. That choice isn't arbitrary. A login flow is built around a human clicking allow in a browser, which is exactly the thing this project doesn't have. This script runs unattended, watching a folder with nobody sitting there to approve a login prompt. A service account is a separate robot identity Google issues specifically for this. No browser, no human approval step, just a credentials file this script reads directly. This is the same choice the Google Workspace module frames as choosing between service accounts and OAuth correctly. And an unattended folder watcher is precisely the case that Answer was built for. Setting one up gives you a credentials file and an email address that looks nothing like a real one. Something like invoice-bot at your projectid.iam.gserviceaccount.com. Here's exactly how to create one, click by click. Open the Cloud Console, and instead of hunting through menus, just type Service Accounts straight into the search bar at the top. It jumps you directly there. Click Create Service Account. Give it a name, something like InvoiceBot, and an optional description, then click Create and Continue. The next screen asks about roles. For this project, you can skip that entirely and just click Continue, then click Done. You'll land back on the Service Accounts list, and your new one will be sitting there. Click the email address of that service account to open it, then click the Keys tab along the top. Click Add Key, choose Create New Key from the drop-down, select JSON as the key type, and click Create. That immediately downloads a file to your computer. This is the real credentials file, the one with client email and private key inside it. Not the kind we accidentally grabbed earlier. Move that downloaded file into your project folder, and rename it to match what the code expects, exactly. Credentials.json. The credentials file is a real secret, every bit as sensitive as the Gemini key we protected a few lectures ago. Anyone holding this file can act as that service account against your sheets. It gets excluded from version control right alongside the .env file, and it never gets committed. There's a second setup step that's just as easy to skip, and it breaks in a way that looks nothing like what actually caused it. Creating a service account does not automatically give it access to your spreadsheet. You have to open the actual Google Sheet, click Share, and add that strange service account email exactly like you'd add a coworker, with editor access. Skip this, and opening the sheet fails with a permissions error, even though the sheet obviously exists, and this code is pointed at the right one. The sheet isn't missing. The robot just was never invited to it. Now think about what actually gets written into each row. Because it isn't just the 4 fields we extracted. The status and the notes column come directly from last lecture's validation. This is the entire reason that lecture built a list of problems instead of just a pass or fail. A bakery owner scanning this spreadsheet doesn't need to open the script or read a log file to know which rows need a second look. The sheet tells her directly. In a column, she can filter on. The source file name rides along too, so if something ever does look wrong, there's a direct trail back to the exact invoice file that produced this row. One setup step worth doing once by hand before any of this runs. Add a header row to the actual spreadsheet. Date, vendor, invoice number, total, status, notes, source file, matching the exact order this code appends in. Appending a row always adds to the very next empty row, so it has no way of labeling columns for you. If you skip this, the sheet works fine but reads like an unlabeled wall of numbers to anyone except you. Run the full pipeline now. Drop all 3 sample invoices in one at a time and open the spreadsheet. You'll see 3 new rows, 2 marked OK, and the dairy invoice marked Needs Review. Its actual problem sitting right there in the notes column. In plain English, exactly where someone would look for it. Back when we built the watcher, we flagged something on purpose and left it unfinished. The already seen set catches a duplicate event within a single run, but it lives in memory. The moment this script restarts, that memory is gone, and every invoice we've processed since then is still sitting in the incoming folder, exactly where it landed. We built a processed folder all the way back in this project's first lecture for precisely this reason. Let's finally use it. In this code, we write a function that takes a file sitting in incoming and moves it into the processed folder. Before moving anything, it checks whether a file with that same name already exists there. If it does, it doesn't overwrite it. It adds a timestamp to the new file's name first, so both files survive side by side. Then, back in our processing function, this archiving step goes at the very end, deliberately after the row gets written to the spreadsheet, not before. 2 decisions here are doing more work than they look like. First, order. Archiving runs after the sheet gets updated, never before. If the sheet's call failed, a network hiccup, an API limit, anything, and we'd already archived the file first, we'd end up with an invoice that's permanently marked handled by its location on disk, with no row in the spreadsheet to show for it. That data would be gone, and nothing about the file system would tell you it ever existed. Archiving last means a crash mid-process leaves the file sitting in incoming, looking exactly like it hasn't been touched yet, which is actually the truthful state to leave it in. Second, notice this checks whether a file with the same name already exists in process before moving anything. 2 different suppliers can easily both send a file literally named invoice.pdf. Without this check, the second one silently overwrites the first the moment it's archived. The original invoice doesn't error out, doesn't warn you, it just quietly stops existing. A timestamp gets appended only when a collision actually happens, so the folder stays readable for the common case, and still protects you the moment 2 files genuinely do collide. Now here's the actual shift worth understanding, not just the code that implements it. Before this lecture, have I processed this invoice? Was a question only answerable by an in-memory set that vanished on every restart. After this lecture, it's answered by something durable. A file sitting in incoming means not yet handled. A file sitting in processed means it is. The folder itself is the record now, not a variable that happens to still be alive. That's a meaningfully more trustworthy kind of memory. Restart this script as many times as you want, and it never loses track of what it's already done, because the proof isn't held in the program anymore. It's held on disk. One honest gap, worth naming rather than hiding. There's still a narrow window between the sheet row being written and the file actually being moved. If the script gets killed in that exact instant, the invoice is logged, but the file is still sitting in incoming, looking unprocessed. It's a real edge case, and closing it completely would mean checking the spreadsheet itself for a matching invoice number before ever appending a new row. A stronger, slower kind of protection that's worth knowing exists. Even though it's beyond what we're building here, run the full pipeline one more time against all 3 sample invoices. Each one now leaves incoming empty and lands correctly in processed, sitting there as permanent physical proof this script did its job. Even if you close the terminal, restart the computer, or come back to this project next week. Every scheduling tool we've used so far shares one assumption. The script runs, finishes, and exits. The bakery report generates a file and quits, and everything else we've scheduled behaves the same way. This pipeline doesn't. Our invoice watcher is meant to run forever, sitting there watching a folder in real time. That's a genuinely different scheduling problem, and it rules out one of our usual tools immediately. GitHub Actions is out, completely, not because it's the wrong fit stylistically, but because it's built around jobs that start, do something, and finish, typically within minutes. A workflow that's supposed to run indefinitely doesn't fit that shape at all. You'd either have it killed by a runtime limit or be fighting the platform the entire way. What we actually need isn't run this on a schedule. It's keep this alive permanently and bring it back the moment it isn't. On Windows, Task Scheduler can still do this, just configured completely differently than it was for the bakery report. Instead of a daily trigger at a fixed time, set the trigger to @startup, so the watcher comes back automatically the moment the computer restarts. Then, in the Task Settings tab, there are 2 checkboxes that matter far more here than they did before. If the task fails, restart every. Set that to something like 1 minute, so a crash gets automatically retried. And critically, if the task is already running, then the following rule applies set to do not start a new instance. That second one isn't optional polish. If Windows ever started a second copy of this watcher while the first was still running, you'd have two separate processes, both watching the same incoming folder, both capable of grabbing the same file. And every bit of the idempotency work from last lecture would be fighting against two watchers, instead of protecting against one. On Mac or Linux, cron isn't actually the right tool here either, for the same reason GitHub Actions isn't. Cron runs things periodically, not continuously. The equivalent job goes to a process supervisor instead. A tool called Launchid on Mac, or a systemd service on Linux, both configured to keep the process alive indefinitely and restart it automatically if it ever dies, the same way Task Scheduler's restart setting does on Windows. The concept transfers directly, even though the tool's name changes. This is worth knowing exists, even if we don't build it line by line here. Set up either version, and this pipeline stops being something you have to remember to run at all. Step back and look at everything sitting behind that one restart setting. A folder that notices a new invoice the instant it lands, whether it's a clean PDF or a photograph of a receipt. An AI model that reads it despite messy formatting, missing fields, or a total buried under a discount. A validation step that decides what deserves a second look instead of blindly trusting every number. A spreadsheet that ends up as the single source of truth, readable by someone who's never opened this code. And a folder of archived files proving, permanently, exactly what's already been handled. None of that required a person to be present for any single invoice. Thanks for watching. If you like this video, make sure to hit the like button and subscribe for more courses. See you in the next video.